being able to hear the audio.
Maybe Arjun, we can invite the next Dr. Arjun. We can invite the next speaker.
Sure, sir. Sure.
That is better.
Okay, sir. Manojit sir, so we'll come back to you later on. The second speaker is Dr. Rakhi Khandelwal. So the topic of her presentation will be synthesis of silver nanoparticles by low-cost, sustainable method using glycerol extract. Manojit sir, so we'll come back to you once your technical difficulties are sorted. So, ma'am, can you begin your presentation, ma'am?
Yes. Good morning, sir. Good morning to all the dignitaries and participants. Am I audible, sir?
Yes, you're audible,
Yes.
ma'am. Could you share your screen?
Very warm good morning to all of you.
Yeah.
Let me share my slides, sir.
Yes, sure.
My slides are visible, sir?
No, ma'am. It's not visible yet, ma'am. Yes, it is. It is starting the presentation. Yes, it is. But we are not.
Now it is visible, sir?
Yes. You can start the slideshow, please.
Shall I start?
Yes.
Okay. So once again, a very warm good morning to all the dear participants or all the dignitaries of this esteemed conference. Myself, Dr. Rakhi Khandelwal, Assistant Professor Chemistry at Government Mahila Engineering College, Ajmer. I am presenting my research work on synthesis of silver nanoparticles by low-cost sustainable method using Glycyrrhiza glabra extract. The outline of my presentation includes introduction, materials and method, characterization, conclusion, and future perspective. We know that the fabrication of nanoparticles by means of environmental friendly method is an expanding arena of nanotechnology. Here I am presenting my work on synthesis of silver nanoparticles by using root extract of plant Glycyrrhiza glabra. Basically, three main things are very important in this research work, that is the silver nanoparticles. Second one is the method which we have used to synthesize this nanoparticle, that is the green synthesis method. And third is the plant which is using for the green synthesis method, that is the Glycyrrhiza glabra. So first question comes to our mind that why we focus our studies on the silver nanoparticles. The reason behind choosing the silver nanoparticle is that due to the very important optical, thermal, electrical, biological properties of silver nanoparticles. These are gained lot of attention of the researchers, and due to these applications, the silver nanoparticles are very useful in biomedical, catalytic, and various industrial applications such as human healthcare, cosmetics, water treatment, textile, imaging, and biosensing. That is why we focus our study on silver nanoparticles. Second important thing is the green synthesis method. So what is the green synthesis? Basically, the green synthesis methods are the methods which are using less chemicals and the energy saving method, that so that we can save our environment. In the traditional chemical method of the synthesis for silver nanoparticles, generally the silver nitrate is used as a source of silver ions. Then we are using the sodium boron hydrate as a reducing substance and potassium bromide as a stabilizing agent, and one more chemical, that is sodium citrate, is added for the buffer solution. So in the traditional chemical synthesis method, we are using four chemicals, and temperature is also high required in this chemical traditional method. But when we are using the green synthesis method, sodium boron hydrate is not required, potassium bromide is not required, and sodium citrate is also not required. So in place of these four chemicals, we are using only two things, that is sodium nitrate, which is the source of silver ions, and second one is the plant extract. So instead of using reducing substance, caping agent, and buffer solution, three chemicals, we are using the plant extract only. So this is the very promising synthesis method. It is eco-friendly, cost-effective, energy and time-saving method. It can be easily manageable and scaled up on large scale. We know that the green synthesis method can be done by using microorganisms and by using the plant extract. But we focus our study on the synthesis by using the plant extract only. Now, third important thing is the selection of the plant Glycyrrhiza glabra. We are choosing the plant Glycyrrhiza glabra for our studies because this plant is available at low cost in Asian and European regions. It is edible and has no toxic constituent, which make it suitable for the preparation so that the synthesized nanoparticles can be used for medical applications also. The phytochemicals present in the extract of roots of Glycyrrhiza glabra act as a reducing as well as the capping agent. So no other additional chemical is required in this synthesis. Only one silver nitrate solution is required. Now coming towards the synthesis part, as I already shared that this is the one pot synthesis method including no chemical other than the silver nitrate. So only two things are required. One is the root of Glycyrrhiza glabra and second one is the silver nitrate. To prepare the extract of roots of Glycyrrhiza glabra, we purchase the dry root from the local market. It is easily available in the local market and then washed it properly with the distilled water. After drying the dry roots, we powdered them. And 1 gram of this dry root powder is soaked in 100 ml of distilled water for 20 hours and then filtered. The filtrate was then centrifuged for 15 minutes at 5000 rpm to get the extract of Glycyrrhiza glabra. Second one is the silver nitrate solution. We prepared the 0.01 m strength silver nitrate solution. Now the synthesis part. For the synthesis of silver nanoparticles, the root extract was added to the silver nitrate solution in 1:10 ratio. The color changes from transparent to yellowish and then reddish brown, indicated the formation of silver nanoparticles. Then this colloidal solution was centrifuged for 15 minutes to obtain the silver nanoparticles in the solid state, which is then dried and collected as a dry powder of silver nanoparticles. We know that in the solution of silver nitrate, the silver nitrate dissociates into silver ions and nitrate ions. The biomolecules present in the plant extract of roots of Glycyrrhiza glabra reduces these silver ions, which results the creation of silver atoms in the solution, which are then agglomerated into oligomeric clusters. Now, these oligomeric clusters resulted in the formation of silver nanoparticles, and the proteins present in the plant extract act as a capping agent to stabilize these silver nanoparticles. In this way, we have synthesized these silver nanoparticles by using the plant extract. Then, the synthesized nanoparticles have been characterized by UV visible absorption spectroscopy, X-ray diffraction measurements, scanning electron microscopy, energy dispersive X-ray analysis, transmission electron microscopy to probe their morphology, crystalline structure, size, and phase detection. First, we have performed the UV visible absorption spectroscopy for the synthesized silver nanoparticles, and the in the UV spectra, we obtained the SPR band at the 369 nanometer. We know that the valence band and conduction band of silver nanoparticles are relatively close to each other, which allows unrestricted electrons mobility. And due to the simultaneous oscillation of electrons in resonance with the incident light wave, these electron generates the surface plasma resonance band. And for our synthesized nanoparticles, we obtained this SPR band at 369 nanometer, which confirms the formation of silver nanoparticle. Bands at lower frequency, that is at around 260 nanometer, is also obtained, which could be due to the transition involving silver nanoparticles with higher multipoles. In this spectra, multipole transition is noticeable, which indicated that the symmetry of silver nanoparticle is less than that of the sphere. So two main conclusions we have drawn with the UV visible spectra. First is the conformation of silver nanoparticles. Second is about the symmetry. That is, symmetry is slightly lesser than the spherical. Then the XRD measurement has been done to probe the crystalline nature of silver nanoparticles. The XRD pattern of synthesized nanoparticles reveals the silver oxide nanoparticles also, along with the silver nanoparticles. The peaks at 38.1, 44.3 degree, 64.4 degree, and 77.4 degree and 81.4 degree are corroborating with the standard silver JCPDS, while the peaks at 27.8 degree, 32.2 degree, and 46.2 degree are corroborating with the standard JCPDS of silver oxide. So the XRD measurement shows presence of silver oxide nanoparticles also in the synthesized particles, and it can be inferred that the nature of the synthesized nanoparticle is crystalline in nature with the crystal structure face-centered cubic. That result is concluded from the XRD data. Second important thing, that particle size calculated from the XRD data using Debye-Shrazad equation is 36.4 nanometer for silver nanoparticles. Though these are the main conclusions from the XRD measurement, that is, crystal structure of nanoparticles is face-centered cubic and the particle size is 36.4 nanometer. For further structural analysis, we have performed Rachel refinement also. It shows that the phase fraction of silver and silver oxide nanoparticle is in the ratio of 68:32. It is clearly exhibited the presence of silver nanoparticles as the major phase. Then the qualitative elemental composition information about the synthesized nanoparticles recorded by energy dispersive X-ray analyzer. It reveals the formation of silver nanoparticles in the significant amount. We have also performed the scanning electron microscopic analysis for the synthesized nanoparticles. The SEM images shows that the silver nanoparticles are polydispersive and crystalline in nature. But the size calculated by SEM images is slightly higher than the size calculated by XRD measurement. This may be due to the fact that in SEM images, we have calculated the size of agglomerates. And we know that due to the high surface energy, the silver nanoparticles easily clump up together to form the agglomerates. That is why slightly bigger size is obtained in the SEM analysis. Then the transition electron microscopic analysis we have performed. The TM images shows clear lattice fringes which assures the crystalline nature of the synthesized nanoparticles. Then the selected area energy dispersion shows concentric circles, which are due to the polycrystallinity of the synthesized nanoparticles. So the TEM images shows the crystalline nature and the spherical shape of the synthesized nanoparticles, while the SEAD confirms the polycrystallinity of the silver nanoparticles. So these are the characterization of our synthesized nanoparticles, and the conclusions we have drawn from our research, that this approach produces silver nanoparticles in a clean, non-toxic, eco-friendly, cost-effective, and efficient manner at room temperature without any additive. The silver nanoparticles were produced in around 68% with a particle size of 36.4 nanometer. The shape of the synthesized nanoparticle was found to be spherical and the crystal structure was face-centered cubic. We have successfully synthesized the stable nanoparticles following the third and ninth principle of green chemistry, which stated that third principle stated that Wherever practicable, synthetic methods should be designed to use and generate substances that possesses little or no toxicity to human health and environment. Since we are using the plant extract only, other than the silver nitrate, so it is very eco-friendly synthesis method. Second, the ninth principle of green chemistry is the energy efficiency, which stated that the energy requirements of chemical processes should be minimized considering their environmental and economic impacts. The synthetic method should be carried out at ambient temperature and pressure. And we know that our synthesis method is carried out at room temperature. So it is the very energy saving method also. Future prospects of our research work. We are looking forward to find out the biomedical applications of these synthesized nanoparticles, especially in the cancer therapy. Why? Because the research work already done on this application part on various biomedical applications proved that cytotoxic toxic features of silver and silver hybrid nanoparticles are cell type dependent, and in this domain the higher cytotoxicity was recorded against cancer cell compared to the non-cancerous fibroblasts. This stimulates us to investigate the possible applications of synthesized nanoparticles as potential cancer inhibitor. And since we have used the edible plant extract for this synthesis, which make the silver nanoparticles more biocompatible for human being and environment. So we are pro- very hopeful to find out some positive results. These are some references. I express my immense thanks to Technical Education Quality Program, 3rd Rajasthan Technical University Kota, for providing financial assistance for this research work, and also thankful to UGC DEA CSR Indore Center for providing XRD, SEM, EDX, and TEM studies facilities. And not I am also thankful to the organizers of this esteemed conference to provide me opportunity to present my research work at this grand platform. Thank you.
Thank you, ma'am. So for this very insightful talk, maybe we can have one or two questions from the audience.
So you are not audible.
Um,
Pathway for the synthesis, because these plant extract will have a lot of phytochemicals. Could you follow a mechanistic pathway? That's a very challenging task. Could you look into that aspect? How the plant extract really support the synthesis process, the mechanistic pathway?
Not really, sir. Exact mechanism we could not find yet, sir. But your suggestion is very well. We will try to find out exact mechanism for the chemicals used in the plant extract, for the chemicals present in the plant extract.
Right. Okay. Thank you. That could be of interest to you also. Yes. Thank you.
yes.
Thank you, sir.
Thank you, sir. Can we move on to the next talk for the?
Thank you. Let us.
Yes.
Thank
you.
you.
Manojit sir, is your mic ready? So maybe we can go to your talk and then go to the third one. Is your ready?
Yes, sir. Right now, I think I am audible to everyone.
Yes,
Yeah?
you're audible, sir. Yes, sir. You can start your presentation, sir.
Okay. I'm just carrying it doing that.
Please upload. Yeah.
Yeah. Yeah. My
Yes.
screen is available to everyone. Is it
Yes,
visible?
sir. It is visible, sir. It is
Okay,
visible.
okay, okay, okay. Thank you, thank you. Sorry for the technical inconvenience. Okay.
Yes.
Uh, First of all, I am very much thankful to the organizer for giving me opportunity for that talk for this piece of work of our ongoing project. That is synthesis and structural vibrational studies on lanthanum cobalt ferrite. And I'm Dr. Monoji De from Choksha Group of College Bilaspur, it is in Chhattisgarh. And I did my PhD, I completed my PhD from Guru Kashida Central University, it is in Chhattisgarh itself. Okay. Now coming to the schematic presentation, summaries of the presentation, that is the first, the basic structure of the spinels and then the experimental details, how this nanoparticle gets synthesized, and the result and discussions and conclusion, future aspects, and some acknowledgements are there. First of all, coming to the spinal structure, this is the one special type of structure, spinal structure, where basically the general formula is like AbO3, and this is the mixed phase of the tetrahedral. A side is basically that tetrahedral, and B side is octahedral. Cations are there, and oxygens, that O represent that oxygen, and this is the octahedral side, and this is the tetrahedral side. 1 cubic unit cell of cubic structures. There are 64 tetrahedral sites and 32 octahedral sites present here. And according to that distribution of the cations, that is A site as well as B site, that cations, these are categorized in different cases like that normal spinal, inverse spinal, or mixed spinal, like that. And if we go to how it is distributed, if we looking about that, if Fe ion, that is it is only at the B side, then it is the normal spinal structure. That example for the normal spinal structure is the zinc ferrite. And if that Fe3 plus ion, that is well distributed among the A site as well as B side, then it is the inverse spinal structure. The example for this one, that nickel ferrite, cadmium ferrite, and cobalt ferrite also there, copper ferrite is also there. Now, why this spinal structure or spinal materials are so much interesting? Because it has the enormous number of applications depending on the different synthesis method. And if we can play that morphology, structure, composition, as well as different structure and substrate issue, that strategy you can follow to apply in the different application part, that we can apply the supercapacitor, metal and batteries, and water splitting, like laser devices, as well as magnetofluid. Enormous number of applications are there. Now coming to the objective of this presenter, because the cobalt ferrite has a lot of attention because of the syntonic material, microwave absorption catalysis sensors in different purpose sensors, as well as lithium-ion batteries, and as well as biomedical applications are there. That's why cobalt ferrite is chosen here. And basically, objective of this work is to check or to enhance to check the magnetic properties of this material by doping that lanthanum in that B side. So now coming to that experimental section, there are various experimental processes that are available to synthesize the cobalt ferrite nanoparticles, like solid-state ceramics, solvent method, combustion technique, resonance method, and co-precipitation method, chemical synthesis, pulse laser deposition. All type of methods are available, and that as per our ability in our institute, we just use the combustion synthesis. Now coming to the workflow of this synthesis method, that first we take the precursors material like cobalt nitrate and ferric nitrate, and some citric citric acid was there. Mix all this, and by melting this material, this precursors material, then we just burn it on a just hot plate, and we just take out all the material and just grind it and make it calcine. Then it's grind it, making pellet for the different synthesis and sintering processes there. And after that, it is ready for the characterization. And anyone to check the phase or like the phase, so they can take the XRD as well after the calcination. And Now coming to the characterization synthesis from coming to the XRD spectra. Here it is the XRD spectra shows all the structure are the single phase final type of structure having the FT3M space group and phase identification using the high score class and connected with that ICDD PDF4 plus database, and from that database we just calculate, we just compare with the standard data of the cobalt thread, that is the ICDD number is here. All the peaks are here well matched with the ICDD data, and if we take the major peak, that is 311 peak, in a short range, we can find that shifting of that peak with respect to as we increase the lanthanum concentration. As the lanthanum ionic radii is larger, that's why it's shifting lower 2 theta direction, as that indicates the lattice parameter that will be increased. And now coming to the, if we calculate the lattice parameter by using this formula, and this follows that the lattice parameter also increases with the lanthanum concentration, and crystalline size you just calculate with the division formula, and it decreases with the increasing of lanthanum concentration. As we focus on that magnetic properties of this nanoparticle, doped nanoparticle, we just focus on that how that the jump length in that tetrahedral and octahedral side that can be calculated from this XRD data, that we just show here that as we increase the lanthanum concentration, this jump length will increases, then it will decreases also. Now, if we doping of any systematic system, then there will be some strain induced in that unit cell because of that foreign atom that just go and sit in that site also. That's why we just calculated the strain for the all the cases, that is the cobalt ferrite as well as 5% dope, 10% dope, and 15% dope of lanthanum ferrite. By using of the formula, Williamson-Hall formula, we just fit it in the straight line path, and we just calculated the strain in each case. From that Williamson-Hall plot, we can find that the strain value that will give by the epsilon in the previous, this epsilon will give us the strain value that produced in that in the unit cell. That value is initially it is decreasing, and after that it is the increasing. The data is here only. Now coming to the XRD overall, whatever the calculated we are valued, the lattice parameter that is continuously increasing as is shown in the figure, that major peak, that 311 peak, that continuously decreasing in the left hand side. The crystalline size is also decreasing as we increase the lanthanum concentration. The jump length in the octahedral side as well as tetrahedral side and as well as octahedral side we also calculated here. Okay. Now coming to the morphology and elemental analysis, this figure this is figure A. This is in the copper ferrite PO, and this is 5%, this is 10%, this is 15%. As we can see from that microstructure or morphology, it is a fluffy type of nature here. We just find out, and there is lots of pore and lots of pore here find out here only, and that's why this type of material basically we can use very water remediation of the heavy metal as well as heavy metals from the water as well as from the any sensor type of application we can do. And coming to the vibrational structure, we did that STR Raman microraman spectrometer, and that as the cobalt ferrite is the spinal structure, it from the group theoretical analysis we can find that it has 5 Raman active modes, and 5 Raman active modes are there. These Raman active modes coming with because of the vibrations of the oxygen ion with the at the tetrahedral side as well as octahedral side. The vibrations may be in different types like the symmetric stretching as well as asymmetric stretching, symmetric bending, asymmetric bending, like that. So now this I unfortunately I just missed it. There is A1G. This is because of the symmetric stretching of the oxygen anions, or EG modes, that is because of the symmetric bending of the oxygen ions, and T2, T2G1, T2G2, and T2G3. These phonon modes, basically the oxygen, these modes due to the asymmetric stretching of the oxygen atoms with respect to the tetrahedral and octahedral cations. Now, how we can find the structure, whether it is the spinal type or not. If we look into that Raman spectra, if we deconvolute this peak near about 680 centimeter inverse, this peak can be deconvoluted in two parts. That is the main characteristic structure or characteristic peaks for the. This is known as a shoulder peak. This is associated. This can find only this spinal structure only. So now coming to the conclusion, and this is one of the ongoing projects right now, and we are focusing on the magnetic properties of this doped material. So right now we just did this part only. Coming to the conclusion of this work, we just synthesized the lanthanum cobalt ferrite by using combustion technique, and from extracting just calculated different parameters also, and the same images shown that the gains are the porous type of nature and microstructure that changes the doping material by microstructure changes with the doping material, and Ir pattern confirms that elemental presence in that sample. In the Raman spectra, that confirms about that different Raman active modes present in that material, as well as the shoulder peak near about the 680 centimeters inverse, that confirms about the spinal formation of the spinal structure here. Now coming to the different feature aspect about the spinal ferrite, by different application of this material, we can different structure, we can use the different application for nowadays. That's why this spinal type of materials are very much interesting or very much well accepted for the research community. There are some few publications related to the spinal materials here, and I acknowledge to my Professor Dr. H.S. Tiwari sir, and I from the UGC University Grant Commission for providing me the fellowship during my PhD tenure. And this is one of the work of our MSc student, Mr. Sunil Kumar. And I just want to thank to all of my co-authors of the papers and collaborators. Thank you all.
Thank you, sir, for the interesting talk. So I think Professor Masahiro Yoshimura has a question.
Yeah. Okay. This case is the most important in the cobalt valency state, right?
Yes, sir.
And then
Yes,
there, I think, your case is the doping of the lanthanum, and it's not forming spinel, because in the spinel, lanthanum is too big. So the perovskite is easy to form, to mix phases. The reason why there's some limitation of the solubility of the lanthanum, it means of the perovskite coexisting and or dissolving lanthanum cobaltite, lanthanum iron oxide. Okay, that case cobalt 3 plus is easy to form. So that is looks like your magnetic data. I have not completely understood of all of them, but I just suggest you can look at our paper. Okay, RSC Advanced 2021. Okay, we have the valence stability of the cobalt and perovskite. Okay, so that you can look at, and then to check about that, and then we are now going to the spinel and the veraphosite, etc. But maybe you can better to look at that. Then we can discuss more.
Yeah,
okay,
sure,
it's my suggestion.
Sure.
Yes, cobalt 3 plus and lanthanum A side, perovskite.
Yeah. Thank you for your suggestion, sir. I'll look into that paper also.
Thank you, Professor. So do we have any more questions from the audience? Okay, we can move on to the next speaker for this session. Thank you, Manojit Desa. Thank you for the interesting talk.
Thank you.
Next, I would like to invite Dr. Shreyasi Sarkar to present her presentation on the resynthesis of silver nanoparticles using the freeze-dried leaf of Pederia fetida and its process parameter optimizations.
Am I audible?
Yes, ma'am, you're audible, ma'am.
Okay. My slides are visible? Hello?
No, ma'am. No, ma'am. I think we are yet to see your slides still.
Oh, no. Sorry.
Yes, ma'am. It has started presenting your slides. We'll be able to see it in
Okay.
short time.
Thank you for giving me opportunity to give a talk in ICN 2022. Now,
Ma'am, your slide,
I am Dr. Shreyasi Sarkar. Good morning, everybody. I will give
excuse
seminar
me.
on.
Your slides are not
Hello.
visible still. Your slides are not visible yet.
Now visible? Hello.
It is visible now, ma'am. Yes, ma'am.
Okay.
Can you go over the first slide and
Yes. Good
thank you, ma'am.
morning, everybody. I am Dr. Shreyasi Sarkar. I am going to give a seminar on green synthesis of silver nanoparticles using the freeze-dried leaf of Pederia foetida and its process parameter optimization. Now, the application of silver nanoparticles, it is mainly used in hospital, industrial settings, and biomedical fields. Why nanoparticles are important? Because it has unique properties like very small size, it has different shapes, it contains surface charge, it has high surface area to volume ratio, it has unique physicochemical and biological properties. AGNPs are mainly used as an antimicrobial agent in different areas like cloths, fabrics, water purification, toothpaste, deodorant, filters, washing machine, kitchen utensils, wound dressings, toys, etc. Now, what is green chemistry? Green chemistry is the use of different biological sources like microorganisms and plant portions,
Ma'am,
as for example,
excuse me, ma'am. I'm
roots,
sorry for interrupting you, but your slides are not changing as you change it.
not changing.
No, ma'am. No, ma'am.
Now,
No, ma'am. Actually, it is not. You have not gone into the slideshow mode yet. Yes, it is changing now only. It is you have gone on to the third slide. I'm being able to see it, but it
okay,
is
then
not
I
in
am
this.
doing in this mode.
Okay. Okay. Thank you, ma'am. Okay.
Now, use of different biological sources like microorganisms, plant portions, as per example, roots, fruits, stems, seeds, leaves, which contain both the reducing agent as well as the stabilizing agent. It produces metal nanoparticles without the use of polluting and toxic reagents. It improves the cytocompatibility and lower toxicity of the metal nanoparticles compared to the chemical synthesis. The process is simple, cost effective, environmental benign with improved product quality. Now, the main objectives of my study to synthesize the silver nanoparticles from the freeze-dried leaf extract, both aqueous as well as ethanolic of P. foetida leaves. Then to optimize the process operating parameters in the shaken Teflon container, investigating employing a response service methodology. Now, the concentration of the silver nitrate, temperature, and rotational speed are considered as factors, and the surface plasmon response peak centered within a wavelength of 420 to 450 nanometer for silver nanoparticles considered as response. Now, each factor were studied at 3 levels: high, medium, low. For concentration of silver nitrate, it is varied from 1:9, 1:7, 1:5 concentration. For temperature, it is varied from 50 degrees Celsius, 40 degrees Celsius, and 30 degrees Celsius. And for rotational speed, it is varied from 160 rpm, 140 rpm, and 120 rpm. This is the methodology. You can see from here, this is the raw P. foetida leaves, and it is kept in ILA freeze dryer unit 1200 for freeze drying for about 128 hours. We get this type of product. From this, we have prepared 3 solutions: D, E, F. D is totally aqueous, E is 50-50 ethanol and double distilled water, and F is 70-30 ethanol and double distilled water. Now, when we synthesize silver nitrate nanoparticles from this solution, F solution gave very less production, and D and E gave nearly equal result. But to make the process cost effective, we discarded this one and we proceed with D solution. This is the methodology. This is the synthesis of silver nanocolloids. 1 ml of leaf extract, either D or E or F, is mixed with 5 ml of freshly prepared 1 millimolar aqueous silver nitrate solution. It is kept at 30 degrees Celsius for 120 120 rpm for 120 hour. This is the 18 ml sealed Teflon container used for the study. And after that, we get this deep brown color silver nanoparticle solutions, and which give UV spectra at around 420 nanometer, peak around 420 nanometer. Now the results. We have performed 3 to the power 3 design of experiments for D. Now the factors were silver nitrate concentration, temperature, and rotational speed. The highest level of each factor is coded with 1, medium level is coded with 0, and the low level is coded with -1. And the response is considered as expressed as silver nanoparticle content. We have performed all total 27 experiments, and from that we get at run number 23 1.481 arbitrary unit, and at run number 25 we get very less production. Next is the analysis of variance table for the quadratic model of the freeze-dried P. foetida leaf aqueous extract. You can see from this table, P value is less than 0.05, which is here we get 0.001, less than 0.001. So the model is significant. And also the P value for different factors A, B, C are also less than 0.05. So all of them are significant to the model. Now yield is expressed as AGNP content in this is the equation of the yield, and you can see from this quadratic equation the factor A, B, C, all of them are significant. Next is the 3D interaction plot of AGNP's yield. You can see the interaction of AGN3 concentration and temperature with the yield of silver nanoparticles. Now, as the concentration of AGN3 increases, there is decrease in the AGNP content. And for temperature, there is initially increase in AGNP yield up to certain level, then there is a fall. This is a 3D interaction plot of AGNP yield by the freeze-dried P. foetida leaves, and you can see the effect of rotational speed and the temperature here. As the speed increases, there is increase in AGNP content, then there is a fall. For both temperature and AGN3, the pattern is same. This is the perturbation plot. You can see here the contribution of ABC in the same plot. As the concentration of A increase, there is decrease in yield. But for B and C, that is for temperature and rotational speed, there is initially increase up to certain level, then there is a fall. This is a normal plot of residuals for AGNP synthesis by the freeze-dried P40 leaf aqueous extract. Residual is the difference between the Y observed and the Y predicted. You can see the positive and negative values of residual are equally distributed along the straight line. So the model is significant. This is the relation, and this figure gives the relationship between the predicted and experimental values of AGNP's yield by the freeze-dried P40 leaf aqueous extract. These are the points which I have got from the experiment. All the 27 points are found to be equally distributed along the straight line. So the model is significant. Conclusions is that the model predicted the optimum conditions for the synthesis of AGNP content, that is 1.367 arbitrary unit at 1:5 silver nitrate concentration, 39 degrees Celsius and 142 RPM. When we perform the experiment using the same using the same optimum conditions, we get 1.391 arbitrary unit AGNP content with 1.73% error. So RSM successfully validates the optimum process parameters for the synthesis of AGNPs by the freeze-dried P40 leaf aqueous extract. These are the references.
Thank you,
Before
ma'am.
finishing my session, my presentation, I want to thank my supervisor, Dr. Deepankar Haldar, professor of FTB department, Jadavpur University, to guide me and provide me research equipments to carry out my postdoctoral research work. And I want to thank Professor Sabu Thomas sir and other dignitaries of ICN 2022 to give me opportunity to give invited talk in international conference for the first time. Thank you all.
Thank you, ma'am. I think Professor Yoshimura has a question for you, ma'am.
Okay, well, did you have check over the pH in the solution in the beginning and the end? Because Ag nitrate and then some additive, okay, stabilizer, the reducing agent should be. That case, the pH is very important. If it must be shifted to the more neutral or like alkaline. This case, the Ag will be precipitated as nucleated, cluster, nucleated, and growth. But if it was acidic, no. So that's the reason why you must check about of the pH in solution at the beginning, at the middle, and at the end. Okay? Did you have
Okay,
check
sir.
about
Okay,
the
sir.
pH?
No, I haven't checked it.
Please do that. And
Okay,
then
sir.
you can check over the intermediate compound, complex silver.
Okay,
Okay?
sir.
Complex
Okay, thank you,
silver,
sir.
and then there's some organic Ag complex. That
Okay,
is a
thank you,
make
sir.
cluster. Okay?
Okay.
In the
Okay.
pH high region.
Okay, thank you, sir.
Yeah.
Thank you. Sabu sir, you're not visible. You're not audible, sir.
Could you look at the phytochemical components of this plant extract?
No,
What
sir.
are the important
Thank you
phytochemical components?
thank you for your suggestion, but I haven't checked it.
So
In near future, I will apply for project and I will try
that
to
will be
study.
that will be very interesting to show
Yes,
a
I know mechanistic model study is very important.
you gave a very nice talk. Congratulations,
Thank
and
you, sir.
I'm glad that you went for freeze drying. What advantage you get out going for freeze drying? You made
No,
use of,
sir. Actually, P40 leaves are local medicinal plant. You can
yeah, yeah,
store it for so many days or so many years.
very good. That's
By
very good.
freeze drying, you can store it, and we have seen that the preservative value is great for
Thank you.
freeze drying. Thank you, sir.
Perfect. Yeah.
Thank you, sir. Thank you, ma'am, for the talk.
Okay.
Ma'am, I have a doubt.
Okay.
Thank you for your wonderful presentation. What about the quantum yield and stability of these nanoparticles?
No, it is found to be stable more than 1 year. We have kept it in the fridge, and after that we have checked it, the UV, the spectrophotometer, and we get the same result. Arbitrary unit is found to be stable.
And what about the quantum yield?
Quantum field, I don't know actually. I'm from biochemical engineer. For postdoctoral work, I have shifted to nanoparticle study.
Okay, okay. Thank you, ma'am.
Thank you.
Thank you, ma'am. So we'll move on to the next speaker for the session. So we'll have Dr. T. Uma Rajalakshmi for presenting her talk on the synthesis of Kosher TiO2 sodium alginate nanocomposite for efficient photochromatic degradation of eosin blue and methyl violet dye. So I think Dr. Uma Rajalakshmi hasn't actually joined us for the session. We'll go to the next talk, Dr. V. Shivanandan Achari. So his talk will be on John isotherm methods for textural characterization of nano and porous materials. So could you present your slides, sir, on the screen?
Excuse me.
Sir, I think your mic is on mute. Sir, I think your mic is on mute. Yes, sir. You're audible now, sir.
Very good morning to all. Hello. Is the slides are visible to you all, dear?
Yes, sir. It's visible, sir. It's visible now, sir.
Okay. Respected Professor Sabu Thomas, the Chairman and Vice Chancellor of the prestigious MGU University, and the organizers for giving me a rare opportunity to present my research findings for the last 30 years on absorption science and engineering. Today, I like to present you John isotherm methods for the textural characterization of nano and microporous materials, an Indian contribution in analytical science. Experience goes like that. When we are dealing with about absorption characterization of porous materials, we are most convincingly familiar with Langmuir isotherm, Freundlich isotherm, Brunner Emmett Teller, that is a very famous surface area analytical method, BET isotherm, then later by Dubinin-Radushkevich equation for the textural characterization of microporous materials from the USSR, then followed by many other common isotherms. When I was doing my research in Department of Chemistry, University of Kerala in the year 1992, when I got an opportunity to read an article that appeared in Indian Chemical Technology Journal, that is ICT, Indian Chemical Technology Journal by CSIR, I have seen an isotherm that is mentioned as John isotherm. When I looked into that, the author is from National Physical Laboratory, Delhi. I thought of that he may be a foreigner, but identifying that it is a publication from New Delhi, I thought how I can contact that person, whether he is an Indian scientist or a from foreigner working in a national capital. Then accidentally I got a chance to interact with one of the friends of Dr. John, and within 1 week I landed in Delhi and found his home and started discussing with John as a parallel interest. Dr. John is born and brought up in Kerala from the Haripad, that is Chepad near Haripad in Kerala state, and he was a student of Meghada's Saha. And in 1948, he obtained his PhD from the Washington University under the guidance of Professor Brackley. You know, Brackley had been one of the famous scientists whose contribution ultimately led to the invention of Brunner Emmet isotherm, because the capillary condensation, capillarize of water molecules in the soil horizons ultimately lead to the pore filling mechanism of porous materials, and finally the famous invention of the famous BET isothermication. Imagine that the time when the BET isotherm developed, an Indian scientist who born and brought up from Kerala state then started his research work in isotherms, and later he published as a John isotherm method in famous journals like Carbon as well as Journal of Material Science. When I joined him as a student of interest in adsorption science, he was 85 years old. And within the limited time, we published some papers in Journal of Material Science on John isotherm in 2002. Then later discussions have been made later into 2006, and we extended the isotherm characterization to with my name as John Shivanathan Acharya isotherm, and presented in Carbon Conference 2006 in Robert Gordon University, UK. And I will tell you what is meant by an isotherm analysis. Isotherm analysis allows us a more accurate and comprehensive poral structural analysis to be obtained from high resolution. We need absorption data, because any porous material has a capacity to fill their porous structures with the nitrogen gas when it is exposed to liquid nitrogen temperature 77 K with a relative pressure spanning from 0.1 to relative pressure 1.0. Then this analytical, very important textural analytical technique can be applied for the characterization of any type of material, natural material, or synthetic material, or carbonaceous material, nanomaterials. Then it goes according to our requirement. In most of the catalytic people are continuously using BET analytical or isotherm technique for the characterization of porous structure. So tailor-made porous structure can be assessed and can be evaluated by this method. Micro and mesoporous materials and carbon nanotubes, material with a hierarchical porous structure can be analyzed using adsorption isotherm method. Then development of high resolution experimental protocols for the adsorption of various subcritical fluids, generally nitrogen gas at 77 K, due to the geometrical the supremacy of the molecule, and they can be tightly packed in cylindrical or slit shaped structures with a uniform energy for the packing. Then argon gas at 87 degrees centigrade, and most commonly carbon dioxide at 2 K can be used as a probe for the determination of porous structure. Then why this presentation in ICN in any university conference? Some guidance on gas absorption methodology can be highlighted. Then study of solid surfaces, can discuss the advantages and the limitations of absorption techniques. Then merits of using John isotherm methods applied on solid gas liquid systems, and assessment of surface area with John isotherm methods. And now generally we use BET isotherm or DR isotherm techniques for the solid gas adsorption equilibria, but John isotherm, when it is applied for the characterization of porous material, we will get a comprehensive and complete information about the pore filling mechanism of the materials and categorization of solids. Using John isotherm methods, we can categorize the porous material. That is a new thing that is highlighted by Dr. John in his isotherm. Then being this is a conference and a highlight that is intended for material scientists, and our target group is giving me immediate pressure and delight, because more pure and applied research people are gathered in the ICN conference. This is the very important reference literature, how porous materials can be characterized. This is published in 2005 IUPAC, and who are working on the textural characterization catalyst or porous material. This is the primary reference article that in 1985 the review published, and it is revised in 2015 by Matthias Thomas from the very famous UK university, and Kaneko is a renowned absorption scientist from the Japan, and their contribution is very valuable in the study of porous material, especially in carbon research. Absorption gases with a special reference to the evaluation of surface area and the pore size distribution. Most material scientists has to refer and learn this paper very deeply for the interpretation of their findings. Then in this paper, in the technical report, you can see what is meant by surface area, external surface area, what is my internal surface area, roughness factor of solid materials, and how pore morphology can be described. Then porosity is defined as the ratio total pore volume to the volume of the particle or agglomerate. That complete the chemistry and physics of material, porous material is described in this IUPAC technical material. Then classification of pores and pore classification is scientifically given in this technical report. What are the micropores, macropores, mesopores? Ultimately, what are nanopores? Because nanomaterials are there, then even micropores having size less than 0.7 nanometer is very important. They are known as finer pores, wide micropores, super micropores, and the calculation of surface area, everything is described in this technical material. This is a characterization of classification of pores according to the IUPAC technical material. Then whatever the material we synthesize, we use can be categorized into this different 6 categories. That is the beauty of isotope. Then the individual characterization, identification, interpretation will be easy. You take the sample, put into BET isotope, get to the general features of the isotope, you categorize the material to which type, then you analyze the material properties. So the comprehensive study will be completed when you are having a good BET surface area analyzer. So this is the character, what are microporous material, mesoporous material, and the technical report. Then I will come to you very quickly what is meant by, what is the significance of John isotope. Then let us have a look into the contribution by Langmuir. Langmuir, then he explained the concentration of gases or any material on the surfaces and the energetically how it happens, and what is the condition when a unit monolayer is completed by the molecules, how the multi-layers are formed. That scope of energetic favorite conditions for the concentrating any molecules on a surface has been first laid by Langmuir in the year 1904. That is a premier contribution. Later by that is in 1938, Brunner and Emmett and Teller, 3 scientists working in a catalyst laboratory in New York, coming from 3 different countries. One is from USA, then Brunner is from Bulgaria, and they contributed much more for the intricate discovery analysis of the porous structure through his very famous mathematical model, Brunner Emmett Teller equation. That mainly it created based upon Boyle's law, that is when pressure is applied, the volume is reduced. That means the molecules, to resist that, if there is enough space for the molecules to move, the molecule will condense and concentrate in the intricate porous structure. So the amount of any gas get accumulated, any pore volume, can be directly related to the pressure value. So the pressure and the volume relationship, the Y value, that is argument, the value is P by V, that is the related to pressure volume relationship, is related to the relative pressure P by 0. It conforms to a straight line. Whenever a mathematical model is applied to explain basic primary data, if it conforms to a straight line, there will be an intercept, there will be a slope. The intercept and the slope will tell you more about the characteristics of the material. So that is the beauty of applying mathematical models for the textural characterization of any material. Put the data into any mathematical relationship, identify the constant and parameters. The magnitude of the constants and parameters will tell you more regarding the, it will reveal you the secrecy of the material characteristic and properties in wide words. That is the beauty of mathematical models. In that respect, the contribution by Brunner and Emmett is highly appreciated by the modern science. They were the most distinguished scientists of the USA, of the world, for the last 75 years. The famous book, The Absorption of Gases and Vapors, by Brunner in 1930. Brunner is so much associated with Einstein and their interaction. Einstein's letter reads that the position of Brunner is more than the contribution of the Einstein. So even Einstein wrote many letters to Brunner for seeking job. That is a historical evidence. I am telling you what is the significance of surface area and the Brunner-Emmett Teller equation, 1938 paper. That is the masterpiece of the textural characterization of porous material in American Journal of American Chemical Society in 1938. Brunner isotherm and derivation. That is how the surface area can be calculated from Brunner-Emmett equation. Find out the monolayer concentration. That is, I have. This is intercept. This is the slope. From the slope and intercept, we can calculate monolayer capacity. Then applying the Avogadro's number, molecular weight relationship, cross-sectional area, we can calculate how much, what is the total surface area occupied by 1 gram of the material. This is the famous Brunner-Teller equation. Then when we apply BET equation, we apply up to 0.3. There are some examples. We can calculate surface area by monolayer adsorption. When it is applied in the liquid phase, if the phenol is taken for the determination of surface area of any material from the adsorption term, knowing the cross-sectional area of any liquid molecules, we can also calculate the surface area once the cross-sectional area is given. This is an example. When phenol adsorption data can be utilized, if the scientists are not having any high-value BET analyzer, we can do some experiment in the liquid phase, take the monolayer adsorption capacity using here, these are the example how the surface area can be calculated. Then Dubinin-Ashtakov equation modified by later Radickovich for the determination of micropore volume. Then here comes our interest, that is John isotherm. Here log is utilized for the linearization. John identified log of the log. Then we take the pressure P by P by 0, take the log and the log. Take log, then again log, double log can give you a straight line relationship that is related to the V, the volume adsorbed. That is log P is equal to C plus N log V. Then this is that is a semi-empirical isotherm that will give you the almost equal or more significant result compared to the famous established Langmuir isotherm. This is the first paper by Dr. John in 1985. You can see that this is from the Materials Characterization Division, National Physical Laboratory, New Delhi, and later John isotherm can be written as log P is equal to C plus N log V. Then this is another paper published by John. This here we can say the John isotherm can transform into different type of isotherm, established isotherm. John can be converted to Dubinin-Ashtakov equation. John can be converted to BET isotherm, that is Hasley's equation or Harkins-Urras equation. So every time that John isotherm proved its the validity over the years as a sole contribution by Dr. John, then John isotherm can compete with any other established isotherm. That is the famous Dubinin-Radickovich isotherm equation. And John kept continuous contact with Dubinin and Brunner and discussed everything, the supremacy and the validity of his isotherm. Those scientists appreciated John well for contributing such a very outstanding research work from India, from National Physical Laboratory. This is the graph where John isotherm conforms to, under different situation, to Dubinin-Ashtakov equation as well as to Langmuir equation. Then this is when I was doing my research, I have spent a lot of time with John by spending almost 6 months with John's home in Delhi. And occasionally I was so fortunate to have a photograph with him at the age of 85, some papers, and we published in Journal of Material Science. And compared to other isotherms, John isotherm give you complete categorization of the material. In IUPAC classification, any isotherm can classify into 6 categories. Here 9 categories, that according to the shape, the slope of the lines connecting the relative pressure log P and log V, and depending on the shape of the curves and the straight line, and we can categorize to different 9 categories of the materials can be distinguished, and accordingly the properties can be explained. These are some of the examples John applied. Dr. John applied his isotherm for the characterization of materials. Different materials give you different shape, and accordingly we can categorize. This is John isotherm modified for the liquid phase. Log C is equal to C plus N log Q. Log A here is the quantity adsorbed from the liquid phase. So C is the concentration. When the isotherm transferred in the liquid phase, instead of relative pressure, we can use the concentration. You take the equilibrium concentration of the adsorption system and take the double log, plot against the quantity adsorbed log A, you will get a straight line, then the slope. The slope will give you the characteristic of the property, it is known as the adsorbability of the material. Depending upon the value of n, we can say whether the material is highly efficient or not efficient. So m or n is a parameter that determines the adsorption efficiency of the material, adsorbent capacity of the material. So advantages of the John isotherm. One and the same equation is valid for all types of adsorption. In Dubinin equation, Astakov equation, where the value is n, in Radushkov equation for the microporous material, log square divided by p by 0, that the value is 2. So the equation has to modify accordingly depending upon the condition of here. One and the same equation is valid for all types of isotherms. Can be plotted directly from the data. Different phases of adsorption can be identified from the isotherm kink or the sudden change in slope. Isotherm can be located easily. Only comparatively low pressure adsorption is sufficient to evaluate the monolayer capacity for the type 1 isotherms. These are the significant and significance of John isotherm. One of my students completed a PhD thesis under John isotherm. This is Macy Thomas, and here John isotherm as well as the extended form John Shivanandan Acharya isotherm is elaborately accepted, and she awarded PhD degree. Our scientist contribution can be done in the form of PhD thesis. Is a wonderful experience. John isotherm for the characterization of microporous carbons published from my group in 2017. Then this is the John isotherm. This is the modified liquid phase adsorption. John Shivanandan Acharya isotherm equation. The log Q can be calculated. Then this is a example we published, paper published, how the different slopes are obtained. When the slope completed, a kink is formed. The first phase is a type of adsorption, followed by different type of another type of pores are filled progressively. Then wider pores are filled progressively. Then the mesopores are filled. Then different types of pore filling can be characterized depending upon the change in the slope or the kink of the isotherm plot. That is the beauty of John isotherm. The different type of filling is mentioned in this graphical simulation. This is John isotherm, and this is some of the pictures from the landmark of the Dr. P.T. John when he was working in National Physical Laboratory. Then it was a picture with John is interacting with Dr. Brunner when he visited National Physical Laboratory, Delhi. Then that is interacting with the Brunner, and this is how the John isotherm conforms to Langmuir isotherm. This is also our contribution. John isotherm can give more, is following the same informations and the same path the Frunlich isotherm followed. So this is a situation where the John isotherm is experimentally validated for the liquid phase that is presented in International Carbon Conference by myself. John isotherm for the porous material with respect to solid gas equilibria, different conditions and evaluations, and how the characterization is done and interpretation is made is visible from the graph. Here we can see when the John isotherm, in John isotherm, different depending upon the material, different slope values can be obtained. N1, N2, N3, different N1, N2, N3 accordingly. One type of filling followed by another type of filling, another type of till the monolayer adsorption capacity is completed. Then John isotherm values, monolayer values are calculated, and it can be compared with the DR equation as well as Langmuir equation. It's a recent paper published in a journal of Chemical Kinetics. Then we applied this isotherm for the nanomaterial incorporated carbon materials, have huge potential in catalysis as well as in adsorption science. The behavior of nanomaterial when it is embedded in carbon material, how it is behaving in when it is acting as a valuable, efficient adsorbent material. This kind of technical characterization is possible using John isotherm. This is one of the recent paper published by our group regarding John isotherm. Then this is the modified John Shivanandan Acharya isotherm equation. Log C is equal to C plus N log Q in Journal of Chemical Kinetics. Then how it is applied and the graphs are plotted. That is John Shivanandan Acharya adsorption isotherm plots of phenol. When phenol is applied, you see in the first case the material behave in a way. The second, the material behavior is different. The third material, three different kinks are obtained. The slopes are different. So the adsorption phenomena is different for the third material. This kind of validation is possible using isotopes. This is one of the recent paper in Journal of Chemical Environmental Chemical Engineering, when the John isotope is applied for carbon aerogel materials. That technically we were able to characterize the material using our new isotope equation, no problem. It will give comparable value with more interpretation for the material characterization. Is a recent paper in 2021 in separation purification technology, microporous carbon with a highly dispersed nano-lanthanum oxide for enhanced adsorption of methylene blue. Here again the material is characterized using our modified equation, log C is equal to C plus N log Q. The material behavior is different for the with respect to the tuning or the tailor making of the material, and the changes in the structural and textural properties is visible, and it is well interpreted. Here we never used any other equation for the interpretation of material. Our own equation, our team working on our own material, our equation is used for the interpretation of the data we are publishing. So we are solely independent.
Excuse me, sir.
We are not.
Sorry to interrupt you. Please conclude the session.
Yeah, it is in the end. This is the last part.
Okay, fine.
Thank you. Thank you for your very patient listening and allow me to present my result within the stipulated time. Thank you all. Thank you very much.
Thank you, sir. So I think we have two questions from Dr. Indra Rajendran.
How about the fit with experimental data? The fit, you got a very nice fit because you made a comparison with Langmuir. How about experimental data fitting?
So we will apply, then we identify the set of data where the deviation is happening. Accordingly, we will take the data just before the kink and apply the regression analysis. Then the second set of data that conforms to a straight line, we take that data and do the regression analysis for that set.
And the fitting was good with experimental data, right? The fitting was good, right?
Yeah, very well. Then we will analyze accordingly, separately. Yeah. Wherever the change in the slope identified, set the data as a separate group, do the analysis and fit that line.
Oh, right. And using this model, can we also investigate the mechanistic pathway for the diffusion process? Can you also look at the mechanistic pathway?
Yes, yeah. Because the adsorption coefficient, that is N, that is the slope value, can speak a lot of things. Dr. John taught me everything regarding that. Because it is related to, it has some energy, is related to energy, the absorption capacity, and a lot of material property can be speak out by the slope value.
It's great.
Everything is published.
Professor Ajari, you had a direct personal meeting with Professor John, right?
Yeah, I have been with him for 6 months in Delhi. Every day in the morning, I will go to him and sit with him. At that time, he was 85, I was 23 years old. And he was looking for a disciple to transfer the entire information to the coming generation, because he was working in National Physical Laboratory and there was no research scholars at that time. And in that respect, I was very, very lucky to have a close interaction with the giant who contributed in the absorption science.
How old is he now?
Sir, when I met, he was 85. In 2005, November 2nd, he left this world at the age of 9.
Right. Okay,
I have a rapport and a relationship with their family members. Whatever happened in my life, regarding the John isotope, I continuously communicate with them. I always keep an emotional relationship with that family.
Great work you have done. Thank you.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you all.
Hello, sir.
Hello.
I have a doubt. Does John isotope model gives information about functional mechanism of adsorption?
That means you are telling about the surface functional groups?
Yes.
So that it will give you some information. It will give you, because the different layer of different stages of adsorption can be, if there is a functional group, suppose a functional OH group is there on the carbon surface, carboxylic acid group is there, then ionization occurs. Accordingly, a particular layer of adsorption is due to the ionic mechanism or ion exchange. Accordingly, we can distinguish the pore filling mechanism or adsorption mechanism.
Okay, sir. Thank you.
Kindly go through my publications, and each publication describe different type of behavior of the materials.
Okay, sir.
And promote this isotope, because he sacrificed his entire life for a very rare contribution. Any more questions, please?
No, go ahead.
Okay, thank you, sir.
Thank you, dear chair, for chairing my session, Dr. Arjun Mohan and Lakshmi V. Nair.
Thank you, sir. Thank you so much.
Thank you. Thank you. Thank you, sir.
So thank you, speakers, for the wonderful presentations. And now we are going to the next session. So before that, thank you, Dr. Arjun Ajit Mohan, for chairing this session.
Thank you so much, sir.
Clap to Arjun.
Now
Thank
we
you,
are
sir.
moving on the next session. Now we are moving on the next session, theory, modeling, and simulation. I invite Dr. Sudipta Basu as the chairperson.
Good morning, everyone. Hello, sir. Good morning. Good morning, everyone. So now this is the second session of this morning, and this is about theory, modeling, and simulation. Our first speaker is Dr. Bindu Krishnan from Department of Physics, Sri Kerala Varma College, Thrissur, Kerala, and she will be talking about simulation studies on tuning of plasmonic resonance in core shell structures. Dr. Bindu, please share your slide. Yeah. And welcome.
I hope my presentation is visible.
Yeah, it is coming. Yeah.
So today I'll be talking about simulation studies that we have conducted on plasmonic resonance in core shell nanostructures.
Dr. Bindu, sorry to interrupt. I think there is some echo is happening.
Yeah, okay, sir. Let me check how.
And also, please make it in a slideshow mode.
Yeah. Okay.
You may like to use a headphone if you have.
Yeah. Okay. As you all know, surface plasmons are coherent excitations of conduction electrons in the near surface of metallic structures.
Excuse me, madam.
Yeah.
Madam, can you please put in slideshow mode?
Yeah.
And I think still some echo is happening. I do not know why.
It's not from my side, so I have switched off the phone. I don't know.
Okay, I'll request everybody in this meeting to switch out their microphone. Yeah, please go ahead, Dr. Bindu, and please put it in the slideshow mode. It is still not showing.
I have put it in the slideshow mode.
But we don't see a slideshow mode.
Madam, I think you shared this only one slide. Can you please share the entire screen?
Is it visible now, sir?
No, actually, you can. It's first you please stop sharing, then share the entire screen option. Now please share the entire screen option.
Yeah. Okay. Is it visible, sir?
No.
Not yet.
Yeah, can I go ahead, sir? Even if it's not full screen. It's visible, right?
Okay. Now your screen is visible.
Yeah. Okay, can I go ahead, sir? Yeah, so I'm working in
Okay, fine.
aluminum and copper plasmonic mainly because much work has been done in gold and silver. So we thought we'll do some more work in aluminum and also on silver-based core shell structures. So while the surface plasmon of a particular metal is confined to a particular wavelength, we can tune the plasmon wavelength over a wide range if by coating it with a dielectric material and then by changing the core diameter and the shell thickness, we can really fine tune the resonance wavelength. That's the interest of this study. So we have used COMSOL multiphysics software, commercial software which use finite element method, and also we have used me-calculated software from a website, Nanocolloids. Both uses in both of these we use the basic theory that is used is me-scattering theory, and we know that light will be absorbed and scattered, and the sum of both these will give rise to we can denote it as extinction. So all these extinction, scattering cross-section, extinction cross-section and absorption cross-section can be plotted together in each case. That's what we have done. So this is, for example, this is the first one is silver silica coating, 50 nanometer diameter, 50 nanometer silver, 10 nanometer silica coating. And here you can see that that three curves is the yellow one is total extinction coefficient, the blue one is absorption, and the red one is scattering. So the scattering and the absorption will give the total extinction coefficient. And you see that as expected, silver, when it is silver is coated with silica and when silver is coated with TiO2, there is slight change in the peak wavelength. To demonstrate that, I have shown this. Now we have, I will describe briefly what is done in COMSOL simulation. We define a geometry. For example, in this case, it's a sphere with a coating. And then we can input the input material properties. There's a huge library of materials in COMSOL from where we can choose silicon dioxide, titanium dioxide, silver, gold, anything you can choose. And along with that, we will get the relative permittivity, permeability, conductivity, everything. And then we can choose appropriate boundary conditions. And then we define something called meshing. You can see that there is a fine meshing that is there. Meshing means in finite element method, we are solving the equations in a small mesh and then we total the whole thing. So the more finer mesh we use, the more accurate the simulation will be. And then we have used frequency sweep method so that the incident light will be over a frequency range. And then when we plot, we will see at what wavelength the scattering is maximum, the absorption is maximum. These are the, this shows that we get, whether we use COMSOL multiphysics on the right hand side and the me calculator on the left hand side, we are getting more or less the same results. And with aluminium, now I'm going to concentrate on aluminium. For aluminium, people say that aluminium is not a very suitable material for plasmonics, mainly because people say that aluminium, as you know, when come into contact with air, an oxide layer is formed. That is supposed to be the disadvantage. But it has been experimentally proved that when aluminium is formed, a thin layer, oxide layer is immediately formed, but it has been studied with the sole purpose of the growth of this layer, and it is shown that within a short time it reaches maximum 5 nanometer, and after that the thickness remains the same. So essentially, whenever we are talking about aluminium, we are dealing with aluminium with a 5 nanometer thickness shell of aluminium oxide. After that, it doesn't change. While in the case of silver, it is always, gold is very passive. But in the silver, we are always dealing with the threat of further interacting and deteriorating over the time with interaction with the atmosphere. While in aluminium, in the beginning itself, an aluminium oxide shell is formed, which is a constant thickness shell. Then after that, it won't change. So what I suggest is aluminium need not be discarded because of this. But suppose we are taking a 50 nanometer aluminium sphere, then we immediately, if we apply aluminium oxide shell of 5 nanometer, and then what we get with that, the wavelength, the scattering cross-section, that will remain the same over a long period. So the same disadvantage that has been often quoted for aluminium plasmonics can be changed into an advantage if we consider into account this oxide shell also. So we have that is the case if we need to study more on single aluminium nanoparticles. This can be applied. But we have also tried applying what happens when TiO2 layer is coated in aluminium, because it has a lot of photocatalytic properties. So the dielectric we have chosen to be TiO2. So this is the case of aluminium TiO2 5010 nanometer the scattering cross section, and we see that without coating, aluminium often has a resonant wavelength in the UV region, but with TiO2 coating, we are able to shift that into the same 400-600 region in which the silver peak comes. So essentially, we are getting the same wavelength which we get with aluminium, but with a very much more economic material, aluminium. It's not a very costly noble material. Now we have studied in detail how we can tune the wavelength by varying two parameters. That is, either for a fixed shell thickness, what happens when the core radius is varied, and the next study when the core radius is fixed and when the shell thickness is varied, what is happening. So in the figures, we can see that the 25, 40, 50 is the core radius, and we have kept the shell thickness 10 nanometer fixed. So we can see that the shape and there are two peaks. Actually, these two peaks come from dipole and quadrupole contributions. These two peaks, in these two peaks, in the 25 nano region, the UV peak predominates, and the next peak which comes to the visible region is the intensity is low. And when it reaches 40, it is almost equal. And when the core radius reaches 50, the peak wavelength in the visible region is becoming more prominent. So we can really see the wonderful way we can tune the wavelength and which peak dominates by varying the core radius, keeping the shell thickness constant. Now next here, we varied the shell thickness by keeping the core radius fixed. And then also we can see that the wavelength really changes a lot. Here, for some other further studied, we have taken the parameter, not just the radius, but PRA, that is shell volume by total volume. core plus shell volume, the sphere, the total volume which includes the core and shell, and the ratio of the shell volume by total volume, and variation with that we have taken, keeping in mind that further theoretical studies we plan to do. Then we need this parameter. And these are the polar plots which COMSOL gives in all scattering studies. Polar plots means how the scattered light, it shows the direction. It shows 0 to 360 degree in which direction the light is scattered. So the 2D plots of the far field pattern of a metal sphere. So actually for nanoparticles, it looks like a dipole antenna in the usual case, which in the left-hand side. But when a dielectric shell is given, in some cases, we see that the polar plot is radically modified. What this plot means that forward scattering is predominant and backward scattering is really suppressed. This has a lot of applications, especially in solar cells. This thickness is not only able to fine-tune the wavelength, but more than that, it gives us a chance, a tool to control the direction of scattering in a preferential direction. And why that is happening? So, see here, the backward scattering is totally suppressed. And in the case of the 50-10 nanometer curve, this was the curve that we saw. And here there is another phenomenon that is actually happening, phaneresonance. Phaneresonance was discovered in 1961. It's a quantum mechanical phenomena discovered by scientist Fano. He discovered it in the auto-ionizing systems. But over the past few years, a lot of people have been interested in the phaneresonance that is happening in optics in a number of plasmonic nanostructures. And phaneresonance essentially happens due to the constructive and destructive interference between different light modes. So, and when that happens, in the light, if there is a continuous something which gives a continuous spectrum and something which gives a discrete spectrum with a particular frequency, and when these combine together, we get this Fano shape. So that is the schematic shows how phaneresonance occur and the shape, and see what the shape we got, the 40 nanometer, 10 nanometer case of silver TiO2. The scattering, what we got is almost exactly the same of the Q parameter varies a bit, but it is definitely, we find the signature of phaneresonance. So what is actually happening here? It is constructive and destructive thing happens, and so immediately below this wavelength of the maximum wavelength, backward scattering is suppressed, and that is due to the destructive interference. So here, whereas in this particular case, Kosher structure, which gives the continuous range of continuum and which gives the discrete state. Obviously, the discrete states comes from the plasmon resonance of the metal, which is more or less at a particular frequency, and the continuum comes from the spectrum of light scattered by the dielectric shell, which doesn't have a particular resonance frequency at a particular region, but it gives a rather broad spectrum. We have plotted that also. In the case of aluminum and TiO2, we have plotted aluminum alone, the plot of scattering, and what happens if there is only a shell of TiO2, then we get, instead of a peak, we get a flat thing. So that is what is happening here, phaneresonance. In the general applications of plasmonic Kosher structures, there are different applications. One is, as we all know, that there is strong localization of light around any plasmonic structure, and that gives the signal amplification, which can find application in Raman fluorescence, nonlinear signals, spectroscopy sensitivity, etc. Especially in a particular case of Raman spectroscopy, there is something called shell-isolated nanoparticle enhanced Raman spectroscopy, shiners. In that case, the plasmonic Kosher structures find a lot of applications. And of course, when we use TiO2, it can find application in photocatalysis. But then we are more interested in the application of photovoltaics, because we do simulation in this part, but we would like to associate with somebody who's actually fabricating such structures. And then if we can collaborate and publish a paper, it's always good with experimental results backed up with simulation, and theoretical explanation is always the kind of best paper. So we don't have that much facility in our college. I'm coming from a small college in Kerala. So we can do all this.
Dr. Bindu, sorry to interrupt. Can you please wrap it up within 2 minutes?
Yeah, of course. I
Sure.
just say that this can find a lot of application in solar cells, whether the plasmonic structure can be introduced on the top surface of the solar cell, in the active layer, also in the back rare aluminum back side. So in all these cases, this can increase light trapping and efficiency. So if somebody is working in this area, it will be nice to collaborate with them. And thank all my PhD student Ashwati Vijayan for the work, and I thank the organizers of ICN 2022. They have been inviting me in all years. I thank you a lot, Sabu Thomas sir. Thank you.
Thank you very much, Dr. Krishnan. And now the floor is open for questions.
I have a question. Could you, using your modeling approach, could you optimize the core size, the core size and shell size? Could you optimize?
Yeah, that depends on what you want.
Yeah.
If we want a UV, see, for certain applications, we want the peak to be in the UV region in bio applications. Then we can get it there. If in another application, if we want the peak wavelength in another region, we can tune it. That is it. Depending on the application, we can fine tune.
Yes, and do you have good agreement with experimental?
No, that we don't have. That's what I'm looking for. We can do optimize, and then if somebody can test that, or in the other way, if somebody is working in this area in the experimental range, if they can tell me what wavelength they want, then I can find which core dia or shell thickness which give you that.
Right.
So I really want collaboration with people who work experimentally, either in solar cell or in sensor applications.
We have done some Kosher synthesis in our laboratory. And my collaborator is from South Africa.
Yeah.
Maybe we can have some discussion.
Yeah.
Because we have synthesized many Kosher structures.
Yeah.
And the plasmonic resonance.
Yeah.
And fitting some of our results with your theory could be interesting.
Yeah, definitely, sir. That will be really nice, because I don't have the experimental setup and full-fledged lab, but I can optimize it using.
Yeah, thank you, Dr. Bindu. Good.
Any more questions?
Hello, madam.
Yeah.
First of all, thank you for the wonderful presentation, ma'am. So, madam, actually, I need a suggestion for actually. I am also interested in modeling, simulation, etc.
Yeah.
So in your presentation, you mentioned about the CAD software for geometry definition, right?
Yeah.
So, madam, I also started to learn CAD software, but whenever I searching, I'm see CAD software for civil engineering applications, etc. So for material science application like this, how can I start?
No, you need not do all that stuff. In the console, there is already many of the geometries are there, and it is very easy to change the geometry in console. If you have console, you need not go into detail about CAD and study. No. We can really, there you can just pick a sphere, just give a coating. In the COMSOL itself, there is a facility of all that. COMSOL is a conglomeration of engineering, science, different fields, optics, heat modules. We can combine all these things together.
Okay, madam. So COSMOL is also a computer-aided software?
Yeah, COMSOL is a very costly thing. That is a problem. COMSOL is a very costly software. So buying it, if you want to buy it with a license, it's a bit costly. And but different modules cost different also. If you are interested in a particular thing, you can buy only one module of COMSOL, which comes under 1.5 lakhs and all. And but once you have COMSOL, it's very easy to do all the things because it has a lot of inbuilt things in that. Okay.
Okay, madam. So instead of COSMOL, can I use some free softwares like AutoCAD or something?
I don't know about that.
Oh, okay, madam. Thank you. So, and madam, you also mentioned about the polar plots.
Yeah.
So
that
is that so applicable in the solar cells, etc.?
Yeah.
So I'm working on solar cells. So how it is?
Solar cells if we are putting the plasmonic things in the top level, we want the light to be forward scattered because we want to limit the scattering back into air, but more light into the active layer. If we put it in the downside, we want the other way around. So depending on where we put the plasmonic thing, we want a different directional changes that we can do with this.
Okay, madam. Thank you so much, ma'am.
Thank you very much. So is there any further question? If not, then I would really like to thank Dr. Bindu Krishnan for her excellent presentation. Thank you, Dr. Krishnan. So our next speaker is Dr. J. Meena Devi from Department of Physics, School of Electrical and Electronics Engineering, Shastra Deemed University in Tamil Nadu. And the title of this talk is Effect of Shape on the Properties of Gold Nanoparticles. Dr. Meena Devi, please share your slide.
Okay, sir. Thank you, sir. I'll open my presentation, sir.
Yeah.
Is this visible, sir?
Not yet.
I think it's coming out.
Yeah, it is.
So now I have opened the title slide. Is that visible to all of you?
Yes.
Okay.
Please go ahead.
Okay. Very good morning to one and all. I thank the organizer and Sabu Thomas sir for giving me an opportunity to present my talk in ICN 2022. So today I'm going to talk about the effect of shape on different properties of golden nanoparticles such as structural, thermal, hydration. In this simulation study, I have used molecular dynamics simulation technique to study the property of gold nanoparticle of different shapes. So experimentally, this is a theoretical simulation study. Experimentally, many different shapes have been prepared such as sphere, cube, rod, cage, star, plate, ribbon, belt, shell, wire. So and these shapes have been reported to render fine-tunable physical, chemical, and novel property. So when we move to anisotropic shape, they have a larger surface area, they have lot of corners, edges, and because of this, mobility of the charge carrier is changed, and you have it has many surface-based application, anisotropic shapes. They have enhanced optical property, electronic property, as well as chemical reactivity. Mainly when we change the shape and size, this gives rise to enhanced optical property and chemical reactivity of gold nanoparticle. So these are the details of the systems I have simulated. So in the present study, I have considered 4 different shapes: sphere, cube, pyramid, rod. Sphere is isotropic shape, and other remaining 3, cube, pyramid, rod, they are anisotropic shape. So I have generated these shapes from the bulk metallic gold. So the similarity between all the 4 systems is generally I have taken it around 250. All the 4 nanoparticle has around 250 atoms. Sphere has 249 atoms. Cube 256 gold atom. Pyramid 249 and rod 252. So these are the 4 shapes I have taken and the number of gold atoms in it. So next, this is the condition in which I have simulated. I have used molecular dynamic simulation technique for studying the properties of gold nanoparticles of different shapes. So I have put each shape gold nanoparticle inside a water box. The water model I have used is a tip 3P water model. I have simulated them in NPT ensemble. So the temperature I have taken is room temperature, pressure is atmospheric pressure. I have applied periodic boundary condition. The total simulated time is 20 nanosecond with the time step of 2 femtosecond. So this is the final configuration I have got after simulating them for a period of 20 nanosecond. All the 4 shapes have attained a stable configuration. As you can see, this is a spherical shape. This is a roughly spherical shape. I have carved out from this a bulk gold metal. Next, you can see cube, pyramid, rod. All the 4 of them have formed a stable configuration. Then next, after forming the stable configuration, I have characterized their length. So I have found their characteristic length to find their surface area, volume, and to calculate the surface to volume ratio. I have calculated the radius of the sphere, side of the cube, and the base and height of a pyramid, and the length, breadth, width of the rod. So these parameters I have used to calculate the surface area and volume. So next, from the calculation of the characteristic length, I have calculated the surface area, volume, surface area to volume ratio. As generally we know, the isotropic sphere is thermodynamically more stable as it has less surface area and a larger volume. Here also you can see the surface area of sphere is less and its volume is higher, and the rod has the higher surface area. And among the 4 simulated shapes, pyramid has the largest surface to volume ratio. Next, I have calculated the total energy of the 4 nanoparticle, and I have plotted it as a function of the time. As you can see, throughout the
Dr. Meena, we can't hear you.
Hello?
Sorry, we lost your voice for last couple of seconds, maybe. Last half a minute or maybe. Yeah, please go ahead.
Okay, now I'm in 8th slide.
Yeah, slide is visible, 8th slide, but there is some disruption in your voice. We can't hear you.
Okay, I will tighten
now it is fine. Now it is fine.
Shall I repeat it, sir? Shall I move on to the 7th slide? Now I'm in 8th slide.
No, I think please go ahead.
Okay. So I have calculated the total energy as a function of time and plotted it to see the variation in the stability. So as we can see, sphere is more stable, then cube, then pyramid, then rod. Next, I have calculated the cohesive energy, formation energy, surface energy. Cohesive energy is taken from the average of total energy. Next, I have calculated formation energy and surface energy. So formation energy can be calculated from the total energy of the nanoparticle minus number of atoms in a gold nanoparticle into cohesive energy of a bulk gold. So this gives the formation energy.
Sorry, we lost your voice again. Hello?
Here in this order, you can see the stability. The formation energy also forms the same strength. So surface energy, I have calculated the radius of gyration to see the compactness of the system. So this plot is done between radius of gyration and time. As we can see, the sphere is more compact, then cube, then pyramid, then rod. So the order of compactness is from sphere is most compact, then next cube, then pyramid, then rod. So then what I have done, I have to characterize so I have correlated the energy and compactness. So I have plotted a graph between cohesive energy and radius of gyration. So the stability of gold nanoparticle has enhanced with the degree of compactness. Am I audible, sir?
Yes, please go ahead.
Okay. So then next I have done the structural characterization to see the crystalline nature of the simulated gold nanoparticle of different shapes. I have calculated the radial distribution function between gold atom. So this uniform symmetric pattern reveals the FCC structure, and you can see a peak at around 4.8080. This shows the lattice constant of the golden nanoparticle of different shapes. This matches with the experimental result. Then I have calculated the integral of RDF, which gives the coordination number of the golden nanoparticle. As you can see, the result is very clear in the region between 8 to 10. So sphere, which is a more compact structure, has more number of coordination atoms. Then next, cube is the next compact structure. It has more number of coordination atom. Then pyramid, so it has more number of coordination atom than cube. Then finally rod, it is a less compact and elongated structure. It has a less number of coordinated atoms, less number of coordination number. So this result we have beautifully arrived in the region between 8 to 10. So that so once we increase the degree of compactness, the number of coordination number has also increased. Next, I have calculated the specific heat capacity from the energy fluctuation. I have calculated for all the 4 systems. So, so there is no much difference in the specific heat capacity of 4 different shapes. I have compared it with the bulk gold value from experimental. So that value is little higher. So this may be because this is bulk, and this is what I have done is for gold nanoparticles, and because the surface area is larger, there may be some difference. So what I conclude in the specific heat capacity result is, in the shapes I have taken, for the size I have taken, the shape doesn't have much influence on the specific heat capacity value. Next property I have studied is the hydration property. So to examine the hydration property of gold nanoparticle of 4 different shapes, I have calculated the total interaction of energy between gold nanoparticle and water. As you can see, so the more negative energy is formed for rod, and the less negative energy is formed for sphere. So the rod has mucher interaction with water, and sphere has lesser interaction with water, because rod has a larger surface area and sphere has a lesser surface area. Then to characterize the hydration cell, I have plotted the radial distribution function between nanoparticle and water oxygen molecule. So the well-defined peak shows the hydration cell, and the first hydration cell is around 4 angstrom. And here also you can see this peak with this maximum for rod. This shows the number of water molecules in the hydration cell is higher for rod, and the amplitude of the peak is less for sphere. This shows the number of water molecule within the hydration cell of the sphere is less. This we can clearly know from the plot between number of water molecule in the first hydration cell. So this graph explains the number of water molecule formed within the first hydration cell for each different shapes. As you can see clearly, the rod has the among the 4 simulated shape, rod has the maximum number of water molecule in the first hydration cell, and the sphere has the relatively less number of water molecules in the hydration cell. To further characterize this hydration property, I have calculated SASA. SASA is nothing but solvent accessible surface area. So this measurement will give the how much amount of surface area of nanoparticle will be available to the water molecule. Here also clearly you can see this sphere has a less accessible area, and rod has the higher surface accessible area. So throughout we get the consistent result. That is, the elongated surface, elongated structure could accommodate more number of water molecule, and the compact structure could accommodate only less number of water molecule. So so now I have done a plot to correlate the degree of hydration with the degree of compactness. So I have plotted graph between SASA and radius of gyration. So this clearly shows the degree of hydration decreases with degree of compactness. For more elongated structure, you have the hydration wettability property of the gold nanoparticle has enhanced. So this is in the order. So rod has more wettability, then pyramid has more wettability, then cube, then finally sphere. So in biological application, the wettability is very important. So because in we have in all living system more than 70% is water. The water interaction with the nanoparticle is important. So by taking different shapes, we can tune the interaction between the gold nanoparticle and the aqueous environment. So finally, I am concluding. I have got 3 results. The stability of the gold nanoparticle has increased with the degree of compactness, and the degree of hydration is higher for elongated structure. So for our simulated shapes, and the size, the shape doesn't have much influence of specific heat capacity. So this is the ongoing work. Still, I'm extending it. I thank you for your attention.
Thank you very much for your presentation. The floor is open for questions.
See, nanoparticle shape has a very strong effect on the toxicity. Could you do any study in that direction?
Toxicity, sir.
Toxicity effect. There's a shape, the size has a very strong effect on toxicity.
Toxicity, okay.
Yeah. Could you do any theoretical work in the direction?
So I'm doing, for theoretical technique, I'm mainly using molecular dynamics simulation technique. I do not know how toxicity can be calculated using simulation technique.
Yeah,
maybe experimental.
Yeah, the size is a very important factor.
Only inspired by experimental papers, I did this work, sir. So I saw so many
papers. Yeah, a lot of experimental papers on this. Thank you. Thank you. Yes.
Okay, sir.
Yes, our Japanese colleague. Yes.
Sorry, Dr. Mashiro, please go ahead.
Yeah, okay. Well, you have this, say that the shape and also the number of the atom, of the gold atom. This is a 250 around.
Yes,
that
sir.
case, yeah. This case is not crystallized. This is still in a cluster because minimum gold atom, gold nanoparticle crystal. Okay, it's needed more than 2 or 3 nanometer in diameter. In your case is either half. So in this case, it's not crystallizing. This case.
But
there are many papers in gold nanoparticle and melting temperature. Okay.
Okay, sir.
So this case of the half of the 2.2 nanometer. Okay.
Okay.
0.2 nanometer around this case is the 250 cluster. That is the case. It's not crystallizing.
Okay.
It's lower than melting temperature is lower than the room temperature.
Okay.
And the surface contribution, you said is 30%. Okay.
Okay.
30-40%. This case is the crystallization temperature is below to the several few hundred something. So that is the model itself is okay, but to compare of the data, published data, okay, this is a cluster in some solution or in vacuum or in surface is attached. It's not only in hydration. So that your model itself is, I agree, and then they appreciate it very much. But you should compare of the experimental data already published in even the surface energy contribution is that one. It just looks like for me it's a little bit different. Yeah.
Surface energy. Okay. I will compare it with the literature, sir. But from the simulated system, we could see the spacing remains the same. From that only, I'm concluding it's crystalline. I'll compare with more experimental literature, sir. The surface energy, I saw joules per meter square they have given. I'll check. I'll put the I'll do the comparison with the experimental literature also, sir.
Okay. So that case of the 200, around here, 200 of the 200 atoms. Okay. This case is the radius, not only the shape. In the radius, surface energy is very, very large. Okay, 30%. This case of the crystalline is very difficult to crystallizing, even the cloth packing. So that in the your model in the cube, pyramid is okay, and then the cube and also something the spherical is a 111 and 100 and so something. Okay, not real cube, but some sublattices, surfaces.
Yes,
cluster. Okay, so that case you can put it in the surface cluster surface energies, not total surface energies, because this was calculated in the big size crystal. Okay.
Okay. Okay.
So your case is a cluster, so that the area is not the size of the crystal.
Okay.
That is my point. This is looks like the still in our
Ultra small nanoparticle, maybe very cluster.
Very small nanoparticle. This is the less than 2 nanometer. Okay.
Okay.
Your
Yes.
size. You less than 2 nanometer. 2 nanometers case is a gold melting temperature is below room temperature around.
Okay.
Okay. That is my comment. Okay.
Okay, sir. Okay, I will check the surface energy calculation again, sir.
Okay. Yeah.
I'll compare it with the literature, sir. So I have done it for room temperature, sir. This.
And then let me know your publication. Okay, if you possible. I hope you know my mail address. Okay.
Okay.
Okay. Thank you.
Thank you, sir.
So is there any further questions on this? If not, then I would sincerely thank Dr. Meena Joshi for her outstanding presentation. And so I would now request Dr. Manojit De to chair the rest of the session.
Yes, sir. Thank you. No issue. Okay. The next speaker is Anant D. Kulkarni. And Dr. Anant is from the Department of Polymer Sciences. It's in Mumbai. The title of the talk will be Exploring the Polymer and Nanocomposite Materials, Quantum Chemical and Density Functional Theory Perspectives. Dr. Anant is there?
Yes, can you hear me?
Okay. Yeah. Sure.
Thank you so much. First of all, I would like to thank Professor Sabu Thomas, sir. It started with a basic introductory discussions during one symposium which happened in May at our university, and then through wrangling discussions, series of discussions, we decided, and I'm fortunate he has and thankful to him for giving me opportunity to present the work. Basically, I'm a computational chemist or I do computational simulations, and my particular talk is focused on a domain of this where we are trying to develop the understanding from quantum chemical to get into multi-scale simulations. So this talk will focus on that. So as it's been mentioned, I'll be discussing about polymers and nanocomposites using quantum chemical and density functional theory perspectives. This is for my other friends who are from experiments, and they keep on telling me, experiments are the only means of our knowledge. This is a great gentleman, Max Planck, said like that. And whatever I do is, or the simulation people do, is poetry or imagination. So this talk is just attempt to tell them something about the powerful technique that is called simulation. And as we know, these are some stalwarts from chemistry who got Nobel Prizes in computational and theoretical chemistry, and many of them are even from physics. Okay, so it's like long back, I mean, scientists have realized that experiments and the theory, they are the only two pillars of science where you go ahead and do everything. But over last 60 years or so, we have recognized the third mode, that is simulations. But simulation, to be very precise or to be very honest, it's a broad term. What do we do with simulations in chemistry? Okay, let me focus on that with respect to time scale and the length scale. Engineers work with this macro scale, and even the polymers, all we have, or the things we can see here, but many interesting things lie at the nanoscale. Mesoscale, we can, for time being, we can keep it aside. So the simulations which I'm going to talk about will cover nano and the atomistic, essentially atomistic domain, where I use ab initio quantum chemicals, semi-empirical, and MD simulations to talk about this. So my focus is using these techniques to predict the things over here. So if I do all this spectrum all the way, let's say up to micrometer range, that also covers our nanoscale regime, it will be called multi-scale simulation. And at Somaya, I'm happy to tell you that we are in a process to develop a lab which can cover multi-scale simulation all the way up to this, that is all the way up to, let's say, micrometer range. So let me start with that. Okay, in computational chemistry, as my earlier friend, she told, we are having two different domains. One is related to molecular dynamics and molecular mechanics. But all these techniques which deal with structure and dynamical properties, they have to rely on very accurate experimental and the quantum chemical data. And I belong to the domain where I use quantum chemical techniques to develop this data, the parameters, and use the best, smallest model like oligomers and to the nanoscale. Because as we all know, quantum mechanics you can use only for the small systems. How do you go for the nanomaterials? That is a bottleneck problem. I'm going to talk about that, how you can use quantum chemical techniques to do the nanometer or nanoscale systems. So let's start with that. All these methods, they come with some price tag and the computational complexity. So the methods on left side, they're inexpensive. Of course, MD simulations, Monte Carlo, they are expensive. But as you go on and start looking at more accurate method like electron correlation method, they're very, very expensive. And you need essentially simple supercomputers to work with this, or the parallel clusters. But I'm going to talk something which is going to make it more interesting. Okay, so if I look into the applicability of computational chemistry, we have so many things we can work out if we are doing it correctly. So the things which I'm talking, they're typically related to quantum chemistry. So this is a list which is not an exhaustive. So we can look at the structure, spectra, electronic properties, thermodynamics, and so many interesting things. So if I'm looking at, let's say, a multi-scale simulation, I can even simulate the mechanical properties as well. We are heading to that actually at Somaya. So the importance of these simulations is we want to understand what is happening at atomic level. Can we simulate the complicated scenario? Can we minimize the complexities which are observed in the experiments? And can we complement the experimental findings? And if I'm doing it correctly, we can guide the experiments, okay? Or even challenge if we do with the proper confidence limit. So that is where we are, okay? So one of the region which, or domain which we are trying to discuss is nanocomposite polymers. So it is just the popularity of polymer nanocomposites, which I Googled it in the morning. It returns with more than 2 crore hits, which is not surprising. And in particular, we are looking at this biopolymer nanocomposites and polymer nanocomposites for aerospace applications and solar cell applications. Let me do some advertisement also. We'd like to add many more things here. So if anyone is interested in doing quantum chemical simulations of nanocomposites, collaborations are welcome. I'll be happy to discuss with you. Okay, so let's start. My prime objective is to first simulate structures and energetics. Now, when I look at nanomaterials or polymers, we can expect many more conformations. So how do we going to discuss these conformations? What is the chain length, or what is the size to property relationship as I go on building from a smallest, let's say monomer or a simple molecule to the nanocluster? And if I'm doing it correctly, can I predict with very good confidence the spectra like UV visible, IR, NMR, and then the properties which are essentially interested for electronics like band gap energy, molecular polarizability, and many more interesting things. Well, this forms a small objective from big plant project, which I was telling you, multi-scale simulations. So the first one we started is like a toy project. This was synthesized by my friend from Rajasthan, Udaipur University. He was working with formaldehyde aniline polymer, and which is doped with silver. And then we had a discussion, can we go ahead and simulate these, simulate the structures as well as predict the shape of these materials. So we started with very basic idea. We started with the monomer, but monomer is not a good representation, but we should be able to do it correctly as we go on increasing more and more number of molecules. The technique which I used is a density functional theory to start with small molecule. Essentially, I'm using Minnesota density functional from the group where I belong, Minnesota density functional with Professor Truller. I was working in that group, and we have realized that it works very well for main group chemistry. and that is with some elaborative basis set, dev to TCVP. Those who are from computational background, they can, or I'll be happy to discuss the complexity. So the method along with the basis set and computational simulation language we call model chemistry. So let me tell you this also, that selection of proper model chemistry is very important, and how you model it, because when I start modeling from the atomistic or the smaller fragment level, I should take care of having the proper chemical reactivity. I should not break the molecule the way randomly. There is some proper way. So we take that care and start building up the model one by one, like we may go on building a wall. Okay, so we go ahead and went on developing smaller models. It was an approach to develop a theoretical model which works properly. So I can generalize this and go ahead and say, okay, if you work with this density functional, with this basis set, okay, you can get some good results. And we can even take care of the directional approach. So this was one of the conformer as we go on developing. And the blue clouds on this left side monomer indicates that this part as well as the part on the other, that is going to be more reactive. If I want to study, let's say, hydrophobic hydrophilic effect, this is hydrophilic effect, as you can guess. So water interaction will be possible only on these sides where my amines are, the nitrogens are there, and we go on developing. Okay, this is a simple model. Okay, it is not the complete one. We are still going ahead with a larger one, but this was the starting point, and we got some very encouraging results. Let me show you that. Even at this stage, we got some good agreement with the experimental IR spectra. This one figure which you are seeing is a simulated IR, and when I compare even the smaller model, we get some good agreement. That was a good something very encouraging, but we could not do great on NMR part. Okay, as you can see, these numbers, though they lie within the region, I would like to refine this. So the story doesn't end here. The lesson which we learned here is we should go for the larger structures, larger oligomers, because that will be a faithful representation. How long we can go, that is yet to be answered. Okay, I'll tell you as we go on. Okay, so that was the first lesson. These initial results, since they were complementing some experimental part, we could publish in a book, lecture notes in bioengineering. So the lesson we got here is we can use some good density functional to do some basic modeling. And with that, we went ahead and we selected the another candidate, that is polyvinylidene difluoride, which is very important when you start thinking polymers for aerospace applications. So this is one of the prototype for which the data is available. We shortlisted because it exists in two different phases, and it is easy to model. Means I can go on developing the longer and longer chain and see at what is the appropriate level, at the molecular level, what is the appropriate length, which can represent the good data. Okay, so these are some properties which make PVDF an interesting polymer. It is good chemical and flame resistance, aberration resistance is there. It is having radioactive resistance. So this is one of the very good candidate. Hindustan Aeronautics Laboratory, Hindustan Aeronautics Limited in Bangalore, they are working on this. Okay, so there are other properties also which can take us to the polymer science domain, but let me come to the simulation part. So we go on developing. The story is like we go on developing, and we see now the polymer is getting into the helical form, which we can expect. Now this is just for alpha helical part or alpha phase. Beta phase, I'm not showing here the result. We are working on that. So now with confidence, I can say even with density functional theory, quantum chemical calculation, I can get all the artifacts of the real polymer in this chain. Now, the challenging part is we have to tune our method, density functional model, to get the best band gap energy. We are working on that. But on simulation part, the simulation of IR spectra part, we have some good news. Okay, these are the spectra for 12 and 18 oligomer, and we are happy to tell that from 8 onwards or 10 onwards, the spectra gets saturated. So even if you go on adding more and more number of units, essentially the main spectra, IR spectra, remains unaffected, as you can see here. Okay, it is fairly well represented. So is that the end? No. The important part is, as we go on more and more units, the intensity goes on increasing, which is an indication of charge separation. So that should be taken care, that should be understood properly, that charge separation is there. So which bonds are getting weaker, or how you can work out for various applications, that is very, very important here. Okay, so that was one aspect. Similar, we went ahead and we tried one more toy system, that is MDMOPPV, which is another important polymer from solar cell applications. So there's a monomer, and the modeled monomer is here. And again, the story is same. We go on developing longer and longer chains and look at band gap energy. And now this is going in some right direction after the third trial. Okay, these are the chains which are having very beautiful pattern. There is no alpha and beta phase over here, but we are looking at possibility of other conformers. On simulated IR spectra, it gets saturated after 8. So now at the third exercise, I can say that if I want to model a polymer correctly within DFT, okay, and say something with confidence, the smallest oligomer I should consider is 8, but that is not the end. If I want to study band gap, I have to go further, which can take us to the bulk level. Okay, so we went ahead and we had this band gap energy with respect to the cluster size, and we expect it will get saturated after 12 or something. It is slowly showing the convergence trend. And the interesting fact is the band gap which we measure is 1.5. Now we are expecting to improve it here, where the actual experimental value is 2.2 on electron volt scale. Okay, so now we are at a stage where we can say we can model it, we can fine-tune the DFT or the density functional framework to get it correctly. So these are the primary results. We are working on that and will soon communicate it to the journal. So that is one part that was very encouraging. But the answer is it a good to represent a big molecule or nanocluster part or nanomaterials with such small models? Answer is no. Okay, so we went ahead, but as we know that, okay, this I should not be adding here. Okay. So we went ahead and started thinking we want to add more and more number of atoms, so that I will be talking in nano dimensions, and quantum nanocluster quantum dot is one field where we can use it. Okay, now this is very challenging. They're having many applications. So we started again. Let me tell you that as you go on here from DFT or post-Hartree fog, which is correlated level, okay, which is very essential to study all these properties, the things becomes very tricky. It is a bottleneck problem, like you cannot go for the larger system. It is a difficult task, but still not an impossible. And it is possible with the technique called molecular fragmentation. It is an approach reducing the computational complexity. It is an approach developed by Professor Gadre from University of Pune. And this type of efforts were there in the were available right from 1972. People were thinking to reduce the complexities in quantum chemical calculations, and we at Professor Gadre started in 1994, like thinking of simulating the electrostatic properties and all. But now what we have is one of the very beautiful approach where we can go ahead and look at the molecule, like we may take a panorama mode photo and then have a complete picture and saying, look, here is some beautiful picture. So we go on cutting the molecule with some constraints, some principles, some do's and don'ts, which are here. So with some conditions, these are here. Let me list them quickly for you. We can cut single bond, we can cut weak bonds, non-planar rings we can cut, but we should not cut multiple bonds, planar rings, okay? And then with certain things we should take care, and we can use for the larger system. It has been tested for several other systems as well, and it works very well. That is the beauty of molecular tailoring approach. And once it is done, what you get out of this is very good, very accurate quantum chemical energy or density functional energy. Those who know a little bit of quantum mechanics, we can even get something at complete basis set limit. That is the beauty of this approach. So we are using that to study quantum dots, prototype quantum dots of CDAC, and then core shell quantum dots of CDAC ZNS. Now, this is something which is very interesting. We can look at 1.5 to 2.8 nanometer size quantum dots. We are still extending it for the larger quantum dots. So this scheme is modified slightly to take care of this semiconductor quantum dots. So what are these quantum dots? We started with the very sturdy density functional framework, that is PBE0 with LAN-L2, which is manageable basis set. Okay, we have to improve this further, but these are the prototype clusters which we cut from the crystal. And the reason why we have selected is these have surface reorganization effect, and the data for these particular magic numbers, n equal to 33, 66, 99, and so on, this data is available where we can compare the data from simulation with the experiments. So these are the structures. One is 66, CDAC 66, CDAC 99, and all the way we are going all the way up to CDAC 185. So CD 185 atoms of CD, 185 atoms of SE, and it is 2.7 nanometers. So now we are in nanometer regime, which is very otherwise difficult to work with quantum chemical framework. This is a modeled core shell quantum dot where we are having 66 CDAC as at the core, and the shell is ZNS 199. So this is even a larger one, which will be tricky. So if you look in terms of the computational efforts here, as we go on from 1.5 to 2.8 nanometer diameter, the number of basis functions goes on from 858 all the way up to 4,810. Now, if I want to do this type of simulation, I simply need a powerful computer, HPC. And the total atoms is 370, of the order of 370. We are trying to go beyond 500. Okay, we are working out that also. And this surprise, if I tell you that we had done this simulation on just Intel Core i7 with just 32 GB RAM, it is surprising. Definitely we are doing something different. Okay, so we don't need that much powerful resource now. And what are the results? Have a look here. Okay, so slight underestimation is there for the smaller dot. These are the experimental values, 285, and this from our calculation. But as we go on higher level, okay, this shows fairly good. But this is the freshly cut quantum dot, okay, just where there is no great surface organization. But if we look at the surface passivation and surface reorganization, okay, then we get some good agreement, barring some exceptions. Okay, 3.2, 3.11, 2.5, 2.62, which is in electron volts, which is very good. It is encouraging. Okay, so we are at that stage where we can go ahead and improve it to match. So now we are having a technique where we can look at the systems in nanoscale or nano dimension region. It can be quantum dots, it can be polymer composites, it can be long chain polymers. Now we will be happy to work out with that with good confidence. So that is the beauty of this approach, and we can work out within quantum chemical framework. Once we have that, the next part is how we work out that with MD, which will get us full picture. Okay, so what are the conclusions here? We can use MTA assisted DFT or quantum chemical approach to study the large systems. Okay, band gap energies, we have to look carefully when we select our proper density functional framework. Okay, and then we can go ahead with larger once we tune our density functional framework and get some meaningful results. We are at that stage. We'll be communicating this work very soon. Okay, so where are we heading? We are using this MTA approach within quantum chemical and density functional framework, where we are looking at polymer conformations, polymer nanocomposites, larger cluster with very accurate level of theory. And once we have this, we can propose whether we can propose a better force field for MD simulations, and together use this multi-scale simulation to study mechanical properties That is what we will be heading. We are working on that actually. So whenever we are having next session, definitely I'll be happy to present with this. So let me conclude my talk with this. I would like to emphasize strongly my belief. Okay, the area of computational chemist, when 100, if not 1,000, will go to computing machines instead of laboratory. This is a quote by Robert Millikan, who got Nobel Prize in chemistry in 1966. So it won't be complete. My talk won't be complete unless I thank my mentors, my advisors, Professor Sridhar Gadre from Pune University, Professor V.N. Rajshekharan Pillai, Vice Chancellor of our university, Professor Shivram, ex-NCL Director, Professor Libero Bartoluti, Chairman of Chemistry Department, East Carolina University. He is my collaborator. Then Professor Shrikant Lonikar, Dr. Vadgaonkar from NCL, Professor Yashonath, SSCU IISc, Professor Shigeru Nagase, my boss in Japan, Professor Don Truller, who is so generous to give me access to Minnesota Supercomputing Institute to do some of my simulations. I was fortunate to have associated with him. Professor Carl Johnson, who was very kind to help me on multi-scale simulations of many systems at University of Pittsburgh. And thank you all for your kind attention.
Yeah. Thank you, Professor Kumplani, for a nice presentation. Now session is open for the question and answer. Any question from the audience?
Yeah, I have a small question, Professor, very nice talk. Could you also, in your modeling approach, could you also consider the cool length of the polymer in the matrix and the rods? Sometimes we might use rods or different shape. Some of the modeling experts also, try to look at the diameter of the particle and the cool length of the polymer chain. Could you give us some light on that?
Okay, I'll be happy to do that.
Yeah.
Thanks. That's a nice question, actually. Because I'm always open for the discussion with the experimentalists. That doesn't mean I'm not interested to talk with computational people. Since you asked this, it was a very apt question, actually. Look, that was the first attempt we started is whether we are able to model that, because these polymers within quantum chemical framework, people model that. But it is just a model, okay? That's saying a buffalo can be a model for elephant just because it is black, okay? Which is not a faithful representation, okay? As we know, though someone may argue it is four-legged animal, black and herbivorous, it is not a proper model. So first challenging part was, though there are studies on polymers with DFT, it should be matched with the experimental. Then I'm going in the right direction. So that was the first part. Now we are at a stage where we can go ahead and think of what you are saying, many strands or the structure or in 1D or 2D like that. That can be definitely done. So if you have a particular system in mind, I'll be happy to discuss and collaborate or work on that. Yeah, so just we can discuss how we can, what is it's going to be, or what is it's the monomer, and we can go ahead and build in 3D how it can be. That cluster building approach is there. We can go ahead and use it for polymers as well.
Thank you. Very good. Yeah.
Okay. Any other question from the other audience?
Yes, sir.
Yes, please. Some interesting question.
Sir, good morning, Professor. Thank you for the presentation. Sir.
Yes. Yeah, please. Hello.
Yeah, just go ahead with your question.
Yeah, I think.
Yeah.
Or you can just email me. I'll be happy to answer.
Yes, sir. Sir, can you hear me now?
Yes.
Yeah.
So in the aerospace application section, you mentioned about selection of polymers and tune DFT model to get a appropriate band gap, etc. Right, sir?
That is just one part, but the thing is whether we can model the structure correctly. Okay, because it in both phase, alpha phase and beta phase. So how we can work out, that is a step one. Okay, that's what I said. It is a small part of a big system. So though alpha stage is stable, we have to think of in terms of Boltzmann distribution, how beta phase also will be coexisting. Okay, so together when I go, whether I want alpha phase or beta phase, that we have to first finalize, and then we can take either of the modeling, alpha phase or beta phase, or mix it. Okay, we can work out with that. And then
okay, sir.
And if you want to do this reactions on that surface, that is also possible. I had done those type of studies. Okay, reactions on this surface. For aerospace application, it is typically thermal protection system of a space shuttle. We had done the simulations on that, multi-scale simulations. So we can simulate even the reactions occurring on the surface, even at room temperature, even at high temperature as 1650 degrees Celsius, and even at moving at, let's say, 8.5 meters per second. That is a very high speed, 2.5 Mach. Which is a typical speed of a spaceship during re-entry or atmospheric re-entry. We can even simulate that surface also with multi-scale simulation. That is the strength of simulations, which can match with wind tunnel experiments. So you take it from me. We had done that type of simulations. It is possible.
Oh, okay, sir. So actually, you're talking about tuning DFT model. So what are the parameters we can take, or what are the criteria to choose a particular parameter, sir?
Look, it is like if you ask me how to make aloo paratha, okay, which I cannot tell you just in 1 minute or so. The first thing is, like, as we know, I mean, it's like a surgeon also has a knife, kitchen also we have a knife, and a butcher also has a knife. But that same knife, you cannot use it for doing a critical surgery. Okay, so like that, there are different density functionals, different basis sets. You can go ahead and make various computational models, more than 200. Okay, but you should know which one is correct. Okay, it's just like you cannot use cannon to kill a cockroach. Okay, so you should have a proper way, or your density functional should be appropriate enough to deal with your problem. So there are some of the density functionals are developed for surface reactions. Some of the density functionals are developed for catalysis. Some of the density functionals are developed for main group chemistry. Some of the density functionals are good for organic reactions. Some are good for barrier heights and energetics. So you have to think which one you want to do. Okay, and based on that, okay, just because it is there in the program, if I start using it, then I'm doing the mess. Okay, because you may start with the minimal basis set, something like 631G or 321G. 631G is, people call it decent. Even we used to call it decent in 1998 when I was JRF. Okay, but if I start saying saying that I will use 631G to simulate this surface or the reactions at the surface, I'm doing hopelessly wrong. Okay, because that won't tell me the energetics, and unless I tell the energetics or match the spectra, I'm not doing my job properly. Okay, so you have to say that, okay, check which density functional, which basis set is good. Check the literature, check the system with which you are dealing, check the density functional or the methods from the developer, that okay, this will work for this particular system. Okay, and then once you get that, you will be pretty close to, like Google, low accuracy mode. But if you want to go to someone's home correctly, you have to put Google in very high accuracy mode, so the error is less. Okay, and how you can go on further minimizing the gap, okay, so that you can even guide or challenge the experiment, that is something you realize after, by experience only. Okay, there is no clear-cut protocol how you can go on refining. Okay, for that you have to talk to a practitioner who is into that, and then he or she can help you. But blindly, a word of caution: computer is not intelligent. Whatever you give, we just give numbers. So that is just data. And computer, even if I give wrong data, okay, it will give me some numbers. So those numbers, whether good or bad, whether they are making some sense, physics, chemistry, or science, it all depends on how we develop it. Okay, what goes inside. So unless we are sure what we are giving it, which model I'm using, it is garbage in, garbage out, GIGO. Okay, so we have to be very, very careful while selecting any model chemistry and even modeling the system. Okay, so that is the short answer to this, but what you get is you have to develop your understanding for the system. So after 3 trials, now we are at a stage where we can say something, okay, this is what we can use for our systems. So that is the key.
Okay, sir. Thank you, sir. Thank you so much, sir.
Okay. Let's congratulate Dr. Kulkarni for his nice presentation.
Thank you, Dr. Day.
Yeah. Thank you, sir.
Thank you.
Now I think there is no more talk in this session only. There was 3 talk was there. Now.
Okay. Let's conclude this section: theory, modeling, and simulation. I thank you, Dr. Sudipta Basu and Manojit De for nice sharing the section.
Thank you.
Then we can move on to the next section, energy. I invite Dr. Raki Kandelwal, Department of Humanities and Science Coordinator, Government Women Engineering College, Ajmer, Rajasthan. Welcome, ma'am. You are not audible. Ma'am, you are not audible. Sorry, ma'am. Can you please check again?
Yes, ma'am, you are audible.
Hello? Ma'am.
Yes, audible.
Actually, you are audible.
We can hear you, ma'am.
Okay.
Ma'am, actually, I'm not being able to hear what you're speaking, so it is not audible for me.
Yes, madam. Thank you. Oh.
Share the screen, sir. Click பண்ணுங்க சார் மேலே இது click பண்ணிட்டு
I cannot see me, no? Can you see me? The slides also? Is it slides are visible to you? Okay.
So entire screen is shared, sir. Entire screen is shared.
Can I start now? So first of all, I would like to thank Dr. Sabu Thomas, Vice Chancellor, MG University Kottayam, for giving me this opportunity to present the work which I have done last 5 to 6 years here. And I used to visit MG University very often. I know Professor Arvind Kumar also. I visited, I think, 3 to 4 times where I had a chance to see our Professor CN Rao also. So thank you for inviting me again to give the talk about how we can produce hydrogen using the light as a source of energy with the photocatalyst. Might be interesting for you. So why we are going for the renewable energy, as you know very well, because of the rapid economic growth as well as the population exposition. So that is automatically enhancing the demand for the energy. And currently more than 84% of all energy, so which are meeting from the, which is made from the fossil fuel. However, faster depletion of the fossil fuel as well as environmental pollution, global warming, as you can see very often in Kerala, how we are getting the thundersnow, the rain that is just how do we call the thunderburst because of this warming. So because we are using continuously the fossil fuels that is producing the greenhouse gases, which is a reason for the increasing the global warming, one of the reasons for getting such kind of rain. And already in 1874, Jules Verne already said that water will be the coal of the future. So last more than one decades, I think more than 5 decades, people started using the water to produce hydrogen by splitting. Once the physicists in Honda they discovered splitting the water through electrochemical methods. After that, people are extensively working on this method to produce hydrogen using water as a source of energy, but it's not possible. It's a thermodynamically hidden process. So for now, people have started using the scavengers through which they're able to produce hydrogen effectively. That's the reason it has taken again momentum to produce hydrogen using a water in the presence of sunlight. Why we are producing hydrogen is one of the primary candidate, and having the highest energy density. It's abundantly available, as you know, it is in the water, organic matter as well as hydrocarbon. So that will be the future failure undoubtedly. As you can see here, the world energy consumption by energy source. As already I told you about all these things, you can see here the projection, the renewable energy the usage is gradually increasing. I think more than 50% of this future energy will be met from this renewable energy. So people are working on that. Even our Prime Minister also, the 2020 November announced the hydrogen mission, National Hydrogen Mission. People are working towards that. Last year, our Finance Minister also sanctioned 1,500 crores for that. So for the future, we are producing 6 million tons of hydrogen. So after 5 years, the production will be increased 5-fold. We are expecting to be 30 million tons. So the remaining the 25 tons they are going to produce to the renewable energy. As you can see, 95% of energy which we are consuming, 13 terawatts energy. So mostly from the coal tar as well as fossil fuels only. So 5% of energy which we are which you are utilizing now, mostly from the renewable energy. So renewable energy, there are different methods of production of hydrogen. One is the thermal methods. In that you can see here thermolysis, thermocatalysis, thermochemical, and electrical, which is powered again by this solar thermal, electrolysis, and plasma deposition. So we are focusing on photocatalysis. In that also photoelectrochemical. This is one of the promising methods people are focusing now. The PV, electrolysis, and biochemical. This is a very less production of hydrogen. So among the different methods of production of hydrogen using the renewable energy, since we are working in photocatalysis, we are interested to use the photocatalysis, also focusing on the photoelectrochemicals. I'm going to talk about 5 to 10 minutes how the photocatalysis is feasible method to produce hydrogen using sunlight. So this is left side, you can see the mechanism. Any semiconductor which has a band gap more than 1.2 can easily absorb light from visible region, and the electron from balancing band move to conduction band. These electrons, the protons, so they take away electron, you can produce hydrogen. This is uphill process. It is not a spontaneous process. Once it gets excited, as you can see here, this reaction is spontaneous. That is the reason we have been working. The lambda of this band gap, as I already told you, 1.25. Or this light with wavelength 1008 nanometer is sufficient to excite the electron from valence band to conduction band, or we need delta energy of 237 kilojoules for thermal energy to decompose water to hydrogen and oxygen. This is the overall water splitting reaction. As you can see here left side, and the band gap of semiconductor should be greater than 1.23 electron volt, as I already told you. And the bottom of the conduction band must be located at more negative potential than the proton to produce hydrogen. The top of the valency band must be more positive than the oxidation potential water. So these are the prerequisites when you take the semiconductor. It is not only the band gap of the semiconductor, and also the position is very important. So it is more negative and more positive. You choose the catalyst in such a way that you can be able to produce more hydrogen. But we are only looking at the reduction process, not oxidation process. Since the oxidation process takes more time, we are suppressing the oxidation process. So we call the photo reforming. For that, we are using the sacrifice reagent for methanol, ethanol, triethanol, amine, so many things, lactic acid, so many sacrifice reagent we have been using. So this sacrifice reagent react with the holes, and then we'll again getting the secondary radical. That secondary radical also producing hydrogen. So this is called the photo reforming. So we are stopping the oxidation, and then we can enhancing the only reduction process. If you see our methods of production, we can see maximum hydrogen. Not we cannot get the stoichiometric production of hydrogen and oxygen. This is another method of producing the hydrogen from water using the sacrifice reagent. We call scavengers also. So what is evaluating the performance of photocatalyst? The three things are parameters are very, very important. The apparent quantum yield, as you can see here, the number of hydrogen molecule released and number of instant photon in 1000. If the apparent quantum efficiency is very high, you can be able to produce more hydrogen. In addition to that, if you take any photocatalyst, if they meet the STH, solar to hydrogen efficiency, if it is 10, that catalyst can be used for the commercialization. It is not so easy. So this is a molecule, so this is a formula in which you can easily find out the STH, the catalyst that you are producing hydrogen in your laboratory. If it is more than 5 or about 10, you can easily use that catalyst for the commercial scale and large scale production of hydrogen, provided they should be stable for 10,000 hours. In addition to that, there is a turnover frequency, the number of water molecules split in an active site of a particular period of time is given. That is again the stability of the catalyst. So three things are very important when you choose any photocatalyst for the splitting of water to produce hydrogen. In addition to that, we cannot use the UV light all the time. It's a tropical country where we can get the sunlight most of the time. And if the catalyst which absorbs light within this 500 to 700 nanometer, as you can see here, they can able to meet the STH of 10. So whenever you prepare the catalyst, the semiconductor, if you absorb the visible region, if you take TiO2 mostly around this region, that's what we are taking the low band gap semiconductor where they have the absorptions is in the region, but the recombination is very fast. That is the reason we are using the mixed oxide catalyst. As you can see here, the catalysts which are suitable for the production of hydrogen, where they have the more reduction potential, more oxidation potential. We can use the copper is the best catalyst, whereas iron is not the best catalyst, as you can see from this graph. And also another prerequisite, as I told you, the catalyst is absorb light between 500 to 700 nanometer in such a way that you can be able to meet the STH of 10. And another, you can see the overall progress, as I said earlier, after discovering of the production of hydrogen by water's electrochemical splitting by Fujishima and Honda. After that, people started using the different types of water catalysts, that's splitting water. Even I worked with Professor Anko, the Osaka Prefecture University 20 years before. So he has widely worked in this area to split the water separately, hydrogen and oxygen, different methods. Still they could not. So now again people started using, as I said, sacrifice reagent. So once you use a sacrifice reagent, we can be able to increase the rate of reaction 5 to 10 times. As a result, people now started working on production of hydrogen using the solar energy. As you can see, the overall progress of this photocatalysis from 1972 to up to 2020. As I said earlier, the mixed oxide catalysts are working efficiently for production of both one-step photooxidation as well as two-step oxidation. This is called Z-scheme mechanism. I can explain you later. So now people are working with even C3N4, other non-metal materials for splitting of water to produce hydrogen. So this gives a clear information where we are right now. And you can see here, as I already told you, the apparent quantum efficiency of the various water water splitting already reported. You can see our recent review. So anyone, those who are going to start work with photocatalysis or splitting of water, especially using sunlight, this review will be very, very useful. So I think you can see the apparent quantum efficiency 254. These are the catalysts where we can get the maximum efficiency for lithium transium titanate, but the absorption is only 360. It's a near visible region where you cannot meet the STH of more than 5. As you can see, all other catalysts, the efficiency is less than 500 nanometer, and this is one of the reasons this catalyst cannot use it for the commercial scale. People still use working on the catalyst to improve the efficiency. So these are the overall catalysts which gives the maximum AQU apparent quantum efficiency with respect to different wavelength. And you can see here the highest reported solar to hydrogen conversion efficiency of various photocatalysts. In that you can see the cobalt-based catalyst gives a 5.4% with respect to wavelength 430. Similarly, another one 515 with the cobalt oxide. As I know, the cobalt oxide in the production is somewhat not best, though the catalyst gives better results. So these are the catalysts so far reported where they can be able to produce STH around 5 and more than 5. If it meets, as I already told you, 10, that catalyst can be used for commercialization. And again, as I told you, the catalyst should absorb the wavelength region between 500 to 700 nanometers. So they are still less than the 500 nanometer. Still, people are working on improving the absorptions towards that visible region so that these catalysts can work efficiently for longer time to production of large-scale production of hydrogen. And this is again apparent quantum efficiency of various photo reforming catalysts, where in the previous one is the one where they did not use the sacrifice reagent, where this one we used the sacrifice reagent, that's called the photo reforming photocatalyst, where only mainly focusing on reduction part. In that you can see the quantum efficiency again of this kind of catalyst, zinc, indium, sulfide, and this catalyst has shown the apparent quantum efficiency of the 93, and you can see platinum based nickel mixed oxide, again not nickel oxide, the mixed metal, you can see the 100% efficiency, and but this absorption is less than 425. So this catalyst again we cannot use it for the large scale production. We don't know about the stability of the catalyst because this is sulfur based catalyst. As you know, sulfur based catalyst, they are very good for water splitting. You cannot use those catalysts more than 2 to 3 times. The chalcogenase, they easily get decomposed. The sulfate leaches out from the system. That is the stability of the catalyst is a very big issue. That's why this cadmium sulfate, we have been using this. We stopped using the metal sulfate catalyst, though the efficiency is very high at first time, but we cannot use the catalyst for a long time. So these are some of the drawbacks. Still, we have been working in the field to meet all the prerequisites to produce hydrogen viably using the sunlight as a source of energy. So as I already told you, you cannot just like that use the semiconductor. Whatever you have been preparing, even it has absorption in the visible region, you cannot produce hydrogen. As you can see, these are hurdles. The band gap is less than this absorption. You cannot use it. Then the other one is the radiation. This is also again the radiation excitation. It also takes energy. It takes some time, and also recombination is another process. And then the fourth one, again you need more energy and produce a hydrogen, and again the recombine to form this water. So you have to take all the 6 steps to produce a hydrogen very carefully. So not only the catalyst which meet all the prerequisites, these are another drawbacks which are the intrinsic in nature. We have to address very carefully. Otherwise, the catalysts are very good, but the efficiency very, very less. For that, we are doing a lot of engineering work to make it more stable, how to take care of the 7 points. This is a photo reforming where we are using the sacrifice reagents. Once you use the sacrifice reagent, so the energy which you are supplying is less. With less energy, you can be able to oxidize so you can know what you can do, the suppress the oxidation, thereby producing the more hydrogen. So these are the normal mechanism. If you take N-type semiconductor with the metal, you can easily produce hydrogen. Similarly, P-type along with the metal, You can refer some of the papers. You can produce N-type semiconductor, P-type semiconductor along with the metal. You can be able to produce hydrogen as well as the mixed oxide semiconductor, where the one catalyst with a low band gap acts as a sensitizer. For example, you say bismuth oxide. Bismuth oxide is able to absorb light in the visible region. Then the energy levels are arranged in such a way that semiconductor 2, even if you take TiO2, the band gap is 2. The energy levels are arranged in such a way that the electron from the conduction band easily move towards the conduction band of TiO2, so that you can activate the TiO2 in the visible region as well as you can prevent the recombination. So this is a mixed oxide catalyst. We have been working on this field because this can be the low band gap semiconductor act as a sensitizer. That this is a way you can use the sunlight as source of energy. This is a Z key mechanism where the electron move from LSM band conduction band. From the conduction band, it move towards a valence band. Then it goes to the conduction band. This is called Z key mechanism. In this place, the graphene oxide supporting materials are playing the major role, where we are able to get more than 10 times efficiency using the Z key mechanism. Either use N-type or P-type metal oxide with mixed metal oxide, metal metal oxide with the Z key. With supporting material, one can easily produce hydrogen, but still it is very difficult. As I said, apparent quantum efficiency and STH are very, very important. So these are another way, as I said, dye sensitized. You can use any dye which can absorb visible light. They can donate electron to the semiconductor, and also this is step 5, improving the absorptions of these semiconductor, adding the lanthanum or other metals on the TiO2. Similarly, in the plasmonic metal, if you dope that plasmonic metal like the platinum, silver, and gold, as you know, because of plasmonic reduction taking place, it absorbs visible region. It is one way of enhancing the photocatalysis through this water split, through the visible light, and then you can easily split the water into hydrogen and oxygen. This is already I told you. So you can work on the metal oxide. In the metal oxide, usually shift the valence band as well as other things. There are so many mechanisms are there, engineerings are there. So one has to work all the. It is not easy to optimize all the parameters. Wherever possible, you can take into account of all these things to produce a very stable photocatalyst, which can be long last for the 10,000 hours. That catalyst can be used for the large scale production of hydrogen. This is a simple setup that we are having in our laboratory. These are 250 ml. It's a kind of the conical flask, and it's covered with tight with the rubber spectrum, and then we expose to light for some time. Then we collect these gases from the overhead cells, and then we can inject in the GC. That is the way we are checking the production of hydrogen using the photocatalyst. We keep those photoreactors in the sunlight. It's a terrace of the building. It's called Raman Research Building, where you have equipped with all the state-of-art facilities. More than 50 crores instruments are here, and this is a lamp. If there is no light, we are using the Oriel lamp. This is from the US. It can produce the light from 200 to 800 nanometer with the different filters. You can cut the visible or IR, whatever you want. You can produce the light. So produce the hydrogen using this either visible light or UV light, IR. So this is a very good light source. We are using this one. If there is no sunlight, some catalysts working in the UV also. For those catalysts, we use this kind of. So the light setup, you see, this is overall the lab setup that we have it here to produce hydrogen efficiently. So this is, as I already told you, so we have been synthesizing a lot of metal oxide. So what we observed, the mixture of metal oxides gives a promising result for production of hydrogen. Not only for hydrogen, we also observed for the photocatalytic decomposition of organic pollutant very effectively, 10 to 15 times, using the sunlight as a source of energy. So we prepared TiO2 by hydrothermal method, and copper oxide, TiO2, and graphene oxide. We prepared graphene oxide by modified Hummer's method, and we put all together by impregnation method. We prepare the copper oxide, TiO2, and RGO, and you can see the temp picture. So the average particle size of the catalyst which is prepared using the ultrasound. So since all the catalysts which we have been preparing, we also put it in the ultrasound. Because of the physical force that is coming up from the ultrasound that can easily control the size of the particle, it always leads to interparticle collision. So by prepare any catalyst which you can prepare, just you simply put it in the ultrasonicator, you can be able to reduce the size from 50 to even to 5 to 10 nanometer. So we prepared the same way. As you can see here, the catalyst prepared by ultrasound were around 16 to 17 nanometer. As you can see the mechanism, emits the copper oxide, act as a sensitizer. The band gap is 2.8. It can easily absorb the photon from the visible region, and the electrons move from the valency band to conduction band. It is in such a way it is arranged. The electron easily move from the conduction band of copper oxide to the TiO2. TiO2 which is less active in the visible region because the band gap is 3.2. The sunlight which falls on the surface of the earth has only 4 to 5% of UV. So it does not work very well in UV sunlight. That's the reason we are using copper oxide sensitizer to activate the TiO2, as well as the rate of recombination can be prevented. In the presence of the graphene oxide, as you can see here, the graphene oxide is very good, which can easily remove the electron from the conduction band and take away to the, if there is any solid particles there, they can degrade, as well as if there is neighbor catalyst are there, because this is a mixed oxide, so they are almost in the same proximity. The electron easily transferred from the graphene oxide to the conduction band of TiO2. So as you can see the you can see the PL spectra, the PL spectra, the photoluminescence spectra of TiO2, as you can see here. This is the more absorptions you can see at 450. That means more recombination take place. The electrons holes are formed, but the intensities represent the more absorption. You can see that means the more recombination is there. As you can see, copper oxide RGO. Oh, time is.
Yes, sir. You're exceeding the time. Can you
Okay, 5 minutes. Give me.
Okay, sir.
So you can see here the photoluminescence is it's an indirect indication. So if you can see the maximum peak, that means more recombination. The less peak means less recombination. Maybe one can think there is no electron hole formed here, but you can see here the photocurrent is very high with the copper oxide TiO2. That means the electron which are formed from the copper oxide easily taken away to the TiO2. As a result, photocurrent is very high and the photoluminescence is very less. This is indication these electrons are easily transported, the recombination is prevented, and you can see here this is a catalyst. TiO2 is less production of hydrogen, and TiO2 RGO less production, copper oxide RGO less production, and copper oxide TiO2 is less production. Copper oxide TiO2 RGO, we are able to produce the maximum amount of the hydrogen. As I told you earlier, the PL spectra as well as photocurrents are evidence for why the hydrogen is producing very high with respect to copper oxide TiO2 RGO. The catalyst is also very stable. So this was published in the 2015 Nanoscale highly cited article. With that, we got the two projects, one from MNRE and one from the DST. Still we working on that. In addition to the TiO2, instead of copper oxide, you can use the organic compound. We use the catechol, and catechol gets polymerization, act as a sensitizer, and decreasing the band gap of the TiO2 from 3.2 to 3. It actually visible light catalyst. As you can see, the photocurrent is very high in the presence of the catechol. That means the electrons, as soon as it is from the catechol, it move towards the conduction band of TiO2 and activate the TiO2. And you can see the PL intensity also less with respect to 3% catechol. And here the production of hydrogen is very high, 1% of the catechol. Similar to the metal oxide, we are using the organic compound. The organic compound gets polymerization. That's the reason it got accepted in the Journal of Material Chemistry. It's a very simple way of bringing the TiO2 into the visible region and then produce hydrogen. And there is another mixer metal oxide, indium vanadate, similar to what's called copper oxide. This is also visible light photocatalyst. As you can see, by mixing the 1 weight percent, 2 weight percent of indium vanadate, you can bring the TiO2 work under the visible light region. This is a mechanism, as you can see here, and the 2 weight percent of the vanadate, so indium vanadate, gives better result in that RGO and the 0.5% of RGO. So 2 weight percent of indium vanadate and 0.5% of RGO, you can get the high production of the hydrogen. As I told, copper oxide, here instead of copper oxide with tin oxide, you have to optimize the indium as well as the RGO. We have done same with the copper oxide as well as the RGO. This is another catalyst, C3N4 already explained. This is non-metal. So the C3N4 also gives a promising result, but the recombination is very high because of 2.8 electron volt. We introduce nickel metal oxide. Once you introduce nickel metal oxide, a lot of deficiency sites are created. As a result, the PL intensity decreasing because electrons are get trapped into this defect. As you can see, the photocurrent is very high with nickel doped what's called C3N4. So this is one of the simplest way of activating the C3N4 for more production of hydrogen, just to be introducing 1 to 2% of nickel. And similarly, we are working on the metal oxide framework. People are now using, because it's like the zeolite material, you can tune the pore size, pore diameter, everything. As a result, we can produce a more amount of hydrogen. And this is another way of producing hydrogen using metal organic framework. So this is a papers that we have published related with hydrogen last few years. And this is my citations and H-index and the project. Recently, we got the PERS project. And this is a project we have completed. This is my group. So they are actually working. All the students are completed PhD. They are working most of them in abroad, UK, France, something like that. This is a present group. I received a few awards. And also I received NS course, but since award from the Harshavardhan. And also I have been receiving award from the SR University. So thank you for your kind attention. I would like to thank the funding agency, DST, MNRE, SCRB, as well as SRMIST for funding for this project to produce hydrogen. We are moving to the phase 1 to phase 2 to produce a large scale hydrogen. So what we observed, mixed oxide catalyst with RGO support, we can be able to produce a mere amount of hydrogen, but still we have to go for a long way to meet the STH of 10 and the efficiency as well as absorption between the 500 to 700 nanometers. So thank you for kind attention. Thank you for giving me the opportunity. Thank you, Ananda.
What was the maximum efficiency you could achieve in terms of yield?
Yield, we are getting a few micromoles of hydrogen.
Yeah.
But it is not, as I told you, the production is not the big matter here. The catalyst is stable. If it meets STH of 10, and you should be in the absorption region 500 to nanometer, even if production is very less, you can expose to long time and more amount of catalyst and increasing the area of the contact, so that we can be able to produce hydrogen efficiently because the metals are very cheap. So that's what still we have been working. Whatever we are producing very less, but we are going to scale up soon. But we got almost STH of 5. And one thing we have to see the stability. As I told you, we have to do many engineering to get the best catalyst. And still we are working. So it's not only the amount of the hydrogen, and also other factors are important. If other factors, if you are able to meet, then production is not the big thing. We can produce by just increasing the reactor volume 1 meter to 1 meter or 1 kilometer to kilometer, that we can produce.
Yeah, some people also have done coating this catalyst with the biopolymers so that the stability could be enhanced. Have you also done in that direction any work, coating, grafting with some biopolymer systems?
Biopolymer, sir?
Yeah.
The TOT is again problem, sir. If you see metal organic framework, so the metal organic framework, organic compound, they absorb light visible agent and act as sensitizer. And at some point of time, the metal oxide also decomposes the organic compound. Same thing, the metal oxide also decomposes the bio compound. That's the reason.
Yes.
That's the reason we are using a lot of supports to minimize the decomposition of biological molecule as well as organic compound.
Thank you.
Thank you, madam.
Yes, ma'am. I'll just share my screen right now. So is my screen visible now, ma'am? So is my presentation visible to you, ma'am? Because I'm not being able to. Okay, I'll start, ma'am. Yes. So at the outset, I would like to thank Sabu sir and also the organizers of this conference for giving me this opportunity to present my work in front of you. All of this work has been done under the supervision of Professor Ansandhya Rani from NIT Calicut. So currently I'm affiliated to the Center of Bioelectronics at Oldham University in Virginia. So the topic of my presentation is development of compact enzymatic biofuel cells based on carbon nanostructures. So coming to overview of my presentation, so these are the topics that I will be discussing with you. Coming over to introduction. So what is a fuel cell? A fuel cell is basically an electrochemical energy conversion device. The fuel cell has an anode, a cathode, a fuel a fuel which is glucose in my case, a reductant which is water can be reduced to which is oxygen that can be reduced to water, or peroxide which can be reduced to water, and a separator that is optional component in enzyme fuel cell. So based on the power that is being produced, fuel cells can be classified into many types, and we'll be discussing about biofuel cells which operate in the lowest regime, that is of 1 milliwatt. Can be used for applications like powering of sensors. Biofuels, enzyme fuel cells come under the category of biofuel cells, and they work on the oxidation of molecules like glucose by enzymes that are immobilized on nanomaterial modified electrode surfaces. So the other component of biofuel cells is microbial fuel cells, which use microbes for the same process. So the most important process of enzyme fuel cell is enzyme wiring. So in the case of enzyme wiring, an enzyme is immobilized or anchored on top of a nanomaterial modified electrode surface, and using and in two modes. It is either the direct electron transfer, wherein the redox core of the enzyme is directly linked to the nanomaterial modified electrode surface, or it is the mediated electron transfer, wherein the redox core is connected to the nanomaterial modified electron surface using a mediator. That means the mediator is used to communicate the electrons that are produced by the redox reaction. So a lot of carbon nanomaterials have been used for the immobilization of enzymes. MWCNT, reduced graphene oxide, mesoporous carbons are all used because of their large number of properties like intrinsic conductivity, large specific surface, and ability to act as conducting nanowires. Now, starting with the technical familiarization. So we usually use cyclic potentiomograms to identify the potential of an electrode towards oxidation and reduction. So when the fuel is added, there is an increase in oxidation current at a particular potential, and when the reductant is added, the reduction current density increases. So the difference between the potentials of the cathode and the anode, that is the reduction and the oxidation, is a calculated OCV of the fuel cell. So a method to find out the real world performance characteristic of the fuel cell is this fuel cell polarization, wherein the experimental OCV is actually the OCV at zero current density, and the short circuit current density is the maximum current density that can be produced by the fuel cell. The power density of the fuel cell is a performance metric of comparison between different fuel cells that are produced, that are made. So depending upon the paper volume and the market demand, this field has received a huge influx of articles, and is also has huge prospects for development. So as to why I got into this work is global warming has been a huge problem because of large scale use of fossil fuels, and not only that, this global warming has led to the emergence of a lot of deadly diseases due to the melting of the Arctic ice. Also, the increment in sea levels has led to a danger to the ocean dependent economies and countries. Because of this, we need to continuously monitor the environment. However, when we use sensors to monitor this environment, it is always necessary that these sensors also operate on environmentally friendly molecules like glucose, which is why there is a sustainable powering of sensors that is required. Therefore, the glucose fuel cells can be used to power very small sensors that can monitor different aspects of the environment. So chronology of the work that I will be doing over here is one, which is a planar fuel cell, that is an agar-based membrane separator fuel cell, and the second one is a 3D printed fuel cell, which is almost the size of and volume of an 9-volt battery. Coming over to the first work, which is a hybrid hydrogel separated biofuel cell. So here there are a lot of papers in literature which actually stated that the hydrogel that is used as a separator is made using a lot of costly components, and in addition to that, there are also complex redox reactions that happen in these electrodes, which make them not very favorable towards mass scale production. So because of this, we envisaged an MWC antipyrine carboxylic acid molecule using a pi-pi interaction strategy, and this MWC antipCA was used for the immobilization of the enzyme using Ca2 plus as the link layer. When the different stages of modification were observed after the SEM, we could see that the materials were getting deposited, and the immobilization of the GOX was confirmed because of the globules that were present at the different parts of the electrode. In addition to this, Fourier transform infrared spectra was also used to find out the successful immobilization of the glucose. In addition to impedance spectroscopy, where there was an increase in resistance, which can be seen from this semicircle, to point out that GOX has been immobilized successfully. Also, CVs in ferricyanide also showed us, corroborated with our findings with the previous ferricyanide and also the EIS and also the impedance. In addition to this, we wanted to understand. So Ca2 plus immobilization is basically an ionic immobilization. So we substituted that with a covalent immobilization, and we tried to find out the change in current density when these two methods were used. So we could find out that the ionic immobilization produced the maximum current density, which is why we could say that the Ca2 plus immobilization is the desired strategy that can be used over here. Now, in the presence of oxygen, when glucose oxidation happens, and when Ca2 plus is used as a link layer, we got an increase in current density, and this current density is actually respectively good enough to be used as an anode of a fuel cell. So we prepared the hydrogel by heating agar and PV at 140 degrees centigrade, and we casted that into a very thin film. This agar PV was used to store as well as supply glucose to the anode side. The storing and the supply of glucose was confirmed using FTR and also using Benedict's study, wherein the exposure to Benedict's reagent, it turned the glucose to brick red. And this is actually seen from this picture, which shows us the agar is capable of storing as well as supplying glucose to the anode of the fuel cell. Now, coming out to the cathode side, we were very careful to synthesize a material, in this case argioceria, that is highly tolerant to glucose, because when we envisage a material that is aura active, it needs to be tolerant to the amount of glucose also. So initially we synthesized the material and we observed it under the SEM and TEM, and under the TEM images we were able to see that cube-like structures of ceria were deposited all over the RGO. We also confirmed the successful synthesis of the material using FTR and XRD diffractograms. And the impedance actually showed that the material possessed very low resistance, because the semicircle has very low resistance. This is how we say that the material has very low resistance. So we use it for the oxygen reduction reaction, and we were able to see that there is an increase in current density with the increase in the rotation speed. However, now this is not as the current density that is being produced by this material may not be high as compared to the PTC, but this material is highly glucose tolerant. So as I stated earlier, it is highly important that the cathode is glucose tolerant, so that the performance of the fuel cell is not affected, and which is why we were able to prove the glucose tolerance of the argioceria material also. Finally, the fuel cell was assembled, and we were able to see that a power density of about 6.25 microwatt per centimeter square was being obtained. So as far as the comparison to literature, we were able to see that it is comparable to the different values in literature, and the estimated cost of the fuel cell was about $4, which is comparatively higher than the $2 that is a reference cost that we have kept for the construction of a microfluidic fuel cell. So in terms of contribution, we have constructed a fuel cell which has a power density of 6.25 microwatt per centimeter square, and the fuel volume that we use is about 10 ml of 500 millimolar of glucose solution. Now, coming on to the second work, we utilized 3D printing in order to construct low volume fuel cells that could actually perform much better than a previous fuel cell. And this is where 3D print, there have been reports of using of 3D printed fuel cells for powering up applications. However, they have used peristaltic pumps over here, and that actually affects the mobility of a fuel cell. So we wanted to construct a fuel cell that could actually be portable, and it also occupied very less volume. So with this in mind, we used 3D printing to construct the container of the fuel cell, and we prepared the electrodes using this scheme. So a carbon cloth, and we modified it with RGO, and then we had PABA, that is para-aminobenzoic acid, electrografted on the RGO in neutral as well as acid medium. So the RGO was actually deposited using an electrochemical strategy, and the PABA also was electrografted. So it is an electrochemical technique again. Finally, on the anode side, we used glucose oxidase that was there in an osmium-based redox hydrogel for the glucose oxidation in the anode. And in the cathode side, we used Prussian blue for the reduction of the peroxide. The Prussian blue is actually electrodeposited using chronoamperometry. So this is actually the molecular structure of para-aminobenzoic acid, and this is the structure of the Prussian blue that was electrodeposited. Some images, the different stages of modification for PABA electrografting, we could see that there was a crumpling of the sheets of RGO that was observed, and this crumpling of the sheets actually confirmed that there was some kind of a modification that had taken place. So we confirmed, using the FTIR, we analyzed the electrografting in neutral as acid medium, and as it can be seen, there is a change in the peaks. So this actually states that there is a different functionality in case of neutral medium that is exposed on top of the material, and in case of the acid, there is another functionality. So typically the amine functionality. Since we also observed that there was a surface charge change when PABA was electrografted in neutral as well as acid medium. The same thing again was corroborated using the Ferrician, and based upon these three studies, we actually envisaged a mechanism wherein in case of the PABA that is electrografted in neutral medium, the carboxyl group was facing upwards, which is why we had a negative surface charge for the neutrally grafted PABA. Whereas in case of the acid grafted PABA, we have an NS3 plus ion that is facing upwards, which is why we have a positively charged surface. So we used a negatively charged surface because we wanted a good interaction with the positively charged amine surface of this osmium-based redox polymer, and we actually got a good current density when we subjected to different concentration of glucose. So this is based on this. We created a scheme for working of the anode electrode, wherein the mediator with the cross linker would actually communicate the electrons to the electrode surface. So the some images, so coming out to the cathode side, we electrodeposited Prussian blue for 360 seconds, and we were able to confirm it using FTIR. So we also used cyclic voltammograms to note the increase in current density with the increase in concentration of peroxide. So peroxide has some kind of a corrosive property towards the anode side, that is the enzyme. So which is why we actually limited the peroxide concentration of the cathode to about cathode electrolyte to about only 5 millimolar. So we had the fuel cell designed in Creo student edition. We had it 3D printed. The fuel cell is about the size of a 9-volt battery only, in fact. So we were able to get a OC wave of about 240 millivolt, and that was stable for about 1200 seconds. And we were also able to get a power density of about 16.25 microwatt per centimeter squared. So this is actually a very repeatable value. We actually tried three different combinations, and we got a very low coefficient of variation over here. So however, after 24 hours of performance, the potential reduced to about 120 millivolts, so which is in comparison to 200, is almost a 50% reduction in OCV. So we wanted to mitigate this degradation, and this is why we used 1 millimolar peroxide at the cathode side. And we are able to mitigate the degradation to about less than 50%. And in a second one, we made the concentration of peroxide in the cathode same. However, we gave a small modification of using HRP, that is horseradish peroxidase, for reducing the corrosive action of peroxide on the anode side. So again, we were able to reduce the mitigation. We were able to mitigate the degradation even further, which is why we would suggest these two mechanisms, these two steps, to actually reduce the 24-hour degradation process. So we also studied the function of the fuel cell performance as a function of temperature, and we were able to understand that from 25 to 55 the fuel cell performed well. However, at 5 and 15 we postulated that the agar based the hydrogel, the osmium based redox hydrogel could not perform at lower temperatures, which is why we got a very low kind of performance. So in terms of shelf life, the fuel cell was able to be used for about 2 weeks with a reduction of about only 250 millivolt. This work actually produces a fuel cell with a power density that is comparable, or in some cases superior to the values that were there in literature, which can be seen from this table. And the material cost of this device, we made this material about only $1.3 and we actually beat the reference cost in this case. And therefore, in terms of contribution, we were able to increase the power density to 16 microwatt, which is more than 100% increase from the previous case. And the fuel volume, we were able to reduce it to more than 50% of the initial volume, and also the glucose concentration, we were able to reduce it to 1/5. So we got a higher power density with using lower volume at lower concentration of the fuel, which means that we were able to tune the performance of the fuel cell to much better values. So as a conclusion, I'd like to state that we've gone over two fuel cells. And these two fuel cells are low volume, low power fuel cells that can be deployed to the environment. So as a future work, so I would like to extend the fabrication methods to additive manufacturing. So also fabric-based based self-powered biomolecule sensing can be done, which is what I'm involved in it in my current postdoctoral stint over here at ODU. So there needs to be material variety, and finally, deployable IoT sensors can be used to monitor microenvironments like fields. So as a conclusion, I'd like to thank the organizers for this wonderful opportunity. I'd also like to thank Raki ma'am for spending a really valuable time in hearing the presentation. I'd like to thank my guide, Professor N. Sandhya Rani, and my postdoctoral mentor for giving me the opportunity to do research under them. The characterization facilities would have helped me a lot to understand my work much better. The funding opportunities that I have received for my PhD lab, and those were the foundations for doing this work. I also like to thank my collaborators and the equipment for actually giving me the data that I have present in front of you. And finally, I'd like to thank my family for actually supporting me in this endeavor. Thank you. Thank you, ma'am.
Yes. I'm audible?
Yes.
Yeah. Yeah. What is the percentage of oxygen content in your RGO?
We have you mean in the electron
Syria,
depository
RGO Syria. You prepared RGO Syria material. Yeah.
Yes. One second, I'll just take that slide, please. Yes, so we have not actually
Okay.
found out the
Yeah.
amount of oxygen.
What will be the effect of oxygen content? How it will affect the end property?
I think from what I've understood from the literature was that the amount of oxygen, depending upon the amount of oxygen, the oxygen reduction property would be enhanced or decreased. That is what I understood from literature, and that would also affect the onset potential of the oxygen reduction.
Okay. And what is the size of Syria? It is
The
nano
size of
size.
Syria is about maybe less than 20-25 nanometers on top of the RGO.
Okay. It's just embedded on the graphene sheet, or it has some chemical interactions.
So we were able to understand from the FTR that there are some chemical interactions, but I would say it is more of a physical absorption. So there are very low cases where the RGO is chemically interacting with the Syria. Hello, sir. Hello. Hello. Sir, you're not audible. Hello. Hello. Hello, ma'am. Hello. No, ma'am. I cannot. I'm not being able to hear you actually. Sorry, ma'am.
Hello, ma'am. You are not audible.
Yes, ma'am. Yes.
Moving towards the third talk of this session, I would like to invite Dr. Jyotirmayi Nanda from Department of Physics, ITER, Shiksha Anusandhan, Bhubaneswar, Odisha, India. Welcome, ma'am. Topic of the talk is nanostructured indoor photovoltaic for IoT applications. Welcome, ma'am.
Okay. Thank you, Dr. Rakhi. Am I audible?
Yes, you are audible. Yes, you are audible, ma'am.
Yeah. So thank you so much for inviting me for this lecture. And also I would like to thank Professor Thomas for giving me this opportunity to speak a few words on this current research topic. So I'd like to share now my slide. Ma'am, just 1 minute. I'm just trying.
Okay.
Do you see my slides now?
No, it is not visible, ma'am.
Now?
Yes, now it is visible.
Okay. I'll make it full screen mode.
Yes.
Is it all right, madam?
Yes.
Yeah.
Please
Okay.
start.
Yeah, okay. So in this today's platform, I'll be talking about this nanostructured indoor photovoltaics for IoT applications. So basically here, this topic, it relates this Internet of Things to this indoor photovoltaics, and also this research topic that which is just continuing for the last 2 days. Actually, we have been talking about this nanomaterials. So basically, we'll be just seeing how the nanomaterials can also be useful with such indoor photovoltaics, and at the end to the Internet of Things or the IoT applications. Okay. Finally, I'll just conclude. So basically, this Internet of Things or this IoT, here this is a technology, and it is optimistically expected to benefit our daily life, and that's why this is the today's buzzword, Internet of Things, because it will regulate our daily life in a very smart ways. So the success of this IoT technology will strongly rely on the function and the number of end nodes. So end nodes means, I mean, the sensors, actuators, all this means wireless sensors, actuators, etc. Okay. So here, in this case, these sensors or actuators, this will detect the conditions or environments and communicate each other or link to the gateway by wireless network. So basically, this IoT, it will form a link between human and human or human with the object, so that we can live in a smart way. Because nowadays we want the things to be smart, and smart means efficient. We want to live in a smart world. So here, this even though this there are a lot of designs to operate this IoT in periodically and let it consume the low power, but this long-term power supply, it's a quite challenging task actually to have the power supply which is stable and all. So that causes a crucial factor for the success of this IoT technology. So that's why the scientists, they have thought about this energy harvesting system for collecting this environmental light and also this mechanical and thermal energy. Okay, so that could be used for this alternative power supply of this currently dominated power source from the battery. So as our society moves towards this renewable energy sources, in order to decarbonize this electric power generations, because we have been just last week we have heard to our Prime Minister talking about this decarbonization, and he was telling that by 2050 there should be net zero carbonization in the country, in our country. Okay, so that's why our society is also moving towards decarbonizations. So in that respect, this PV technologies or this photovoltaic technologies, they will be expected to play an important role. And this, among these photovoltaic technologies, actually there are two kinds of environments: outer environment and indoor environment. So basically here we'll be talking about the indoor environments, because that will be both are utilized, because what I am showing in this slide is the IoT virtualization framework, where you can see that both the things are necessary. Means both the outdoor and indoor, this PV technology is necessary for the complete setup of these IoT devices. So this is just about this IoT application domain, what I was just talking about, and what I was talking about, that making human life much more automated, comfortable, and simplified. Okay, using the right amalgamation of productivity and efficiency. Okay, and there are a few examples I have given here, like this smart buildings and living, smart environment, smart healthcare, smart city, smart energy, and smart transport, and smart agriculture. Okay, so basically we are going to be benefited, though it is a challenging task to achieve this thing. So this is not the task of a single community, research community. Actually, this is a task of that synergy between this physicist, chemist, then this electronic engineers, particularly those who are working on this IoT. So that is needed actually to make it more success. And here, this actually what happens in this IoT systems, as I have told that the PVs are needed. So we'll see that how this indoor lighting systems or this high inefficiency indoor light harvesting systems, they will just convert this indoor lighting arrangement. Basically, the indoor lighting systems are diffused lights. So the diffuse and low lighting conditions, and particularly this is just maybe you can say 1/3 or much more less than that the sunlight. So how efficiently we can just use this indoor lighting?
Excuse me, ma'am. You are not audible. Jyoti, ma'am. You are not audible, please.
Hello, madam.
I think some technical issues there.
Okay, then we can move on to the next speaker.
Okay. So now I would like to invite the fourth speaker of the session, Dr. Subhashish Roy from Department of Chemical Engineering, University of Calcutta, India. He will be delivering his talk on chemical approaches to addressing the instability and toxicity of perovskite-based thin film solar cell. So welcome, sir. Please start your presentation.
Am I audible?
Yes, you are audible. Please share your full screen mode.
I make it full screen, but it is not coming. Just a minute.
Your screen is visible, but your PPT is not open, I think.
PPT, I think, opened here. From here, I opened this PPT, but just a minute. Is it open? On my side, it is showing its full screen. Showing here.
You can try. First stop screen sharing, then again try, please.
Yeah, just a minute.
Still, it is not.
It
Sir, I think you're open on two windows. If you close one windows, probably.
Yeah.
Is it coming? Okay.
Yeah, now it is visible.
Yeah, now it's visible. Okay.
Please go on full screen mode.
Yeah. Okay.
Yeah, done. Okay.
Very good morning to all of you. Sorry for disturbance. First of all, I would like to thank Professor Sabu Thomas and organization committee for giving me opportunity to present my research work. Today, I'll discuss the chemical approach to addressing the instability and toxicity of perovskite-based solar cells, in solar cells. I'm faculty member in Chemical Engineering Department, University of Calcutta. So here, if you see, I will today discuss actually the perovskite materials. Nowadays, perovskite materials is very important for the applications of the solar cells, as it is very cost effective and it's giving the high efficiency compared to the other solar cells. So, but it has some of the issues like instability, toxicity, cost issues, of other something cost related issues. Those issues I try to overcome in my laboratory. So here, different types of the atoms we have done, the thermal engineering to increase the stability, new fabrications method with structural property correlations to increase the stability and the toxicity, minimize the toxicity issues. And also, we tried the computational simulation analysis perovskite, for making the perovskite materials high efficiency in theoretical basis. And finally, I tried to minimize the cost of the perovskite solar cells by adding the different types of biomaterials with additions of the perovskite. So these different types of the atoms, my atoms in my labs we have done, and I will discuss on these issues. So if you see in my laboratory, actually different types of the structured property correlations we have to run. Particularly in this case, in the perovskite material, we fabricate the nano rod, nano sphere, nano fiber, or nano composite type materials, and then finally we correlated the structure property relations, and then we applied for these things in the perovskite solar cells and the other also water splitting, all those So as introductions part, if you see the perovskite materials, its crystal structure actually ABO3 structures. So why it is important actually? Because of the large absorption spectrum itself, adjustable band gap, large power conversion efficiency, and it's inexpensive. But if you see different types of the perovskite materials, there is organic, inorganic perovskite materials are there, halide perovskite materials are there, doped perovskite materials are there, alkaline, halide perovskite material there. But in this case, nowadays, the inorganic, organic, particularly methylamine, lead iodide, lead halide based materials is very highlighted because of giving the unique property and higher efficiency for the solar cells. So if you see the organic, inorganic hybrid perovskite solar cells, here the structural band, the A side, B side, we can easily flexible this A side and B side with putting the doping the other materials like A side, CAs, RB, like that. B side, we can dope the tin, copper, gallium, lead, all those things. But nowadays, the lead related in the B side additions with the leads giving the maximum high efficiency solar cells. So, but people are trying to replace the lead with the other materials. So if you see the solar cells, for the applications of the solar cells, solar actually absorb the light in this case of the solar cell, generate the electron hole pairs and excitons to separate the charge carrier to opposite types of the extraction, these carriers in the external circuit. So here in the PN junction in the middle, we used to use the perovskite base, particularly methylamine lead iodide based solar cells for making the thin film solar cells. If you recently see the literature, the other comparing to the other literature, other solar cells, the perovskite solar cells is much rapidly increasing the efficiency. Nowadays, if you see the Saudi Arab King Abdullah universities from one report came, it's reached around efficiency 28.2%. But it is tandem solar cells with the combinations of the silicon materials. And other also one report we got from the literature, the German Helmholtz Center Berlin. It's got 29.80 efficiency, but it's having the silicon peroxide combinations. But in the case of the single perovskite without silicon additions, it's reported maximum efficiency 25.2% single efficiency. In the Tamdon tips, it is 29.1. So in the fabrication process in the perovskite solar cells, if you see, initially in the bottom, there will be the FTO glasses, conducting glasses. On the tops, there will be PN junctions. In the middle part, that is the perovskite materials would be there. So this is the perovskite material structure fabrication method. So if you see the compared the literature, all the perovskite materials, the low material cost, finishing material cost, all are low in case of the perovskite materials, and the efficiency also compared to the high compared to the other solar cells. But what are the drawbacks? Why it is not commercialized till now? Because one problem is stability and degradations. Because it is not stable at the in presence of the ambient conditions, in presence of the moisture, and also the high heating environment, it is not stable. And another problem, what is, because it is addition of the lead. Lead is toxic. We have to replace the lead for making the environmental friendly. And compared to the silicon solar cell, the cost is low, but we can make it still much more less cost solar cells by adding with other materials. So those are the constants we see there we need to overcome. So if you see the we define types of the perovskite solar cells, we can make a correlation with the power conversion efficiency with top cell bottom and solar cell bottom, solar cell band gap. So in the top cell and bottom cell band gap and the power conversion efficiency, if you see this plot, from here we can optimize the efficiency and we can choose the particular solar cell, particular perovskite materials which is need to apply for the particular applications of the solar cell. So before making the solar cells, the one main factor is the tolerance factor. Check the stability of the perovskite materials. If the tolerance factor is optimized, then the perovskite materials, if it is high, above 90, above 0.921, around like that, so it must be stable. So before we synthesis the lab, we have to check the tolerance factor of each and every perovskite solar cells. And here, if you see that if you change the effective radius of the solar cell, there will be structural tuning also be there as a hexagonal, cubic, orthogonal, like that. So here, our challenge to replace that lead material with other environmental friendly material and also increase the stability of the similar conditions of the halide double perovskite not containing the lead. So why it is not able to replace the lead with the other environmental friendly materials? Because if you see the band structure in the p orbital and the halide s orbital, this is the electronic structures where 6s to s is saturated and p is empty. So in the valence band to conduction band, they easily jump the electrons. But if you see the periodic table in neighbor of the lead, there is if you go the top in the SN or GE, here is the oxidation effectiveness is very high in case of the top element presence in the on the lead. And if you go the left side, there is also toxicity is increasing here also. And if you see the bottom, that is the radioactivity also present in this case of thallium and fluoronium. So here, if you see the bismuth here, some also few problems are here because of the ineffective valency. Because the valency is 3, whereas the lead valency is 2. So this is the valency unmatched here. So selections of the materials here, it is very tough to replace the lead with the other materials. So that's why the people are not replacing leads properly with other environmentally friendly materials. So what are the mainly actually issue of the stability of the perovskite solar cell? One was toxicity, what I already told about the lead, and other is the PbI2, that things is come out in the presence of the ambient condition of the oxygens and the UV light. Then finally it's degrade and finally it's hydrogen and the I2 is produced. So these degradations decrease the efficiency of the solar cells and it's increase the instability of the solar cells. So we need to overcome this. So if you see the degradation factor, MaPbI3, if you increase the temperature, if you see the deep brown color goes to the pale yellow color. Yellow color means lead iodide is coming out from the system. And if you keep these samples, keep these thin films in the long time, like 60 minutes, then it's changed to the color because of the degradations of the stability. And also we have seen that the absorption property also, it is decreasing rapidly with relative humidity if you increase. The high relative will increase relative humidity. The absorption property also decreasing rapidly. So that the film property also degrade, and finally the solar thin films efficiency also decrease. So if you compare the methylamine lead iodide with FAPBI3, the formamidinium lead iodide, in this case, FAPBI3 is much more stable in the presence of the thermal heating, also in the ambient conditions, till up to the 60 minutes. If you see there is a figure, it is still deep brown color still presence after 60 minutes. So it is FAPBI3 is much more stable in presence of the moistures and the thermal stability. And the same things after 17 hours, FAI also is stable, and it is not degrade up to 50% of its own property. So here I will discuss how to replace the tin lead with the tin, presence of the environmental tin, and then finally we optimize the structural property correlations, and finally we fabricate this thin films, solar cells, and we report the efficiency. So this is the process how we fabricate the thin film solar cells with additions of the defined percentage of the tin in methylamine lead iodide. We replace the lead from 10 to 100% by the tin, and finally we optimize the efficiency of the solar cells. This is the fabrication process, and if you see the tin chloride salt, that is a transparent salt gel process we have used for fabrications these thin films. And finally, if you see the structural property, this is the Goldman tolerance factor. If you see the percentage of the tin we increase, and then finally tolerance factors also increase in this case, so the stability of the films is much more stable here. So if you see the tolerance factor on the percentage of the tin we increase, we see the tolerance factor also we increase, and we reach up to 1.013 around. So tolerance factor increasing with percentage of the tin doping in the lead. Then finally we check the XRD, the impurities or other phase. It is seen that without any impurities, the film form properly solid state thin film. And then absorption property we have checked for checking the band gap of the thin films with percentage of the tin. So we have checked the band gap and the Arbach constant of the equation for checking the order disorder structure of this thin film. So if you see the band gap of the film, the band gap with increasing of the 10%, you can see that here the band gap also, it is relatively increasing with percentage of the tin. So we have to optimize the band gap in case of the applications of the perovskite material in the solar cells. So if you see the same structure, there is some of the nano structures, nano rod-like combinations with the nanopairs. It is combined in both cases. And if you see the percentage of the tin, we can change up from 20 to 80%. The structural morphological change we have seen initially, it is the particle size, then it goes to the tubular size particles here. So finally, we optimize the percentage of the tin and we check the optical properties, and then we check the electrical properties. We see the current and efficiency in maximum case, and the fill factor we have checked. Here we have seen that 20% doping of the tin is giving the maximum efficiency, around 9% efficiency in case of the application of the perovskite solar cells. So then this is the replacement of the toxic lead in case of the with tin, and we reported the efficiency, and then we attempt to higher extent, much more extent, increase the efficiency of the solar cells. So what we have attained, the defined type of fabrication process, or a dual-step fabrication process we have used for making the much more stable film. So this is the process where we fabricated this film after heating the surface, and then finally top coated with the full transport material. If you see this property, epitaxial growth of the perovskite solar cells in the normal surface after heating, then finally is fabricate the epitaxial thin film. This is the same images of this film on the upper surface of the perovskite solar cells, perovskite thin films. Then we check the Arbach energy for checking the order disorder defect analysis. For it is giving the good Arbach energy that showing the good uniform structure with less defect. And then finally, we compared the conventional process with the dual step process for the current density, where the dual step process, we got the maximum current density of the fabrication of the cell. And finally, with the, we compared the current density, open circuit voltage, short circuit current, and then fill factor, and this power density also with the conventional fabrication process and dual step fabrication process, where we got the much better efficiency, 11% around dual step thermal engineering process. So we able to increase the efficiency and IPC value in case of the dual step efficiency. The IPC value we got around 84%. So here we can optimize that the conventional process, dual step process is much better than the conventional process, and the 20% twin replacement here giving the maximum efficiency around 12%. Still now, some of the problems we have in case of the tin replacement, poor surface coverage, long fabrication time, exposure during equipment transfer, and other trace of the too rapid crystallizations, those problems still there. We are working on these problems to overcome this. And finally, for the increase the stability, we added the dielectric material with the perovskite materials to show that the ion migration should not happen inside the thin films. So here PLT15 we have synthesis, and finally we incorporate PLT15 with cadmium sulfide in place of the perovskite materials, and then finally we check the other all properties. But if you see the same structure, this is the structure of the PLT15 image, and it is the CDMS image. And finally we analysis the team and same from there we got the nano rod-like structures. Then we did the elemental analysis for confirmations, the molecular atoms presence here. Then from here we have done the.
Excuse me, sir.
Yeah.
Sir, it's about time. Four more minutes left. Okay. Okay,
then
sir.
Okay. Then finally we optimized the power, how much power we are getting from the cells and the current density. From here we got the PLT15 CDS giving the good efficiency around the 5%. Then we have added the dielectric material for increase the stability. So finally we check the aging property with checking the VOC value and the efficiency. We got around 250 hours. It's much more stable than compared to the other process and conventional process. So this film is much more stable than the other process. So here we confirm that the additions of the dielectric materials is giving the maximum stability in case of the perovskite solar cells, and it's giving the good efficiency also. Finally, for reduce the cost, we use different type of biomolecules additions with the perovskite materials. Here some carotene-rich biomolecules we have added to reduce the cost of the solar cells, fabricated solar cells. Also, we have added the chlorophyll-rich biomolecules, spinach juice, those things we have synthesis, and then finally we added with the perovskite materials. This is the process of fabrications of the solar cells by additions of the biomolecules. And finally, we check the XRD for phase formation behavior, and then the same analysis we have done in case of the biomolecules. And this is the biomolecules same analysis where both the porous uniform structure we got, and then UV analysis from UV we check the absorption property and optical property. Then this is a report that the efficiency of the solar cell though here much less, but the cost is in case of the additions of the biomolecules is very less compared to the pure perovskite solar cells. Here is the ethanol extracted dicarotene-rich biomolecules and also the protein-rich polymolecules, the efficiency and the fill factor we reported here. So finally, we conclude the extractions of the organic dyes are carried out from the natural resource using defined solvent. And then finally, we optimize the efficiency, fill factor, and we reported low-cost perovskite solar cells. Okay. And nowadays we are working these types of the materials with additions of the perovskites as a perovskite materials, and then finally we optimize the cost. And we've also done the theoretical and computational analysis with SCAP, and then we optimize the performance and then we compare this theoretical value with the experimental value. And then finally, we check the data with experimental and theoretical and compare with it. Okay, then finally, our challenge the world, it should the perovskite fluoride nowadays, its efficiency reach up to 25%. But if we reach the 30%, then this perovskite solar cell would replace all the other solar cells, silicon solar cells, and also the other renewable source of energy sources. Okay, and this is my paper of publications. And this is the PhD student I should acknowledge, and the UGC and the DST grant, ACRB grant, which giving the fund to support my labs. Thank you very much.
Thank you, Dr. Subhashis, for very nice presentation. Now, session is open for questions. If anybody wants to ask some question to Dr. Subhashis. Okay, I think no question is there. So thank you, Dr. Subhashish.
Okay, thank you very much. Thank you.
Please stop sharing. Yeah. So I would like to invite the next speaker of this session. That is the last speaker. That is Dr. Arun Kumar Chandrasekhar from Department of Sensors and Biomedical Technology, School of Electronics Engineering, Vellore Institute of Technology, India. Dr. Arun will be deliver his talk on the fundamentals of triboelectric nano generator and its smart self-powered applications. So welcome, Dr. Arun. Please start your presentation.
Thank you, ma'am. Thank you for organizing this event and for MG University's Professor Sabu sir. And I'll directly go into the presentation. Just 1 minute. Ma'am, whether my screen is visible?
Yes, perfectly visible. Please start.
Yeah, thank you, ma'am. So, so myself, Dr. Arun Kumar. So I'll be discussing today about the fundamentals of triboelectric nanogenerator and its self-powered applications. So slightly different from the energy harvester group. So it's a newly evolved technology. From 2012 onwards, we are working on this nanogenerator. So basically, we convert the physical energy into electrical energy. So as you know that the global power requirement is growing day by day, and at least we thought of supporting the small scale energy harvester like microwatt maximum to milliwatt range at least if we can make a sustainable device, so it will be really helpful to support the global need. I mean to help for the sustainable renewable energy. So in that aspect, we started to work, and there are different nanogenerators known. So triboelectric, piezoelectric is a well-known principle. So now it is known as piezoelectric nanogenerator, which harvests biomechanical or converts biomechanical energy into electrical vibration, and even the wind energy, water wave energy can be converted using this mechanism. The same way, the triboelectric nanogenerator is also a mechanism where you can convert all these kind of mechanical energy into electrical energy. So we know that the capital that we need to invest for any energy like generators like nuclear power station, hydrothermal, or any other windmill, the huge windmill I'm talking. So it's obviously it's high cost capital, and you need periodic maintenance, and you need huge manpower, right? So when we think about these kind of nano generators, it's small in size, cost effective, and also you can use it for a long period of time. And also you can think about reusable of these kind of nano generator. So basically what we are trying to do is to increase, to reduce, that's the thing, to reduce the consumption of battery. So what are all the possible things we can do? We are trying. Okay, so so now we are focusing on self-powered systems. So I'll let you know what is self-powered system in the upcoming slides. So nano generator, basically there are two, as I told, that one is triboelectric and the second one is piezoelectric. So here we are going to discuss only triboelectric today. So basically we are converting mechanical energy into electrical energy. So there are 4 modes that is available in triboelectric nano generator. The one is called vertical contact and separation, lateral sliding, you can see here lateral sliding, freestanding, and single electrode mode. I'll explain you one by one in my work which we done. So the mechanism also, and here you can see that all vibration or mechanical energy can be converted to electrical energy using this nano generator, triboelectric nano generator, using these 4 mechanism. That is a basic concept. Then the power that which we can generate, it was in the starting phase, during the starting phase of 2012. So it was around 3.5 milliwatt per meter cube. And slowly in the end of the 2013, starting of 2013, we were achieving around 313 watts per meter cube. So now it is around 10 years we are apart. So you can think that how the researchers have been working in this area to increase this power density and other application. So there are various aspects, various areas where you can apply this energy harvester as not only as an energy harvester, you can use this device as a sensor. That is the next part, the sensor. We can consider the signal output which is coming from this nano generator you can as a energy as well as a signal as a data. So that is a very good beauty of this research. So you can implement in biomedical things, gadgets, defense technology, MEMS, personal electronics. So these are all the applications where we use this nano generator. And why we need to develop the thing? To reduce the pollution or to reduce the consumption of any other toxic chemicals to develop the energy storage or energy generator. So at least we can support, that's the thing I emphasize. We are not climbing to replace entirely. At least we can support the need of energy where we can control the pollution issue, and also we can make one step ahead for the next generation of eco-friendly energy source. So here a small, typo error. So here you can see that the energy source, let's see the technical comparison. So we know that solar, thermal, mechanical, and biochemical. So that you can see solar is a well established and formulated technology which has around 5 to 30 milliwatt per centimeter square inverse the power density. But when you think about the mechanical energy harvester, which comes with electromagnetic, electrostatic, and piezoelectric, so the range is between around 10 to 10 milliwatt per centimeter square inverse. So it has a huge range of power density. And the major problem with this mechanical energy harvester is it is a continuous AC output. At the time when you see the solar cell, it is a DC. So you don't need any conversion circuit or anything. You can use directly to drive the DC electronic gadget. But if you want for AC, then you need to convert DC to AC. So it's again a lengthy process. So here, this mechanical nano generators or the mechanical generators has a problem that it is not a continuous output. And especially in the triboelectric nano generator, it is a pulsating output. Whenever the contact and separation happens or slide happens, it is a pulsating output. So these are all the few drawbacks that we are actually trying to overcome. And also the major disadvantage or the major problem of this nano generator is high matched impedance. The device impedance is really high. So researchers are working in developing a power management unit to solve all these issues. And the biggest advantage of this triboelectric nano generators, the fabrication is quite simple and cost is very less. Its weight is low and it has a large power output with high efficiency. Compared to the other energy harvester, the efficiency is really high. The major drawback, as I told, the pulsed output, and high impedance. So we are that is if you are really thinking to work on this area, you can think all these problems and you can start your research towards or addressing that. And yeah, so as I told that here, the major comparison between the electromagnetic generator and triboelectric. So here we use a contact electrification and electrostatic induction. In EMG, you know that we use electromagnetic induction principle. Here, contact electrification and electrostatic. So here you have high durability and high impedance and low durability. Why? Because of why it is low durability? Because it is it's a moving, like it has a wear and tear, right? But we have solution to overcome that. So so let's see something in technical with triboelectric nanogenerator. So the principle here for the triboelectric nanogenerator is like contact electrification of the two materials and electrostatic induction. So it's a very well-known principle that we normally do in the school. It's a small experiment, rubbing of two materials, and which has a positive charge and the negative charge, it attracts, right? The same that's the principle, the working principle of this device, energy harvester. So you need two materials, one is a positive charge, the other one is negative charge, and using that materials we can design and develop our nanogenerator. And the mechanisms and materials here you can see, one is a positive material, the other one is negative material, and the top two you have electrode which is connected together with across a load. And this is called the contact vertical contact and separation, which comes down and it goes up. So in one cycle, when it comes down, the charge difference occurs. So you'll get the first half cycle, and then when it goes back, the charge difference again it happens. So you'll get the negative half cycle. This is how the energy is generated in a triboelectric nanogenerator. So here the material plays a major role. So you need to select one material from extreme positive, the other material from extreme negative. So the combination of these two materials will help you to develop a high output or high performance nanogenerator. So this is a recent trend that is happening. So there are two trends basically. One is material aspect, the other is application aspect. So few researchers, they are trying to introduce new materials for this nanogenerator, for triboelectric nanogenerator. And the other majority of researchers, what they are doing is there are existing polymers and other materials which have negative and positive charges. So they try to understand the material, they identify that, and they use or they try to design a device for their particular application, for a specific application. So that's how the majority of researchers are working in this area now. So basically US and China are dominating in this particular research. And now in India, we start, there are few research groups, they are working in this area. So the energy conversion efficiency, as mentioned here, it is not, it's theoretically it is 85% it's shown. But the thing is, when you connect, I told that in the previous slides, it is a continuous, it is not a continuous or DC output. It is a pulsating or impulse AC output. So again, you need to convert this AC to DC, and it is not a continuous thing. So it is a pulsating, again the drop is A. So actually when you see the efficiency is less, but theoretically when you calculate, it comes around 85%. So this is how the research trend happening. Now let's see few research works that is that we did in our lab from 2015. So this we started in 2013 around this work, and then it got published in 2016 in ACS Applied Material Interface. So the work is named as Human Interactive Triboelectric Nanogenerator as a Self-Powered Smart Seed. So as I told earlier, we use one polymer material which is called Kapton, which is having a highly negative charge. And then we need an electrode material. So we used the laser cutted IDT structure PET sheet coated with aluminium as an electrode. And then we attach that together. And then here it works as a single electrode mode. I told the 4 electrodes, right? In that, this device works as a single electrode mode. And here you can see the same image that before treating this Kapton sheet, before treating with plasma, and then after treatment. Why we are doing this treatment is the increase. We need to increase the surface. We need to make the surface rough so that the surface charge will get increased. And also in the later part of my work, what we did is we normally try to purge CF4, carbon chlorofluorocarbon CF4, so that the fluorine atom will deposit on top of this layer in this, so that increase the negative charge, so that actually contributes more for the energy generation. So here what we did is the interacting material here which we used is bus card, which is plastic, polyethylene, again plastic, and then jeans cloth and newspaper. When you see jeans cloth and newspaper, it comes in the positive end so that you get better output compared to the plastic material. And here the peak power which we obtained was around 6.45 microwatt. And then this device was obeying the Ohm's law, so we connected in parallel so that we increase the current that obtained from 4 device. So this is how we used. And then the next one is this is a self-powered application. I don't think the video is working. So here what we did is we connected 4 devices with a small logic circuit. So whenever the passenger occupies the seat, immediately the LED, the LCD display will lit up the seat number. So this is completely a battery-free operation. Only we need to connect all the device to a circuit and then to LED display. So we don't need any power source for this, external power source. And then a stop indicator where you can sit and stand. I mean, when you harvest the energy, when you do some biomechanical operation, especially in the bus, you sit and stand. So what happens if you want to stop the bus, you press, the energy that is stored in a small capacitor will discharge immediately and it will lit up a light. And the bus driver, in the abroad, it happens like that. The bus driver will stop the bus. So the next work is like smart mobile pouch, where we introduce the wireless power transfer for this application. So the device which we used previously, we used here, but the only thing is there it was a single electrode and here it was a 2 electrode system. And we use a DBD plasma technique, dielectric barrier discharge plasma technique, to create this plasma, this roughness on the Kapton film. And then we did all the electrical analysis. We did voltage, current with the different materials, different contact materials, and we obtained around 1.3 milliwatt per meter square power density. And then the voltage and short. Here the device work in 2 modes. One is sliding mode, the other one is contact and separation mode. So 2 modes, this a single device in 2 mode operation. And stability was showing a better performance for the longer period of operation. So then we took into the next level where we tried to introduce 2 antennas to receive, receiver and transmitter antenna. Since it is an AC signal, so it is easy for us to couple with these 2 antennas. So the power transfer was good. So in 0 centimeter, like around 0.1 centimeter, we are obtaining around 78.4% efficiency of the power transfer from one antenna to the other antenna, or for one coil to the other coil. So this we tried to connect with, we proposed as a charging pouch, so that you can connect a power management circuit and then you can charge your mobile phone. So this was a third work which we actually started. So here what happened is we started developing a new technique to develop the pattern, pattern on the polymer film. Especially here we used a PDMS film. So what we did is we collected the lab waste petri dish, plastic petri dish, which is reactive with, it's a ABS plastic petri dish which reacts with acetone. So we collected that petri dish and then we treated with acetone in different time periods, so that it made the physical roughness on the petri dish, so that we can use that for making our own structures on the PDMS film as a mold. So then we poured PDMS film, 10:1 ratio of PDMS film, and then we made a PDMS liquid and made film. And then we used that film to make other devices, same contact and separation based Teng devices, and we obtained a good voltage around 120 volts and around 5 to 6 microampere of current was obtained in this particular application. So we propose this for a bag where you can attach the device in the backpack, I mean in the school bag or backpack, so that we can harvest the energy when you do your routine activity. And the most interesting work that which we did is, it looks simple, but it's more interesting, and it attracted a lot of researchers across the globe. So the one is called battery-free electronic smart toy. It's actually focusing on commercializing the triboelectric nanogenerator. So here we have a video. I don't think we have much time to play that. You can check in YouTube stating the same battery-free electronic smart toy you'll get. So what we did is we took the film which we fabricated previous. We developed 3 different toys. The one is like contact and separation based puzzle, where we made a figure to cut into 6 pieces, and we made 6 different devices in different position. So whenever this piece is exactly in contact with that position or that device, it will give an output as C. So what happened? So you don't need any battery source to make this electronic gadget to work. Your contact and separation itself will make the device work. So that's a concept here. And then here in this duct, we dissected and we attached a contact and separation based ring device, so that whenever you squeeze the duct, the LED will glow. We did the real experiment as requested by the reviewer, and we got the copyrights from the parents and the institution, right? So it was a tedious process. So here the kids were also playing with this device with the light. I mean with the nanogenerator toy. So then the next one was clapping toy. So that also the same principle, battery-free thing. Here we connected LED in this eyes and ears of this toy. And then this was claimed as a world's first triboelectric nanogenerator-based battery-free toys in various news articles. And the next important work we did was simple, and it's called Human Machine Interactive Triboelectric Nanogenerator as a smart computer mouse. So in the mouse we attached a nanogenerator here, sliding mode, IDT structure. So when you move your mouse, we harvest the energy, and it is stored in a lithium-ion battery. Here you can see the electrical output, which is over a period of 20,000.
Excuse me, sir.
Yeah, yes, ma'am.
So, can you conclude?
Yeah, 2 minutes. Yeah. Yeah. So this is another work which we done, and the other one was to overcome the drawback of this the water, like since you see all the triboelectric nanogenerator is open, it has a air gap between the electrode. So what we did is we tried to make a fully packed tank device, so that we can resist the water, the dust, or in moisture. So all these things. So in that aspect, we developed this humidity resistor, or the fully packed nanogenerator, and we use that for a smart Morse code generator application. So the next one was the blue energy harvester, where we develop a cone-type tank device, and it was used for harvesting the wave energy, water wave energy. And then the application was connected to a fishing net. It was a sponsored project, so we wanted for this particular application. So we can identify it is connected through Bluetooth to your mobile phone, and we can control, or we can trigger the light. And this is an advanced version of the previous work, where we had a hybrid device where you have a 10 EMG and in top solar. So this is a bigger version of this work. The previous, we call it as second generation work for us. And here we used a communication device called LoRa, so which can communicate for the longer distance. We created the app was provided by a company, so we can able to track the position of this buoy when it was floating in the sea. So this is a real images which we done during the experiment, and it's a small work. This is the last work which we for this slide. So for harvesting the vibration, so here we recycle the plastic waste materials, and then we develop a eye-shaped tank device which can harvest the biomechanical energy. And the major application here we used for sensing the tire movement. So in the last, as I told, that material aspect also we are working. So we work with the metal oxide framework for triboelectric nanogenerator and edible tang. Completely the materials are edible for tang. So this is the roadmap, and by 2027 we are trying to achieve the commercialization. So these are few of our collaborators. I would like to thank all my collaborators for this work, and these are few of our cover pages. And this is my PhD and postdoc lab, Professor Sanjay Kim. I'd like to thank him, and also VIT for giving me all this opportunity here to work and do the research. And especially my PhD scholars who are doing research now, research under me. So these are all the few research area that which we are working. So thank you.
Thank you, sir. Very interesting talk.
Yeah.
So now I would like to invite questions. If anybody wants to ask questions from Dr. Arun. I think no questions.
Elaborated on the future
Dr. Arun.
of triboelectricity. What is the future? There are lots of work in this direction is taking place in different parts of the world. What do you think? What about the future of this piece of electricity?
Sir, thank you. Thank you. I got a question from you. So actually, piezoelectric is well known now. It's almost, we know the lead-based materials are there in the market. But now the researchers are focusing on lead-free materials like bismuth, titanium, BITO, zinc oxide, and doping of neodymium. So that's in the picture for various sensors. When you come to the triboelectric nanogenerator, if we are overcoming the issues of this wear and tear and environmental issue, then definitely we can commercialize. You see in my slide that the smart toy, which is already published in the US patent, but still in the process. So the thing is, if it is a short term, that is a key factor. If you are thinking for a short term use, for a kid, for a child, they are going to play with this device for a maximum 3 months or 6 months. So after that, they are going to discard. So if you are actually thinking of like these kind of short-term use application, then definitely we can achieve commercial product in this particular technology. Not considering for a long term. If you consider as a sensor or a small scale or immediate consumption of energy or something like that kind of application.
It will be possible. Okay, very good.
Yes.
Thank you, sir.
Yes, thank you, Dr. Arun, for very interesting presentation. So that was the last presentation of this session. Thank you, Dr. Sabu Thomas and organizing team for providing me the opportunity for chairing the session. Thank you.
Okay, let's wind up the section energy. Thank you, Dr. Raki, for nice chairing the section. Thank you, ma'am. Let's move on to the next section, environmental remediation. I would like to invite Dr. Anand D. Kulkarni for chairing the section, who is from Department of Polymer Science, Somaya Vidya Vihar University, India. And sir, for your kind information, the speaker IL54 is shifted to tomorrow. So we have only one speaker in this section, IL55.
Okay. Thank you, everyone. Thank you, organizers. Thank you, Professor Sabu Thomas, sir, for giving me this opportunity to chair this session. It's a nice platform that we have got to present the work. We can interact, having wrangling interaction with the experts from all over the world at one venture. So let me take the opportunity to invite Dr. R.G. Ravaiya from C.V. Raman Nagar, Bangalore, India. The title of the talk is Studies on Bond Strengths of Polyurethane Coated Nylon Fabric Bonded Samples at Various Environmental Conditions. Please. Are you there?
Yes, sir.
Yes.
Sir, respected chairman session, Professor Sabu Thomas and conference organizers, a very good afternoon to all of you.
I am just going to present now.
Please.
Sir, is my presentation visible?
No. You can share the screen.
Yes, sir. Sir, can you see it now?
No.
One minute, sir. I think sir, I think there is some problem. I am unable to share. 1 minute, sir. I'll just do it once again.
It seems Dr. Ravaya is having some problem. Let's wait for a couple of minutes.
Dr. Ravaya, can you hear me?
He has left us, sir.
Oh.
So it seems he is having some technical problem. Let's wait for him.
Shall we wait for him for 2 minutes? Then we can contact him by phone.
Yeah.
Sir, sorry, I just got disconnected for there was some technical.
Yeah, please go ahead.
No problem, Dr. Ravaya. You can try sharing your screen.
Sir, now it is visible, sir.
No, you can stop sharing first. Yes. No.
Yes.
Yes.
I think it's coming.
It's coming.
Yes, perfect.
Yes, sir. I'll go to full slide mode, sir.
Yeah, please.
Sir, full slide mode is. Can you see my presentation, sir, in full slide mode?
Yes, we can see, but since there is something tricky, please go ahead. I think it's.
Sir, I am changing one slide. Can you see the second slide now?
Yes, we can see.
Yes, sir, I can see. Yeah, we can see.
Yes, sir. Sir, good afternoon to everybody once again. I'm really sorry for the inconvenience. There was some technical problem with the laptop here. Sir, this presentation is basically one of the case studies that we took up for one military research. And the title of the topic is, studies on the bond strength of polyurethane coated nylon fabric bonded samples. They were bonded with heat welding at various environmental conditions. Just to give a preamble, our military works in several war theaters, and Indian Army is man-force intensive, and it is second largest in the world with 1.4 million people on the board. And they have to operate, they have to safeguard our country in most of the hostile environment. And some of the hostile environments are in a high altitude, where temperature can plummet down to minus 40 degrees centigrade, and the desert, where temperature can go up to plus 55 degrees centigrade, swamps, NBC environment, which is man-made environment, wherein people have to operate wearing thermally restrictive protective suits. And then deep sea operations are there, where people have to work inside a cocooned environment, inside a submarine, where they don't have to, they cannot take bath for about 45 days during their operation. And then there are other war theaters like hot and humid jungles, low intensity conflicts, for example, a terrorist activity, or some seas that can take place somewhere near the border or elsewhere, and then surgical strikes. And then apart from these, the aerospace presents its own problems for our soldiers, because military flying is one of the most hazardous exercises compared to the commercial flying that we do in our day-to-day general life. And for all these hostile environments, soldier is a common denominator. And the first layer of the protection for the soldier is the clothing. And sir, I'm changing the slide. Please let me know if you don't see the slide changes. Hello, sir, can you hear me? Hello? Hello?
Yes, we can hear you. Yes.
Yes, sir. Yes, sir. Sir, this is just an introduction. As you know, in the previous slide, we noticed that modern militaries live and operate in the hostile environment. They have to protect the country, staying there for extended tenures. And in the Indian Army context, it's about 2 years to 3 years. And if you take up higher altitudes like Siachen Glacier, people have to put up 90 days operational tenure at minus 55 degrees centigrade, which is covered in snow, where UV index is very high and atmosphere is very, very thin. And in these conditions, they can get into a lot of problems. And to get over those problems, they have to wear certain military gears and ensembles and the equipments, which are generally made using coated technical textiles. Technical textiles are the requirement of the day, as they are used in all life-saving equipment, because commodity textile is only for normal civilian usage. Technical textiles are intended for performance-based characteristics. And some of the examples wherein technical textiles used are one-man HAPO chamber, the one which is on the right hand orange-colored fabric bag, which protects soldiers who are suffering from high-altitude pulmonary edema. Because of the higher altitude, the barometric pressure drops, and then the people get into a condition known as pulmonary edema that happens at high altitude. And then if somebody is suffering from HAPO, which is abbreviated as HAPO, the person has to be immediately admitted to a hospital. But then at high altitude, there are no hospitals present, in the near proximity. So they have to be treated on site. So we have one life-saving equipment. So that is known as high altitude pulmonary edema chamber, which creates virtual descent. If somebody is at Kardungla top, which is at about 18,380 feet altitude, and if the HAPO patient is put inside this bag is going to be pressurized to 130 millimeter of mercury. So at Kardungla top, the barometric pressure is about 380 millimeter of mercury compared to 760 millimeter of mercury at the sea level. So if you are going to add another 130 millimeter of mercury pressure onto this bag, it will add up to that altitude, and it creates about 6,000 to 8,000 feet of virtual descent. And this particular
life-saving equipment is made up of coated fabric. So fabrics are very important in any military activity when a man behind the machine is considered. And military flying, as I told, it's very hazardous because of certain problems like G forces. When a fighter aircraft goes in very high speed in vertical direction, G forces act in other direction. As a result, blood gets pooled on the lower part of the body. As a result, the heart will not be able to pump blood to the brain. This leads to two conditions. One is known as graying out, in which a pilot loses his color vision, and if the situation continues for another 2-3 seconds, he'll get into something known as blackout, wherein he completely loses his consciousness. Just imagine a fighter pilot flying an fighter aircraft at about 1,000 kilometers per hour. If he loses his consciousness for about 2 seconds, so what are the kind of problems he can get into, and what about the mission failure? So these are all the things that we have to consider whenever we put a pilot on board a fighter aircraft. And to alleviate such kind of problems, we use something known as anti-G suit. So what it basically does is, this is a pilot clothing which you can see on the right hand side. So what it does is, basically it senses the G forces that are acting on the body of the pilot, and it pressurizes certain portions of the body like abdomen, the posterior portion, inner calves, and all those things, so that blood is not pulled into the bottom surface, that is towards the legs. So there is one more thing, like AILJ, automatic inflatable life jacket. Suppose a pilot is flying a seabound sortie. If he gets hit by a missile, or if there is some technical snag, so pilots are generally asked to eject from the aircraft if there is any threat to their life, because the pilot's life is very crucial compared to a replaceable military aircraft. And if he ejects, ejection is one of the very hazardous phenomenon. If he ejects and if he is not conscious during ejection process, he may fall on a water body unconscious. So even if he ejects and falls unconscious on a water body, he may drown into the sea. So to avoid that particular thing, we give something known as an AILJ, automatic inflatable life jacket, which is there just around this neck. And it the moment the pilots hit the water, this particular AILJ gets inflated. It gives about 18 kg buoyancy. As a result, pilot stays afloat. All these things can happen, but what if he falls on shark infested water? That is one of the questions, because he may eject, he may fall safe on water body. The AILJ may keep him afloat, but if he is if he is in the shark infested water body, so he'll get attacked by sharks. So we have to give him shark repellent also. So these are all the things that we have to look at. So this particular branch of military research is called life sciences research, which takes care of the man behind the machine, because man behind the machine is one of the most critical and important entity in any war field. So I'm just giving one particular video here, so which delineates the military flying hazards. So this particular system is called the centrifuge, wherein you can see the pilot sitting on the left side, and G forces are depicted here. The present I'll play this video. As the pilot goes through G forces in a simulation chamber, you can see his jaws drop, even eye sockets fall down, and he'll become unconscious. I'll just play this video. Just you can see, just keep an eye on this particular G, which is number which is coming up. You can see here his eyes are dropping, stooping down, and even jaws are dropping. As G forces reverse, so he'll become all right. Now it is G is around 1.8. He has become normal. And in this particular pilot, you can see he becomes unconscious. He won't be able to pull even 7G. So maximum is 6.07 G. He becomes unconscious. It is known as G-induced loss of consciousness, or known as G-lock in a military, as a military term. And this particular device, which is rated as life critical as well as mission critical, is used to combat this kind of hazards that are part of military flying. So this G suit comprises of coated fabric, and a single fabric is never useful in any military, in any for any ensemble. It has to be bonded to make a defined geometry, so that it gives protection. So as I mentioned earlier, technical textiles are only used as protective devices, and all military inflatables are subjected to rapid inflation and deflation. If I take the example of our G suit, So there is a sensor that senses G-force, because these military activities happen very fast. So there has to be rapid deflation and inflation. As a result, any military inflatable that is made up of using coated fabric has to undergo stringent qualification testing as per the MIL standard, DEF standard RJSS Penta 5, which is coined by Indian military, which is also known as Joint Services Specification. So which are very, very stringent in nature, and they have to withstand very high pressure. To give an example, our G suit, anti-G suit, which is developed by our lab, has to withstand 10 bar pressure, and it is made up of bonded fabric. The bonding can happen either through adhesive or heat welding or through RF welding also, and it has to qualify 10,000 cycles. Only then it becomes a qualifying set. Then only the subsequent manufacturing can take place, and all these things have to perform. All these things generally are used in extreme climatic condition. As I mentioned earlier in the very first slide, in the war theaters, we have got an extreme cold, extreme hot, humid, and this kind of environments. So these fabrics not only have to qualify for the bonding strength, they also have to qualify for extreme temperature durability also, because a pilot taking off from desert area, say for example from Jaipur or Jodhpur, he may land in Leh, where temperature can be minus 20 degree also, and his suit is subjected to that differential temperature. Delta T is very high. Even when the pilot ejects at about say 11-kilometer altitude, where temperature can be minus 55 degrees centigrade from a conditioned cockpit, the fabric, the life saving device faces extreme delta T over there, extreme temperature. As a result, there was a requirement for us to study what happens to the adhesion strength when these fabrics are exposed to extreme temperature in just few hours time or few minutes time. We made use of something known as cyclic testers, wherein the fabrics are dropped into extreme hot and extreme cold temperature chambers, and then the studies were evaluated. In this particular topic, I am going to cover the bonding strength evaluation that we carried out using UTM, Universal Testing Machine, also on ball burst and diaphragm test. But in general scenario, what happens in general research and development scenario, we carry out all these evaluation at room temperature and we qualify. But for military, it is not so. For anything that goes into military, this is not so. They have to be evaluated at various temperatures and relative humidity conditions. And bond strength determination in operational environment is important only because of these kind of requirements. And tensile strengths were carried out using a jacketed UTM at minus 40 degree, minus 20 degree, plus 25 degree with 35% relative humidity, and at plus 40 degree at about 80% relative humidity. And the objectives of studies were to choose a base fabric, which is 120 GSM nylon. GSM is in grams per square meter. If you take one meter square of fabric, it will weigh about 120 grams. Then we coated this fabric with polyurethane, which is based on TDI. And the overall weight of the coated fabric, including the base fabric, became 200 GSM. And we carried out tensile strength at respective operation conditions. We chose 4 different conditions: plus 40 to minus 40 room temperature and minus 20 degrees centigrade. And we also subjected these fabric samples for ball burst analysis, because these are basically inflatables, which are used as inflatables. And we wanted to correlate the relationship between the bond strength and the bond width. Higher the bond width means higher bond strength. That's what we wanted to study. And what is the relationship between bond width and the burst strength whenever the fabric rupture takes place? So that also we wanted to study. And the relationship between temperature, humidity, and the bond strength. So these were very, very important for our thing. And this is one of our experimental setup. So wherein we carried out tensile strength evaluation. For this study, we prepared about 20 samples having these bond width starting from 5 mm to up 5 mm up to 60 mm with an increment of 5 mm. We prepared about 240 samples using special dye, and they were prepared using heat welding at about 35 kilowatts of energy. And the samples are subjected to this particular UTM, which is jacketed, and we had these kind of temperature simulated in this particular jacket. And you can see how exactly this takes place. This video will tell us how the rupture takes place. We used Bureau of Indian Standard 1969 method, and sometimes one thread also holds the fabric, so we'll get different results. And the results are presented in this particular curve, So wherein we have taken load on the y-axis and stress on the x-axis. And some of the variations you can see here, they are because of one or two threads remaining to the fabric. And these are all the experiments that were taken at minus 40 degrees centigrade. So different bond widths are provided at the top of the each fabric core here. And these were the experiments that were conducted at minus 20 degrees centigrade, plus 25 degrees centigrade at 35% relative humidity, plus 40 degrees centigrade at 80% humidity. Sorry, there is a mistake here, typographical mistake. It was 80% humidity over here. And you can see here, we observed two types of ruptures in this particular bonded fabric. One was rupture near the bonded surface. Other one, totally peeling off. The bond came out very easily. And we observed this kind of peeling in case of smaller bond width, say 5 to 10 millimeter of bond width. We observed peeling. And in some cases where higher bond widths were envisaged, so there we had tear exactly at where the fabrics were bonded. So this gave us an insight that as the bonding width increases, the strength of the fabric, the strength of the fabric is less compared to the strength of the bond. And when the bonding width is less, the fabric strength becomes higher compared to the bonding width. And this is one of the experimental photograph which is displayed here. We can see everywhere the bonding rupture is taking place only at exactly where the bonding has taken place. And optimal bond width that is required, we found out in our experiments. So we needed about 550 newtons of load. It should not break at that particular load, and we found out that thing. And you can see the anomaly at low temperature. Bonding decreases, bonding strength decreases at low temperature. As we increase the temperature, it becomes linear. So this was one of the outcomes that we got from our experimental evidences. And we have these observations. The results in the previous slides clearly indicate the variation in bond strength of the same width at different temperature and RH are totally different. And bond width, generally it is assumed as we increase the bond width, so there is a proportional increase in the bond strength also. It is not so. And it was also observed higher bond widths exhibited in lower strengths in some cases, which indicates the rupture is a key factor. The initiation of the rupture is a key factor. Higher bond widths do not linearly translate to higher strength. That is one of the outcome of this particular study. And then subsequently, we expose these fabrics to ball burst analysis, wherein the fabric samples were exposed to this particular test as per ISO standard 3303/1, and they all qualified at higher temperature. That means the strength of the fabric remains higher at higher temperature. So this gives us a conclusion that when we consider a military inflatable, when we have to go for life estimation, which can be service life or shelf life, we have to take different temperatures into consideration, and we have to do the derating. So derating is suppose it rates for about say some number at room temperature. At extreme temperature, it has to be derated so that the life estimation of the product is near optimal. So these are some of our studies, and these are the conclusions from our case study of this particular thing. Thank you so much. Jai Hind.
Thank you, Dr. Rohia. The session is, we are open for the questions. Any questions?
Sir, thank you, sir, for your wonderful presentation.
Thank you, ma'am.
I have one doubt. Is this PU clothing safe? I mean, any toxicity?
No, ma'am. Actually, in military scenario, we have to. Military research is very complex in nature. Let me give just one example. Whenever we consider military flying, so we also have to consider the flying hazards, because if there is some fire, so PU burns vigorously. It also drips, so it causes third-degree burns instantaneously. So even flame retardancy is also very, very important. In this particular case study, we took PU because PU has an extreme low temperature durability. But generally for military, we go for neoprene coated fabrics because neoprene has some chlorine content in it up to 35%. That will give some flame resistance. So as I mentioned earlier, military research is very, very complex. You have to consider several things into consideration, and then only come out with the most optimal solution, ma'am. PU as of now is not toxic because PU polyurethane things we use generally in our generic life.
Okay, thank you, sir.
Thank you, ma'am.
Thank you, Dr. Ravaya. Thank you, organizer.
I have one question, Doctor.
Yes, sir.
Yes. Have you tested any flame-resistant, flame-retardant properties of the textiles after the fabrication?
Yes, sir. Actually, this is one just sample I gave example. We do have several fabrics like instead of going for nylon, which is not flame retardant in nature, we can go for that pararamid, that is Kevlar, and then we can give, because Kevlar cannot be used as a coated as a impervious impervious ensemble, because it is fabric and it has got pores. We have to close those pores and we have to go for coating. So you can choose neoprene as your coating, because neoprene has chlorine and it has got some flame resistance, and you can even go for hypalon. Hypalon is chlorosulfonated polyethylene. You can go for those also. So wherever you don't anticipate flame threats, you can go for polyurethane, because it is extremely good as far as low temperature durability is concerned. You can give these particular things for those scenarios where you don't expect a lot of fire threat. And other alternate flame resistant coats are neoprene and hypalon.
Okay, understand, Dr. Ravi. I have one more question. Like polyurethane is also efficient for the shape memory. It is also a shape memory polymer. So have you tried like that? Because I am also working on polyurethane shape memory textiles.
Yeah,
So
shape memory for
yeah.
textile is not required in this particular case. In fact, it should not. It should not. We should not use shape memory fabric over here, because there are rapid inflations and deflations, and then depending upon the G, the inflation can be very high and it can be low also. So if you get into shape memory, then there is always some kind of equilibration between the actual size and its own memory. So that may lead to some kind of inadequate G protection in this particular case. But then of course there are other examples where shape memory articles are very, very useful. There we can use. As of now, we have not studied shape memory effect of this particular ensemble.
Clear, Dr. Revia. And it was very wonderful work and very nice presentation. Thank you for the presentation.
Thank you, sir.
Thank you, Dr. Ravaya. Yes, comments from the seminar host. Or shall we end the session?
Yes, if there are no more questions from the audience, we can wind up the session.
Okay, let me thank you all for gathering here, and the speaker, the participants, everyone. Thank you.
Thank you.
I think.
Yeah, I would also like to thank Dr. Anand T. Kulkarni, Department of Polymer Science, Saumya Vidya Vihar University, India, for wonderfully chairing the session.
Thank you.
Thank you, sir.
Thank you. So we'll have a break, and then the next session will start at 2 o'clock, right?
Yes, yes. Yes, we have to organize some lectures. So I request everyone to please be online for 2 minutes.
Yeah.
Okay. Thank you all.
Thank you.
Dear all, we will have a short break for 15 minutes. So we will gather here back at 2 o'clock Indian time. So I request everyone to have a small break and please come and join.
This is
Uh,
Professor Napoleon.
yes, Professor. Yes, Professor, please.
I'm chairing the session, right?
Yes.
Okay. So I will join at 2, huh?
Sir, 1 minute, sir.
Is it my call number 1, right?
Yes, sir. Yes. So, 2 o'clock we can meet again.
Yes, okay, I will join. Huh? Thank you.
Thank you.
Good afternoon, all. Let us start this plenary session. I welcome Professor B. Napoleon from SRM Institute of Science and Technology to chair this session. Sir, please.
Good afternoon, madam.
Good afternoon, sir.
Can I invite that speaker?
Yes, yes, sir, please.
Good afternoon, everybody. I'm going to invite the speaker of the session, hall number 1, and is Gabriela from Department of Chemical Engineering, Faculty of Chemical Engineering and Environmental Protection from Technical University, Romania. The title of her talk is Unique Nano Architectronics of Gold Nanoparticles, Layered double hydroxide heterostructure for facilitating the controlled release of nanoparticles of gold. May I invite Gabriela to deliver her talk. It's for 30 minutes. It's a plenary talk. So hope everybody will enjoy. Please.
Hello, everyone. So please allow me to connect again because I cannot open my camera now. Do you hear me?
Yes, very much. Okay, please proceed.
Okay, let's I cannot load my presentation and I cannot open my camera. Sorry. I will try again.
ലെഫ്റ്റ് ആയി ഒന്നുകൂടി ജോയിൻ ചെയ്യാന്ന് പറഞ്ഞു.
on the and then come back to Professor, I think Professor Gabriela has some issues with her connectivity.
Hello?
So shall we move on to the next speaker?
Dr. Gabriela?
Yes, after, can you please call the PL virtual now?
Next one, huh?
Yes, yes, sir.
Okay, I will call. So, may I know Iraya?
Yes, yes, Professor.
Is he available? I think. Hello? Is he available here?
Professor Ilaria?
Yes. Oh, Ilaria. Okay.
Yes, I'm here.
Okay. So he is from Italy, Department of Biomedical Science and Technology Group, University of Rome, Italy. The title of our talk is Multifunctional Nanostructure Platform for Regenerative Medicine, a Biomimetic Strategy. So now may I invite Dr. Ilaria to present her talk for 30 minutes. It's a plenary talk. Thank you.
Thank
Please
you.
go ahead.
Can you
Thank
see my screen?
Yeah, no. Kindly
No.
share your PPT.
Can you see my screen?
No, not yet. Please
Not
share the
yet.
screen.
Okay. Now imaging, yes. Now can you see it?
Yes.
Perfect. Thank you for your
Image is on
presentation.
the slideshow. Okay.
Okay.
Please proceed.
Perfect. Thank you another time for your presentation. As you told, I'm Ilaria Cacciotti from University of Rome, Niccolò Cusano, Engineering Department. First of all, I would like to acknowledge all the organizers of this very interesting conference, mainly Professor Thomas, for the invitation to join this conference with this plenary speech. Today, in my presentation, firstly, I will briefly introduce you the regenerative medicine, the scaffold concept. Then I'll show you some of our results in this field, and at the end, some concluding remarks. So, what is regenerative medicine? Imagine that you know, but just only as a brief introduction, it consists in an interdisciplinary field with the application of the knowledge from several sectors: bioengineering, medicine, chemical engineering, material science, nanotechnology, and so on. In the regenerative medicine, it's possible to identify four main sectors: tissue engineering, biomedical engineering, cell therapy, genetic therapy. Among them, the tissue engineering is gaining a lot of interest. As you can see from the reported definition, it consists in an interdisciplinary field that applies the knowledge of engineering, of the life science, towards the development of biological substitutes in order to restore, maintain, improve the functionalities of damaged tissue and organs with two different approaches, ex vivo and in vivo, that you can see in the reported schematization. What is the main goal of tissue engineering? To overcome the limits associated to the organ transplantation, such as the need for several surgeries, the high hospital cost, the limited availability of donor tissue, the pain, infection, hematoma in the donor site, the risk of infection, disease, rejection in the case of allograft. How it's possible to achieve this ambitious aim? By the combination of different approaches, including the use of growth factor, biomaterials, and cells. In fact, in the tissue engineering, it's possible to identify three main ingredients, three main components: cells, bioactive molecules, and the scaffold that have to interact each other in order to achieve its aim. In particular, the scaffold plays a pivotal role. What is a scaffold? A scaffold consists in a support for cell seeding, cell adhesion, cell proliferation, differentiation towards specific cell phenotype in the case of staminal cells, deposition of extracellular matrix, tissue ingraft, neovascularization. An ideal scaffold has to satisfy a lot of requirements. It has to be characterized by suitable mechanical properties compatible with those of the tissue to be regenerated, sterilizability. It has to be composed composed of biocompatible, bioactive, bioresorbable material. It has to be characterized by a hierarchical porosity. As you can see from this table, it has to be characterized by very, very small porosity in order to interact with proteins, with nutrients, with oxygen, but also big porosity for the colonization of the scaffold by cells. Moreover, it has to be characterized by suitable resorbability times, since it has to be resorbed simultaneously with the deposition and the formation of the new tissue. So, on the basis of all this consideration, it's evident that in the design of an appropriate scaffold, it's important to take simultaneously into account several concomitant factors in terms of composition, microstructure, mechanical properties, surface properties, as well as biological requirements related to the surface properties, since the interaction between materials and cells is pivotal in the tissue engineering approach, and it can occur at different levels, at nano with molecules, micro with cells, macro with tissue, mega with organs and organisms. In the design of materials for tissue engineering, in fact, the comprehension of the mechanism underneath this interaction is fundamental. In this context, the mechanotransduction consists in the conversion of a mechanical stimulus from the surface of the support on which cells are seated into electrochemical and biochemical response by cells, including the secretion of specific substances, the cell growth, the genetic expression, the differentiation towards a specific cell phenotype, for example, neurogenic, myogenic, osteogenic. So the stiffness of the support on which the cells are seated is able to determine their destiny towards a specific cell phenotype. So we can tell that in the design of an appropriate scaffold, in order to obtain an optimal material-cell interaction and the optimal performances, it's possible to follow two main approaches. A first approach, the biomimetic approach, consists in the formulation of bioinspired materials. As you can understand from this definition, the bioinspired materials are materials able to resemble, to simulate the composition and microstructure of the tissue to be regenerated. Otherwise, it's possible to produce multifunctional materials, materials characterized by several functionalities, for example, antimicrobial properties, antioxidant one, and so on. So, following the biomimetic approach, for example, in the case of the bone tissue, regarding the structure, the bone tissue is characterized by a hierarchical structure, as you can see from this reported schematization, at nano, micro, and macro scale. In fact, at nano scale, the bone tissue consists in a composite material. It is composed by hydroxyapatite nanocrystal organized with collagen fibers. So, it's very important at the nano scale to simulate the chemical composition in order to obtain biocompatibility and biodegradability. At the micro scale, it is organized in lamella and in osteon, so it's very important to simulate the porosity in order to promote the cellular infiltration and vascularization. At the macro scale, the bone tissue is organized in spongeous bone and cortical bone. It's very important to resemble the mechanical strength and the geometry. As I told you before, the bone tissue, regarding the composition, consists in a composite material. In fact, its extracellular matrix is composed of an organic component, collagen fibers, and organic one, apatite. The apatite does not consist in a stoichiometric apatite that is characterized by a calcium phosphorus atomic ratio of 1.667, as you can see from the reported chemical formula, with the presence within the lattice of a calcium phosphate hydroxyl, but the biological apatite consists in substituted apatite with the presence within the structure and within the lattice of several vicarious ions in the three main sites, the calcium site, the phosphate site, and hydroxyl site. For example, we can have as vicarious ions in the calcium site, strontium, barium, sodium, potassium, and so on. In the phosphate site, carbonate, silicate. In the hydroxyl site, fluorine, chlorine, carbonate, and so on. So the biological apatite are calcium deficient with a calcium phosphorus atomic ratio less than 1.667. following the biomimetic approach, so it's evident that it's fundamental to synthesize substituted calcium phosphate in order to obtain improved bioactivity, biological performance, enhanced bone apposition, bone ingrowth, and cell-mediated degradation. Moreover, very recently, bioactive glass and glass ceramics material have been proposed as a promising alternative to the commonly and widely used calcium phosphate, since these materials are characterized by biocompatibility, high bioactivity, the bond capability not only to hard tissue but also to soft tissue, improved mechanical properties, and the ability to induce angiogenesis. Moreover, as you can see from this reported schematization, the surface of bioactive glass materials is able to continuously exchange the ions present within the structure with the ions present within the physiological fluids. So the bioactive glass materials can be considered as a carrier for the control release of ions with therapeutical functionalities, for example, zinc, iron, strontium, magnesium, and so on. And you can see in this table different ions with the related biological activity. Moreover, these materials are able, through the release of the ions within the structure, to induce the differentiation of specific genes involved in the bone metabolism, as you can see from the table. Regarding our experience related to the production of a biomimetic system, we set up a specific synthesis procedure for the calcium phosphate pure and substituted by precipitation from calcium nitrate and titration from calcium hydroxide, producing hydroxyapatite, tricalcium phosphate, and also biphasic calcium phosphate that consists in the co-presence of hydroxyapatite and tricalcium phosphate. Moreover, we produced not only pure calcium phosphate, but also mono, B, and 3 substituted ones. Regarding the bioactive glass and glass ceramics materials, we set up a sol gel process. We propose the sol gel process as a promising alternative to the traditional melting procedure for the synthesis of glass ceramics materials, since this kind of approach presents a lot of advantages, allowing to produce materials at a low process temperature, to obtain powder with high purity in a wide range of composition and also in different shape, fiber, film, gels, glass, aerogel, and so on. We produced by sol gel process for the first time the composition 45S5, the Hench composition, the first composition introduced as bioglass, and later our idea was to introduce within the lattice, within the structure of these glass ceramics materials, several vicarious ions with specific biological functionalities, for example, fluorine, magnesium, tantalum, zinc, and so on, obtaining a more complex structure. So the produced substituted calcium phosphate and bioglasses were used for several applications, for the production of coatings on polymeric and metallic support, on ceramic porous scaffold, and also as fillers in nanocomposite system based on polymeric matrix. First of all, regarding the production of coatings based on calcium phosphate and bioactive glasses, as you know, usually prosthesis implants for orthopedic and dental applications are composed of titanium. Titanium is a biocompatible material, but is not bioactive. So in order to promote the osseointegration of titanium-based implants, it's possible to follow two different strategies. A first one based on the improvement of the surface roughness of titanium by a suitable surface treatment, such as thermal plasma spraying, treatment with acid, or to cover the titanium with bioactive material, for example, calcium phosphate and bioactive glasses, using different kinds of procedure, for example, sol gel approach or pulse laser deposition. So, in order to demonstrate the capability of the deposit of the coating on the surface of a titanium implant, we carried out in vitro bioactivity test in cell medium, since assign an index of the bioactivity of a material consists in the formation of a calcium phosphate layer on the surface of the materials by dipping in a cell medium or SBF simulated body fluid. So, in the case of uncoated titanium substrate, we did not observe the deposition of calcium phosphate layer after 28 days of dipping within this culture medium, but just only the precipitation of some sodium chloride crystals, suggesting the not by activity of these materials. In the case of hydroxyapatite coated titanium substrate, as you can see from the reported scanning electron microscope micrographs on your right, you can observe the deposition of the typical apatite layer, that is an index of bioactivity with typical apatite flakes and cauliflower shapes, just already after 1 day of dipping within the cell medium, with a progressive increase of the thickness of this layer during the days. Moreover, this result was confirmed by energy dispersion spectroscopy microanalysis, identifying the phosphorus and calcium peaks typical of the apatite. As I told you before, we set up not only the coating procedure on a metallic support, but also on polymeric one in order to promote the osseointegration of a polymeric cranial implant in the context of two different projects, Cranima before and CISMAC in this moment, with the main aim to overcome the limits of the current polymeric cranial implants, such as the induction of inflammation, the lack of osseointegration, and the low mechanical properties. Particularly regarding the lack of integration, our strategy to overcome this limit and this criticism was to cover the produced scaffold, the produced implant with hydroxyapatite. So we set up a procedure starting from an hydroxyapatite precursor solution obtained by Sol-Gel method, and we demonstrated the obtainment of hydroxyapatite by Sol-Gel process by X-ray diffraction measurement. As you can see on your left, you can observe the typical diffraction peaks of a semicrystalline hydroxyapatite. This result was confirmed by infrared spectroscopy. As you can see from the reported infrared spectra on your right, we obtained the typical functional groups of hydroxyapatite. Moreover, as you can see from the reported SEM micrographs of dried hydroxyapatite, this powder was composed of rounded shaped particles with an average diameter of 40 nanometers. In order to demonstrate the efficiency of the setup procedure for the coating, we carried out some infrared spectroscopy analysis also on uncoated polymeric disc and coated one. As you can see from the infrared spectrum on your right, in the case of coated materials, we observe the co-presence of the typical functional groups of the considered polymeric material and of the hydroxyapatite, demonstrating the occurred deposition on the surface of the material. Moreover, the deposition of hydroxyapatite on the surface of the produced scaffold after dipping procedure was immediately evident macroscopically. As you can see from this reported picture, a clear change of color from white to yellow after the coating was evident. Moreover, this result was supported by weight measurement before and after the coating procedure with an increase of around 10%. Was also confirmed by observation at optical microscope and particularly by observation at the scanning electron microscope. As you can see from the reported SEM micrographs of uncoated sample and the coated one, in the case of the coated in the bottom, you can see a very homogeneous, uniform, defect-free, crack-free distribution and deposition of hydroxyapatite coating on the surface of polymeric material. Moreover, we carried out some cell tests with osteosarcoma in order to demonstrate the capability of the coating to improve the cell viability as well as the cell proliferation and the differentiation towards osteogenic phenotype. In the case of MTT test, we demonstrated the capability of the coated materials to increase the cell proliferation on hydroxyapatite coated samples. Moreover, in the case of differentiation test, we performed this differentiation test up to 16 days into different conditions. In basic medium, in the absence of the osteogenic factor, as well as in a medium additioned with osteogenic factor, an osteogenic medium. As you can see by laser in red test, it's possible to color in red the calcium released from the cells. That is an indication, an index of the differentiation of the mineralization. So in the case of coated coated samples, you can see the clear red color that was improved in the case of osteogenic medium, but it was interesting to observe the ability of the coated materials to induce the differentiation also in the absence of osteogenic factor. In all cases, we obtained both in basic and in osteogenic media an increase of the absorbance value related to the calcium release, suggesting an ability of the hydroxyapatite coating to improve to promote the differentiation, mainly in the case of osteogenic medium as expected. Regarding the bioinspired materials, also we were involved in the production of a porous scaffold, starting from a precipitated hydroxyapatite or substituted apatite powder that we mixed with a porogen agent, a sacrificial agent, polyethylene spheres, in order to obtain by uniaxial pressing the specific pellets to be submitted to a thermal treatment in order to obtain porous scaffold due to the elimination, the thermal removal of polyethylene spheres. In that cases, we demonstrated the capability of this scaffold to promote the differentiation towards osteoblastic and osteoclastic phenotype. In the case of the test with pre-osteoblast, after 21 days of differentiation, we observed the osteoblast, the differentiated cells on the surface of the materials by SEM. As you can see from the reported SEM micrographs, we obtained a very, very homogeneous layer of differentiated cells, very, very spread on the surface of material, suggesting a good interaction with the material, and also the occurred differentiation towards the osteoblastic phenotype was demonstrated by the presence of a mineralized bone calcification nodulus, also supported by alizarin red staining, as well as by the formation of the extracellular matrix. Moreover, as you know, the bone tissue consists in a dynamic tissue. In fact, this tissue is characterized by a balance between two processes, the bone formation by osteoblast and the bone resorption by osteoclast. So it's very important in the case of material to be used for a bone tissue engineering to demonstrate the capability not only to support the differentiation towards the osteoblastic phenotype, but also the capability to support the bioresorption by osteoclast. For this reason, we performed a cell test, differentiation test from a monocyte to osteoclast in 21 days, demonstrating the occurred differentiation by multinuclearity, actin ring, tartrate resistant basis phosphate staining test, and also by observation at SEM of the typical resorption pits due to the osteoclast action. So, by trap staining, we demonstrated the multinuclearity of the differentiated cells, that is an index of osteoclastic differentiation, and by observation at the scanning electron microscope, after 21 days of differentiation, we observed three different shapes of cells, rounded shape, elongated shape, as well as the typical spread shape, that is an indication of a good interaction between the cell and the material. At the end, we observe the surface of materials after the osteoclast removal by soda treatment in order to demonstrate the presence on the surface of the material of the typical resorption pits due to the osteoclastic action. Moreover, we produced, following the biomimetic approach, also nanocomposite fibers by electrospinning. In order to simulate the bone tissue composition, we use a polymeric matrix composed of different polyesters, for example, polylactic acid, polycaprolactone, polyhydroxyalkanoates, using different anorganic fillers, pure and substituted calcium phosphate. We used as technique to produce these fibers electrospinning, that is a low-cost, user-friendly technique that allows to obtain, to tailor the properties of the final fibers by monitoring the solution suspension properties and the process parameters, for example, the applied voltage, the flow rate, the needle target distance, and so on. As you can see from the comparison in the table, the electrospinning with respect to other techniques to obtain fibers present several advantages. The capability to be easily scaled up, to control the fiber dimension, to obtain long continuous nanofibers, and also fibers in a wide range of material. So why fibrous membranes can be seen as a promising scaffold materials? For several reasons. First of all, the fibrous structure will mimic the tissue extracellular matrix 1, as you can see from the reported macrograph. Moreover, the fibrous structure are able to encapsulate bioactive molecules, ensuring their control release. It can be used as support for the surface immobilization of specific bioactive molecules, enzymes, growth factor, drugs, and so on, due to their very high surface specific area. We produce biopolymeric calcium phosphate composite fibers using a polylactic acid or polycaprolactone as fillers, hydroxyapatite and tricalcium phosphate in different concentration. In all cases, we obtain randomly oriented fibers, homogeneous, defect-free, and it was interesting to demonstrate by calcium phosphate maps obtained by macroanalysis a very good dispersion of the fillers within the polymeric fibers in the case of lower concentration of fillers, whereas in the case of the higher concentration of hydroxyapatite or tricalcium phosphate, as expected, we obtained some agglomerates. In the case of polylactic acid-based composite fibers, we carried out cell tests with different staminal cells into different conditions, basic medium and osteogenic medium. In this case, we obtain a differentiation of all different kinds of staminal cells towards the osteogenic phenotype in the osteogenic medium in all cases for both NEAT, PLA, and PLA loaded with hydroxyapatite. Whereas in the case of basal medium, of the basal growth medium, in the absence of osteogenic factor, was possible to obtain the differentiation only in the case of the composite fibers. We ascribed this very interesting result not only to the different chemical composition, to the obvious presence of hydroxyapatite that is able to provide bioactivity and also conductivity, but also to a mechanotransduction phenomenon. As you can see from the reported mechanical properties in the data in the table, we obtain a decrease of the storage modulus, increasing the hydroxyapatite content. And so, as you can see from this schematization, we obtain a better stiffness of the materials, so a better interaction of cells with the materials due to the decreased storage modulus. Regarding the production, following the second approach, so regarding the production of a multifunctional system, as I told you before, in order to promote a good and optimal cell support interaction, it's very important to functionalize the surface. So, for example, we produce a ternary structure based as a polymeric matrix of polylactic acid with the addition of silver nanoparticles in order to provide antimicrobial properties and cellulose nanocrystal in order to provide mechanical reinforcement. In that case, we obtained very interesting honeycomb-like structure, in particular in the case of cellulose nanocrystal functionalized with a specific surfactant in order to promote this good dispersion within the fibers. Moreover, as I told you before, we functionalize the surface in order to promote a covalent bond with silver nanoparticles using a specific organosilane, il trimercaptopropyl triethoxysilane, in order to obtain a decoration of the fibers with the silver nanoparticles. As you can see from the reported STM micrographs, we were able to obtain the decoration with silver nanoparticles of the single fibers. Moreover, carrying out tensile tests, we demonstrated an increase of the ultimate tensile strength in the case of fibers loaded with silver nanoparticles or functionalized and decorated with silver nanoparticles. We performed antimicrobial tests against Escherichia coli. As you can see from the comparison among the different Escherichia coli growth cure, we obtain a complete inhibition of the Escherichia coli growth in the case of fibers decorated with silver nanoparticles. Moreover, in order to provide antimicrobial and antioxidant properties, our idea was also to use some agri-food waste fillers characterized by high availability and low cost, for example, in order to to propose eco-sustainable alternative for a smart and sustainable waste management in agreement with the circular economy and the zero waste standard division, so to give a new reuse of waste materials. For example, we are using extract from fruit waste, from coffee ground, from licorice, from garlic, and so on. As just only to show you an example, why did we decide to use garlic extract, why it's able to provide antimicrobial antioxidant properties. As you know, most of the beneficial properties associated to the garlic are ascribed to the presence of organosulfur compounds such as ION, allicin, the allyl disulfide. Since this kind of organosulfur compounds are able to provide antibacterial, antioxidant, anti-cancer properties, heart protection, due to their ability to produce and release sulfhydric acid. What is sulfhydric acid? Sulfhydric acid is one of the three natural gas transmitters, is able to avoid the free radical development, acting as a reducing element and to enhance specific enzymatic activities. We use different approach, the direct encapsulation of the garlic extract within the fibers or the surface immobilization by drop casting. Following the encapsulation approach, we obtain homogeneous, randomly oriented fibers, more rounded in the case.
Hello, Professor.
I'm going to the conclusion. In the case of the allyl disulfide loaded fibers with higher average size, and we obtain an increase of the mechanical properties in the case of fibers loaded with organosulfur compounds. Moreover, we demonstrated the cytotoxicity of this kind of materials, in particular an enhanced cell viability in the case of fibers loaded with the allyl disulfide, ascribing these results to the ability of these materials to produce and release sulfhydric acid. We observe the cells on the surface of the fibers at fluorescence microscopy, demonstrating that in the case of neat PLA, you can see that the cells tended to be isolated, whereas in the case of fibers loaded with organosulfur compounds, the cells tend to be organized in clusters. That is very important with the idea to create a new tissue. And we ascribe these results to a localized release of sulfhydric acid, as well as to an increased hydrophobicity of the produced system. Regarding the biomobilization approach, we use two different concentrations of garlic extract, demonstrating the occurred demobilization of observation and scanning electron microscopy by EDX microanalysis, identifying the sulfur peak. Moreover, we demonstrated the ability to produce sulfhydric acid and the antimicrobial properties with the absence of the biofilm around the fibers doped with garlic extract. We demonstrated an increased cell viability in the case of fibers doped with the lowest concentration of garlic extract, whereas in the case of the IS1, as expected by the literature, a cytotoxicity effect was revealed. In order to demonstrate the action of the gas release from these materials on the cells, we carried out the test with the cell seated not on the surface of the materials, not in the contact of the materials, but on the Petri dish with the material on the lid of the Petri dish. So we compare these results also with not only with neat PLA, but also with PLA doped with another fast sulfhydric acid releasing agent, sodium sulfide, observing an increased cell viability in the case of materials doped with organosulfur compounds and more stimulating effect in the case of garlic extra doped materials, ascribed to the ability of these materials to provide a slower sulfhydric acid production and a better encapsulation due to its hydrophobicity. Finally, in order to demonstrate a possible protective action of the garlic extract towards the stress, the oxidation stress, we carried out cell testing in the presence of hydrogen peroxide. What can we see? That in the presence of hydrogen peroxide, we can observe around 70% decrease of cell viability in the case of neat PLA and PL doped with sodium sulfide, whereas in the case of garlic extract doped materials, we observe just only around 27% of decrease. So we ascribed this peculiar cellular protection activity from the oxidative test to the prolonged gradual release of sulfhydric acid in the time, as well as to the production of possible other gas in addition to sulfhydric acid. Some concluding remarks, very, very fast. What is the amuletic question? The amuletic question today is a scaffold or not a scaffold. In fact, very recently, a scaffold-free approach was proposed with the use of cell sheet, spheroids, tissue strands as building blocks in order to form the final tissue. Since this kind of scaffold-free approach presents some advantages, the reduced time necessary for tissue formation due to the very high initial cell density, the capability to address the architecture of complex tissue and organs, but also some disadvantages, the inferior mechanical properties of individual building blocks with possible cell damage during the manipulation, the immobilization time necessary for the initial fusion of the building blocks and the position of extracellular matrix in order to obtain the final construct. So, comparing the two approaches, scaffold and not scaffold, you can see that in order to achieve all the aims, high initial cell density, high mechanical properties, possibility of tissue self-assembly, functionalization with bioactive molecules, it's important to combine these two approaches, obtaining a synergetic strategy. Regarding the tissue engineering market, as you can see from this reported data, the global tissue engineering market is progressively increasing in the time.
Sorry to disturb you. It's going out of...
Two slides, I'm finishing, sorry. So, however, even if there is this very big increase of the tissue engineering market, the path from the scientific research towards the introduction in the clinical reality in the market, in the industrial mass application is still very, very long. As you can see from this comparison between the total number of the clinical studies during the time in black and the total number of publication in gray, there is a very, very big gap. Why this dichotomy? This dichotomy, according to me, is to be ascribed to a loss of communication between the research, academic, university world and the clinical reality that would be very, very important in order to better address the scientific research in order to satisfy the clinical needs. How it's possible to overcome this criticism? A simple contact is not enough, but a real and efficient cooperation is necessary towards the common purpose that is the patient health, to obtain a perfect balance among 3P, patient, procedure, and product. So just very fast, I would like to let you know that in this moment there is possible to submit some papers to different special issues, one regarding a conference, other one in polymers and DPI, another one in applied surface science advanced LCV. Also, we are organizing in my university, University of Rome Niccolò Cusano, in June 2023, the Cells and Extracellular Template Conference. So if you need some information, you can contact me. I would like at last to acknowledge all my collaborators, researcher, fellowship, PhD student, also external collaborations, since without them nothing is possible. And of course, I would like to thank you for your attention. I'm so sorry if I take more time.
Thank you, Dr. Ilaria, for the wonderful talk. Highly informative. Now it is open for discussion. Only one question is allowed. Please.
Okay. Well, I would like to ask you many. Okay, hydroxyapatite composite with polymer and also the scaffold is possible, but the apatite itself ceramics, it's always lack of the how I can say the plasticity and also that or K1C. Okay, it's a weak mechanical.
Yeah, but that is yeah. So that's a biocompatible material.
Composite with polymer is no problem to lowering, but the hiring of the K1C, do you have tried and succeeded or not? We have done and then not succeeded. We have only K1C3. We have arrived. That's all on the hydroxyapatite ceramics. We have done in more than 20 years ago, and even that my paper is more than 3,000 citation about that.
But did you try in vitro cell test?
Yeah.
No, really, with composite
so it's
material.
lowering of the K1C, and then the many composite is possible. That I agree. But to increase the hydroxyapatite itself to the more okay, K1C, okay, flexible or something, okay, without mix of the polymer. That is
Yeah.
the direction, another direction of the yours, but this is
So in
one
this
of the
moment, we are
possibilities.
working with composite material. So the idea is to use hydroxyapatite in order to, in the case of composite materials, we can encapsulate the hydroxyapatite within the polymeric matrix, particularly in order to improve the mechanical properties and to obtain mechanical properties compatible with the bone tissue, since we know that the bone tissue is composed of organic and organic components. In order to provide the bioactivity and the osteoconductivity, osseointegration, according to me, it's important to cover the material with hydroxyapatite, since when you incorporate hydroxyapatite within the polymers, it is covered by polymers.
Sorry to disturb you, it's running out of time. It's more than 10 minutes.
Thank you very much.
You can discuss later through email. Thank you, Dr. Ilaria, for wonderful
everything, I'm available by
Thank you
mail
so much.
if you want to contact
We
me.
move to the next speaker, Dr. Gabriela Cargia from Department of Chemical Engineering, Faculty of Chemical Engineering and Environmental Protection, Technical University, Romania. Title of her talk is Unique Nano Architectonics of Gold Nanoparticles, Layered Double Hydroxide Heterostructure for facilitating the controlled release of nanoparticles of gold. So may I request Dr. Gabriela to present her talk. Please restrict to 25 minutes and 5 minutes for question and answer. Then now proceed, please.
Thank you so much, Mr. Chairman. Sorry for before, because can you hear me well?
Yes, very much. You are audible.
So, because my connection was frozen before, so I received another connection, so now it seems okay.
It's okay, it's okay.
My
No
talk today is about nano architectonics of gold nanoparticles, layer double hydroxide heterostructures. I'll present some applications of these complex heterostructures, but the main application I chose for presenting at this conference is the control release of nanoparticles of gold from these novel materials, because it's important for nanoparticles of gold application. Will be important to control the release of gold nanoparticles, exactly like we control the release of a drug, for the drug to enlarge the controlled release at these nanoparticles of gold in time. So in the last decade, many researchers have been focusing their attention on gold nanoparticles and their applications, such that the gold nanoparticles became one of most versatile materials in nanotechnology. This because gold emerged within nano range some specific properties, including their biocompatibility, their low toxicity, but also we have for nano gold a special interaction with light. So the aim of our research was to engineer advanced materials by heterostructuring nanoparticles of gold with multifunctional nanoarchitectonics. Why this? Because today very much attention is given to broaden the functionalities of gold nanoparticles by heterostructuring, such that to combine the gold nanoparticles with another multifunctional nanocomponent for obtaining novel nanomaterials with advanced multifunctionality that is able to join the properties of both components, but also to give rise to the new components. So why it's important heterostructuring? So heterostructuring, and what means heterostructuring? Because heterostructuring is not just an ensemble of the components. So the heterostructuring means the simultaneous existence, but also the close conjunction of gold nanoparticles and the other component, let's say now the support that will give rise to synergistic interactions between the components. So we have to put together both components, but we have also to realize a close conjunction between nano-sized gold and the support, and to give rise to synergistic interaction between the components, interaction that will be able to modify not only the properties of the novel material, of the novel formulation, of the heterostructure component, but the properties that will be able to give rise to new features, to new properties, to new application. Why this, it is interesting, this multifunctionality? Because, for example, the support can come with its own composition, but also the support can bring its own morphology, and also we can make on the support, we can realize the surface modification. But also gold nanoparticles are able to come with their specific size, with their specific composition, and after assembling these two nano components, we will be able to do different treatments on the obtained heterostructure. So we will be able to enlarge the characteristics of the obtained materials by thermal treatment, by reducing treatments, by reduction oxidation cycles, or by adsorbate mediated cycles. This is a reason because it's very important to succeed to tailor not only the micromorphology, the nanomorphology of the joint components, but also to realize their interactions such that their electrons to be able to cooperate, to be able to realize a better transfer from gold, from one component to another, for example, from gold to the support, or from the support to the gold, that will influence both the properties of the support of the joint components and both the properties of the gold nanoparticles. Important progress has achieved regarding the control and optimization of the size and shapes of gold nanoparticles. Although the key characteristic of nanogold is related to its optical response when gold nanoparticles interact with light. This phenomenon is known as surface plasmonic resonance effect. Surface plasmonic resonance is related to the collective oscillations of the conduction electrons in different metal, and it can be classified in two modes. So we can speak about propagating surface plasmons and localized surface plasmon. By realizing the heterostructured plasmonic and a non-plasmonic interface, we can tailor the formation rate of electron-hole pairs, and we can enhance this collaboration between the electrons of the nano units on the surface rather in the bulk. Thus, the photo-generated carriers could promote shorter diffusion lengths, with less recombination probability and the energy stored in the electron hole pairs of the hybrid materials. So we will be able for realizing these heterostructures that we planned, that we designed by to engineer the size of our nanoparticles, to engineer the shape of the size of our nanoparticles, but this close connection and heterojunction between gold and another component will be able to change the plasmon-induced charge separation. In fact, by a specific join of gold and the other nano component, will be able to promote the transfer of electron between nano units and to give rise to specific interaction with light. The way in which we be able to tailor the interaction with light of gold is very important, not only for application in chemistry, in industrial catalysis, for example, in plasmonic hybrid catalysis, but also for application will be very important for application in nanomedicine. So, the other component that we choose in our studies to be heterostructed with gold is layer double hydroxides. So why we choose layer double hydroxides for heterostructing with gold? So what are layer double hydroxides? As you see here, layer double hydroxides are based nanomaterials for biomedical applications. So layer double hydroxide is a clay, is a synthetic clay, but it has diverse multifunctionality and very important, has low cytotoxicity and a very good biocompatibility. We can tailor very easy the diverse composition and structure of layer double hydroxide, but we are able to modulate the electrostatic interactions inside the layers of layer double hydroxide. And also we are going to use the very special properties of layer double hydroxide in the view of their nanomorphology, their special architectonics, to provide a confinement effect for gold nanoparticles. So let's see, in fact, what are their double hydroxides. By virtue of their excellent absorption capacity, tunable acid base, acidity, basicity, and the highly hydroxylate surface, the rigid and crystalline layer double hydroxide have a nano-architectonic complexity, a tailored composition, and a high functionality of the surface, but also it's very important that we can speak about the ease of the fabrication and the low cost of these nanomaterials. In fact, layer double hydroxides are able to serve as a support and to guarantee the stabilization of low nuclearity gold species on its surface by lowering atom diffusion, controlling the nanoparticle morphology, and modifying active nanometal electronic structure. But more than this, layer double hydroxide can confine gold nanoparticles on its surface, but also between the layers by the specific arrangement of the gold nanoparticles on the surface of layer double hydroxide. And also in the layers, between the layers, we can obtain slow controlled release of gold, because the gold from that were deposited on the layer double hydroxide outer surface will be released at a higher rate, but also a very low release of gold for gold nanoparticles will be obtained by releasing the gold from the interlayers. Because the layer double hydroxides are in fact brucite-like clays with 2D layers that are formed by defined by brucite-like sheets, and also they have an interlayer space where we can tailor the presence of different anions and also of different cations. One very important properties of layer double hydroxides is the diversity of their composition. So in the layers of layer double hydroxides, we can replace, for example, magnesium and with a lot of cations, with diverse cations such as copper, iron, magnesium, gallium, and so on. For obtaining our heterostructure and for design a special heterojunction between gold nanoparticles and layer double hydroxides, in our research we used very specific properties of layer double hydroxides. This means the structural memory of the LDH that assumes that the layered structure can be destroyed by thermal treatment, but can be reconstructed after the thermal treatment in the solution containing anions. So we can destroy and we can reconstruct the layer structure, and we say that layer double hydroxides show the memory of their structure when the calcined layer double hydroxides are introduced in the solution containing anions. So let's speak a bit about the method to obtain gold nanoparticles layer double hydroxide structure. So we have just gold precursor. So gold precursor is gold acetate in aqueous in water in the solution, aqueous solution, and we have just the layer double hydroxides. So by just using gold precursor and layer double hydroxides and not other chemicals, we obtain the heterostructure between layer double hydroxides and gold nanoparticles. As you see here, the different colors of gold and the different colors of the sample we prepared show us that we have different concentration. We can have different concentration of gold, but also we can reach different size. We can design different size for gold nanoparticles, but not only different size, but also different shape of gold nanoparticles. It's very interesting that only just by using layer double hydroxides and gold precursor, we could obtain such a complex nanoarchitecture. Do you see? We have the nanoarchitecture is described by large nanoparticles of the LDH, of the clay, of layer double hydroxide. But with these gold nanoparticles, now after 10 years of research, we succeed to put smaller nanoparticles of gold and larger nanoparticles of gold. We can tailor the release of small nanoparticles of gold, or we can tailor the release of larger nanoparticles of gold. So, very important, the conclusion of this special procedure, and it's a green procedure because it's just done in water at room temperature. and we just used layer double hydroxide and the gold precursor. And layer double hydroxide, it's not only the component of the nano assemblies that will bring a lot of functionality regarding their special nano architectonics, high surface area, special acid-base properties, high composition diversity. But the clay means layer double hydroxide, the clay matrix, because it's a clay matrix, it's biocompatible clay matrix will contribute itself to the fabrication of nanoparticles of metals or metal oxides, because this procedure, it's not only for gold nanoparticles. We can use the salt precursor of any metals, and we can obtain the same heterostructures, the same nanoarchitectonic based on the clay memory effect. Because when we put the layer double hydroxide in water, after we destroy its structure, the clay has the gift, because it's a gift, in fact, has the gift to take the anions from the solution, and here the anions are acetate anions. Will take by sure the anions to reconstruct its structure, because it has to reconstruct its structure in the aqueous solution. But gold, for example, here gold cations could not remain alone in the solution. So due to the specific electrostatic properties of the surface of layer double hydroxides, and also due to the high surface area and large nanoparticles, layer double hydroxides can take also gold cations and in general metal cations from the solution, from the aqueous solution, and to organize them. It's very interesting. They can organize them not as big particles. They organize them as very small particles on the surface, as nanoparticles on the surface. It has a preference to organize them as nanoparticles on the surface. So let's speak now about the nano architecture of these heterostructures, because the nanomorphology and the nano architecture that we speak here, because when we speak about nano architecture, we don't speak only about the characteristics and the size and shapes of nanoparticles. We speak about the way in which these nanoparticles are organized inside nanorange. So we were able to tailor the diversity of the gold nanoparticles on the surface of LDH, but also by this specific synthesis, by tailoring the composition of the LDH. By tailoring the composition of the LDH will assure different electrostatic properties of this nano unit. So by tailoring the composition of the LDH, we were able to tailor the size of the gold nanoparticles on its surface, but also the size of gold nanoparticles inside the layer, in the interlayer space, such that we could obtain very small gold nanoparticles. Do you see, can be smaller than 5 nanometers, and these small gold nanoparticles particles are a target in nanocatalysis, in nanotechnology, in nanomedicine today, because their toxicity is low, their biocompatibility is better, but also we were able to tailor specific conjunction of gold nanoparticles and LDH electrons, because for example, we could have chromium inside layer double hydroxide composition. We can have copper, we can have gallium, we can have zinc, such that to obtain layer double hydroxide to behave like semiconductors. So all these tailored interaction between gold nanoparticles and layer double hydroxide will produce very specific electronic conjunction in the designed heterostructure. So by modifying also the precursor that we use during the synthesis, we could obtain a tailored distribution of the size of gold nanoparticles on the LDH. So we could do transformation such that to obtain a specific oxidation state of gold on the larger LDH nanoparticles. We were able to obtain larger nanoparticles or better dispersity of the gold nanoparticles on LDH, or lower dispersity on we were able to increase the concentration of gold nanoparticles on the surface, or decrease of the concentration by fitting these to the applications that we are going to develop. Also, the results we obtain show us that the specific composition of LDH is very important.
Sorry to disturb you. So can you
Yes.
please? How long it
Yes.
will take? Sir?
Sorry?
No, can you please, try to finish it soon?
Okay.
Okay.
So
Thank you.
we also succeed to tailor the surface plasmonic response of gold nanoparticles and its oxidation state by using just the Taylor composition of the LDH. And the EXAFS analysis and XANET spectra showed us that we were able to modulate also the oxidation state of gold on the surface of nanoparticles. Regarding the release of gold nanoparticles, we just started this research, so we succeed to release gold nanoparticles from the LDH clays. So here you have how the adsorbed gold nanoparticles we release in just 1 hour, but the release of gold nanoparticles prepared by heterostructuring gold and LDH by reconstruction calcination method will take at least 8 hours. So we tested these materials in other applications, in energy applications, but I'll speak about this application another time. Thank you very much for your attention, and I want to give a special thanks to Professor Sabu Thomas for organizing this conference, because in these tremendous times, it's very important that research will make its point on this civilization, on this world, and I appreciate very much the efforts that you, all the Indian researchers, make to develop research in India and around the world, and to join you in this effort. Thank you so much.
Thank you for giving a wonderful talk. What about the stability of this layered double hydroxide?
Sorry, I did.
The stability of the layered double hydroxide is always in the
That is very stable.
Stability of the catalyst.
Stability of the catalyst. So layer double hydroxides are stable till 120 degrees Celsius. After this, their structure will collapse, will transform in mesoporous mixed oxides. And very important, I could not speak here, but very important, we can use the thermal treatment of this heterostructure to increase or to modulate the size of gold, because by calcination, the size of gold will increase, of course. So layer double hydroxides are used already in nanomedicine since 10 years ago. So they are used as catalysts or as catalyst precursors. So till 120 degrees, everything is very stable.
Okay. Thank
Okay.
you. Thank you. Thank you.
Okay.
I think you can close.
Close? Okay. Or
Please proceed.
okay. Well, you have made of the intercalated, okay, of the DLH, and then to the gold nanocrystal formed inside. But as you said, gold ion can be intercalated, okay, in the charged page layer. But the gold nanoparticle cannot. It means of the gold ion was intercalated, okay, much smaller than 1 nanometer, okay, much smaller, 1 order smaller. Then it was grown, okay, by reducing agent or charge of the internal charge. So you have not shown of this mechanism. Okay, intercalation itself, cation, anion can be intercalated in DLH. It's no problem. Okay, it's very important and then used as you told. But how it can grow to the gold nano crystal inside? Okay.
So
It
thank you
means
very
some
much,
reducing
Professor.
agent
Thank you very
needed.
much, Professor. I understand very well your question, but
Yeah.
I spoke now. We don't intercalate in this presentation. I don't speak about the intercalation of gold anions. I speak about the use of the LDH to form, to synthesize gold nanoparticles directly on its surface.
Surface
So
or interface?
I used gold acetate. I
Okay.
showed that I used gold acetate. So the anion is the acetate
Yeah.
in the aqueous solution. Gold is cations. As cations, gold will go only on the surface of the LDH as nanoparticle. LDH, this is the most wonderful aspect of this synthesis because LDH can be used to organize gold cations from the solution as nanoparticles on its surface. It's not about intercalation. We have studies about intercalation, but I didn't present here.
Okay. You told in this case the your gold is the nanoparticle nanocrystal or on the surface of the DLH.
On the surface, yes.
I
It's
see.
okay.
Okay. In
It's
that
okay.
case,
And it's very interesting
it
that
can be cluster and grow. It's possible. Yeah.
yes,
Okay.
and it's very interesting that LDH will take gold cations, will put on the surface, but also it's able by using LDH composition, we were able to tailor the oxidation state of gold. I didn't show here, but I have a study together with Japanese researchers where we tailored I can submit you if you are interested. We were able in applied catalysis B, we were able to tailor the oxidation state from gold 0 to gold 3 plus, just using the LDH and gold acetate.
Okay.
Thank you so much.
Thank you for.
Okay. Well.
Thank you for the
Very nice
wonderful
talk.
presentation.
Yeah.
I
Very
think
nice.
also.
Small question. There's
Yes,
a
sir.
small question.
Please, sir. Please, sir.
Yeah. How much of gold you could introduce in the LDH? For example, if 1 gram of LDH.
Yes. Very interesting your question, Professor Sabu. So
yes.
We prepare a solution of concentration of gold. So we could tailor the concentration of the solution if we want less gold. But usually we prepare a 10 or 15% concentration of the solution, and LDH will take as much gold will need to rebuild its structure. So LDH will take the concentration of anions to rebuild the structure. So will take as much concentration will need. So this means between 2 and 15% of gold on the surface of LDH. After 50% of gold on the surface of LDH, they will begin to agglomerate.
Right. I understand. I have another short question. How about the stability of these gold nanoparticles on the surface? Are they stable?
We can tailor to make it depends of the LDH composition, because do you see
Okay,
LDH,
thank you.
these have strong electrostatic interaction on the surface.
Right.
So we can tailor the electrostatic interactions on the surface to assure the stability of gold LDH nanostructure. It depends
Perfect.
of the
Excellent work. Thank you.
applications that you targeted.
So again, we
Thank you.
thank Dr. Gabriela for giving this very interesting talk. I also would like to thank Professor Sabu Thomas for giving me the opportunity
Thank you so much.
to chair the session. Both talks are very interesting. I think many of you might have learned something from out of that. It's because LDH is also new area of research, and the previous work with the gold scaffolds also very interesting work. I think this is very useful for the faculty researchers who are working in this area of research. Thank you, sir. Thank you so much.
Thank you
I
so
think we
much.
close the
Thank
session
you.
with this.
Thank you.
Thank you, sir.
Thank you also. And thank you for the efforts that you done for developing research in this world. Thank you to all of you.
Thank you. Thank you. Thank you.
Now we have come to the end of this plenary session. I would like to thank Professor Gabriela and Professor Ilaria for your excellent presentation, and also I would like to thank Professor Napoleon for your active chairing.
Thank
Thank
you.
you,
Thank you.
Professor.
Thank you. Thank you.
Now we shall move on to the invited session on environmental applications. I welcome Professor Afzal Hussain. Professor Afzal Hussain, are you there? I think the chair has not come. So now I would like to welcome Professor Mayeda El Said from Chemistry Department, the American University in Cairo. Professor Mayeda El Said.
Hello, I'm here.
Yes, Professor. I welcome you now. So your presentation is titled as Bio-Inspired Materials for Absorptive Removal of Emerging Contaminants. Professor, over to you.
Right, thank you very much.
Can you please share your presentation?
I'm sharing right now, yes. Can you see it now?
Yes, Professor. Please continue.
Right.
Can you please put on to the full screen mode?
It's a full screen mode on my computer here.
Okay.
Shall I try again? Or?
I think Madam Gabriel is still.
Screen mode now. Okay, shall I start? Hello?
Yes, ma'am, there is no slideshow. It's not full screen.
Professor, can you please try sharing entire screen? Though there will be an option called share entire screen.
Sharing their screen with the presentation. Okay. Shall I stop this and try again?
Yes, ma'am. Yes, yes.
Okay. It only says present a window or a tab. So, or your entire screen. I don't have this option.
You don't have that option.
Yeah, I can just share a window. I'm presenting entire screen here, but I'm not sure. I cannot see my presentation. So.
Dr.
Yeah.
Said,
Yeah, is it
can you see the three when you click the share button? Can you see the three options?
Yes.
you can select the entire screen.
Yeah, that's what I did actually.
Oh,
That's exactly what I did. Your entire screen, and then yeah.
whole screen, right?
Yeah,
We
but
can
when
share
I
the whole screen.
yeah, okay. So is that
Oh.
clear now?
No, we are still not seeing your screen actually.
For some reason,
Maybe
it's
you can
not
stop
sharing.
the stop presentation and then try to share it again.
I'm not sure why it's not active. The share button is not active. Whenever I try to do it my entire screen, it's not active. So not sure what's going on.
Madam, I think you better log out and log in again and try again.
Okay, so just leave the meeting, you mean, or?
Yes, you log it out and log in again and try it. Otherwise, you can continue
Okay,
again.
let me try. Okay, let me try.
Now you can open your presentation.
Now you can see it.
Yeah, you minimize this screen, and you open your presentation.
So is that okay now?
Not yet. You open.
Professor, we can't see actually. You can start presenting now. You can open your slides.
When I share the entire screen, I can't. It doesn't come as active. That's the problem. So I can only share with the window.
Dr. Said, it was right what you did actually last
It was
time.
okay? Oh, right. Okay.
Yeah, that was okay. That was okay. You just do that and start presentation.
Okay, that's fine. Okay.
Yeah.
Okay.
Yes.
Can you see it now?
Yeah, you can take your PPT now. You can take your PPT.
It's now clear. Can you all see it?
You can take your open your PPT.
It's open actually.
Yeah.
Madam, we can see your screen. You minimize this meeting room, minimize this one, and you open your presentation.
I can't hear you. Sorry. What was that?
You can minimize the screen and then open the PPT.
Okay, sure. Is that better?
No, is this no? You can take your PPT now.
That's my PPT now. I'm opening it. Can you see it?
Okay, okay. Please open that.
It's open now.
Are you seeing your PPT in the screen?
No.
Yeah, you can take your PPT. You can take your PPT. No, not from there actually. Not from there. Take your PPT from your computer.
Like that. Oh, okay, maybe drag it. You mean drag it to the?
No, not drag. Just take the PPT. Is okay. because we can now
Okay, is this
see.
clear now?
Now
see
you
it
can
now?
see. Now you can see your meeting room only. We cannot see because your screen is now showing the meeting room. You can take the PPT, then only we can see your PPT, right?
I'm not sure what you mean by taking the PPT. Is it because it's open on my laptop?
Oh, can you
It is.
close it and again open that?
Okay, I'll try again. Okay.
Okay, can you move the PPT, Ganan? Can you move it? Next slide. We can see a blank. Your PPT is blank. Can you move it?
Okay. I think it's better if I just instead of the entire screen share a window maybe because that would work.
നമുക്ക് അടുത്ത് തുടങ്ങിയാലോ?
Ma'am, can you please try sharing? Then we shall move on to the next speaker now.
Next one. It's coming. It's coming.
It's coming.
It's coming now. Yeah.
Ma'am, the better option is, can you please share your presentation? Can you please mail us your presentation so
Yes,
we can
sure.
share it from our side?
Yes, sure.
Sure, ma'am. Then we shall move on to the next speaker.
Okay. Sure.
So the next speaker is Professor Manash Jyoti Deka from the Department of Chemistry, BP Chalia College, Assam.
Hello.
Professor Manash, can you please share your presentation now?
Okay.
Professor Manash will be presenting on the topic waste-derived fluorescent carbon quantum dots for artificial nano enzyme applications.
Is it visible? Hello.
No, Professor, we can't see it now. Can you please try sharing the entire screen option?
Yeah. I have already shared this entire screen.
നമുക്ക് വേറൊരാൾ തുടങ്ങിയാലോ? നമുക്ക് വേറൊരാൾ ഇട്ടാലോ? നമുക്ക് വേറൊരാൾ സ്റ്റാർട്ട് ചെയ്യും. വിളിക്കാൻ പ്രശ്നമാണോ? അതിനാ പറഞ്ഞു.
Can I send my PPT to that email ID?
Yeah, it's okay. You can share your presentation by mail. Then
Okay.
we'll open it from our side.
Okay.
think it's probably mine is showing now, right?
Yes, ma'am. We could see your first slide. So
yeah, you can see it, right? Okay, yeah.
Yes.
Now it's clear, right?
Yeah. Yes. Yes. Now it's perfect. You can.
Okay,
You may
great. Yeah.
please
I think I
proceed.
got it finally. Sorry about that. Yeah.
Okay, ma'am.
I think I had to minimize. Will I wait for the next speaker or shall I go on?
Now I request Professor Manash to wait for some time. Let Professor Maida El Said do her presentation now.
Okay.
Professor Maida, over to you.
All right. Thank you very much. I'm very happy to be here with you today, and thank you for inviting me over. I'd like to thank my Dr. Sabo Thomas very much for his kind invitation, and I'd like to thank the organizers as well for their great efforts in organizing the conference. I'm here today to talk to you about some of our recent work on the bio-inspired materials for the absorptive removal of emerging contaminants. Before I start, I'd like to introduce myself very briefly. I'm Maida El Said, and I'm an associate professor at the Department of Chemistry in the American University in Cairo. I had my PhD from the University of Cambridge in the UK, and I worked in the University of Maryland in the US for some time as visiting faculty. My talk will just really go very quickly as an overview over the some of the work that we've done in the past couple of years or so on the area of water treatment and bio-based and bio-inspired materials. I'll start by just giving an overview of the water scarcity problem, and then I will move on to the talking about emerging contaminants, which is really our concern these days, and our group is interested in working with these contaminants since they are also an emerging area. And I'm going to focus on some examples of the work that we've done to develop processes for bio-inspired absorbents and to develop also the materials themselves for the water treatment and for removing the emerging contaminants in particular. So, of course, as we know that our Earth is covered by 97.5% of salt water, we only have 2.5% fresh water available. Only 0.77% of that 2.5 is actually accessible fresh water. So we are really facing a problem here with the scarcity all over the world. This is from the Economist Intelligence Unit. It's a study that was predicting the water stress levels by 2040. And you can see that they are calculating the water stress level as a projected ratio of the water withdrawals to the water supply. And they are highlighting by color coding here the areas that have extremely high or high risk of water stress levels by the dark red color and the light color. And you can see areas in the Middle East, for example, affected by that, areas in Asia and India and so on. So according to the United Nations Sustainable Development Goals, there is a need for really managing the water and making sure that we have proper water systems. So if we look at the 17 SDG goals or Sustainable Development Goals of the UN, we can see that they are mostly either directly or indirectly related to the water management, but of course some of them are very clear that they are directly related, like for example number 6, clean water and sanitation, number 14, life below water, and as a result of that there is a need for the management and responsible consumption and production, which is goal number 12. And as a result as well, this would lead to good health and well-being. So what we are trying to do is to work on managing the water by treatment, and one of the important classes of contaminants we are interested in are contaminants of emerging concern. Of course, there has been a lot of research going on the conventional contaminants like the heavy metals and the dyes, but some of these heavy metals have been also recorded as being recently or documented as being also emerging because their levels are increasing. And some of the dyes, like the azo dyes in particular, because of their health hazards, they have also been listed as emerging contaminants lately. So what are emerging contaminants? Sometimes they call them emerging or CECs, contaminants of emerging concern. They are either contaminants that have been present already and released into the environment for a long time, but they have not been properly monitored or detected because there were no appropriate methods to do that, or lack of the methods. Or on the other hand, they can be chemicals that are completely new to the environment, recently introduced because of the industrial developments, and they have not, of course, been detected. This cartoon will show you some examples of the major classes of emerging contaminants, but the ones that we have been also interested in our group are antibiotics, for example, personal care products, some pesticides, and so on. And I'm going to give examples on that later. So our group, STAR-SEP Lab, or Sustainability Targeted Separation Lab, it is a lab that is concerned with separation methods in general, but focusing mainly on sorption and chromatography methods for developing products and processes. And we target processes and products that are environmentally friendly, that are towards the sustainable development solutions, and also we make sure that we try to use green processes and green synthesis for producing our functional materials. Our functional materials are used for different purposes. What I'm going to focus on is the environmental applications today, specifically the water treatment of emerging contaminants. But we also work in other areas of desalination. We also work in areas of food and biochemical pharmaceuticals, because we use our methods as well of separation to separate bioactive compounds like polysaccharides and proteins. So these bioactive compounds also are used in food applications or pharmaceutical applications. And we also work on some biomaterials as well. With the use of the adsorption methods, we apply them in bone regeneration. So I'm gonna focus, like I said, on the adsorption in particular of emerging contaminants and using specifically the eco-friendly bio-inspired adsorbents. I'm gonna divide my talk into three main types of bio-inspired adsorbents. First, agricultural waste and their activated carbon derivatives, and then I'm gonna move to the biogenic nanoparticles, metal oxide nanoparticles, and then I will move to the biopolymer coated nanoparticles. So this is one of our articles that was recently published on a novel approach for removal of methylene blue as an example of an azo dye for removing this dye from fava bean peel. The novelty in the process was, or in the approach, was in using ultrasonication for the absorption rather than the conventional method of absorption. And we actually compared the conventional method to the ultrasonic biosorption. We have here our fava bean peels. Of course, we worked on preparing them first, and then we used them right away for our biosorption studies on methylene blue. And we did, of course, our characterizations, but the goal here was to compare between the ultrasonic approach and the conventional approach. And we did also a modeling, a multiple linear regression statistical model, to be able to look at the factors or decide on the factors that are influencing the bioseparation and how these factors are affected also by being ultrasonic or conventional. And we did the kinetic studies as well to see the rate of biosorption. When we worked on that, we found interesting result that the ultrasonication and the conventional methods are actually comparable in the removal percentages. So here we can see, for example, in the orange color, which is either solid or hollow, the conventional ultrasonic, they are both giving more or less the same removal under different absorbent doses. But what is interesting is that although they are giving the same removal, they did not give the same rate. And I'm going to move to the rate in a bit. Also, you can see that the Q is decreasing with the dose. We have a log-log ratio or log-log relationship here, but which tells us that it's better to work in the range of low adsorbent doses, because you can use a low dose and at the same time get high removal. So we concluded that we have successful removal in both conventional ultrasonic. They are comparable in their values, But what is interesting is that the ultrasonic process is much faster than the conventional one. It actually took place in less time. It's up to 4 times faster, and at the same time maintaining the same sorption capacity and also maintaining the chemical structure as we have confirmed by our chemical analyses and FTIR. We optimized the operating parameters, and we came up with a sort of an equation that relates the Q with the factors that are affecting. We found that the time, of course, the concentration and the dose are affecting, but also X here, which is the mode of operation, whether it's conventional or ultrasonic, is affecting the absorption capacity. And we got very good also R-squared values and p-values for our model. We studied the mechanisms. Of course, as I said, I'm going very quickly through it. So we studied the mechanism, of course, in detail with our measurements, and we did some electrostatic. We did some zeta potential measurements. We found that the binding mechanism here is electrostatic mainly, and there is a possibility also for hydrogen bonding because we have positive, negative charges on the dye positive and on the peels negative. So we got an electrostatic interaction. Another also published work on the bio-inspired adsorbents. This time it's on using the peach stone, which is again a waste product and a food waste, and converting it this time to activated carbons. So we did not use it as such like we did in the fava bean peels. We actually did a further step of treating it to thermally and chemically to get nanoporous activated carbons. And we used it this time for a pesticide, imidacloprid pesticide. So we started by the peach stones and we did some chemical activation with phosphoric acid and then thermal treatment under 2 temperatures, 300 degrees and 500 degrees. So we got PS is the peach stone, PS activated carbon AC at 300 and PSAC at 500. The idea was to look at how we can see the effect of temperature on the activated carbon structure, and this was interesting to find as well. As we said, we try to minimize on the conditions that are used for treatment, so we try to go to lower temperatures as much as possible in the pyrolysis step, for example, and in order to do that, we measured at different temperatures, and we did the treatment at different temperatures. So this is what we got. We actually got an interesting result, which is that the PSAC at 300 is showing a microporous structure, as emphasized by the BET analysis, and the PSAC 500, which is the higher temperature one, is a mesoporous structure. And we found out that of course, the surface area has changed here. And by micro and meso, we mean that if we are having pore sizes below 2 nanometers, that's microporous, and between 2 and 50 nanometers, that's mesoporous. And when we did that, we found that the one that is at higher temperature is actually giving higher absorption capacity, but at the same time, lower rate of absorption. And I'm going to explain that in a bit. And then we had an interaction. We studied the interaction, and we found that the interaction is mainly physosorption interaction. We did some DR modeling. We did some characterization. We found that it is mainly through the pi-pi aromatic interaction or pi-pi stacking, or through hydrogen bonding. Now, as you can see here, the microporous structure of the 301 is on top, and this is forming almost a monolayer. And in the mesoporous, the 501, we are getting hysteresis loop, which shows that it's mesoporous, and you can see also the pore size distribution here that shows that the 301 is below the 2 nanometer mostly, and the other one, of course, is in the range of 2 to 50 as the measure amount or the majority. So the absorption performance with pH here shows that the orange ones, the orange line or the orange scattered points here, are showing the 500 activated carbon. That is the one that is showing higher absorption capacity, which is about 5 times higher than the 300 one. The 300 is down here in blue. And on the other hand, when we did the rate, we found that the rate of the 300 is faster. when we look at the regeneration, also we did regeneration cycles, 3 regeneration cycles here, and it was regenerated very well with 0.5 molar HCl at 25 degrees, both of them actually. So we concluded that we can reach up to 80 and 99% removal with these activated carbons, but at the same time, we need to look at how the pyrolysis temperature affects the textural properties. So it affects the textural properties and the absorption performance. And the 500 would be advantageous in terms of the absorption capacity, but again, because it gives 5 times higher than the 301, but the 300 is much faster in kinetics because of its micropore structure. So it's at the end of the day, it's a trade-off between the absorption capacity and the kinetics. What do we want to do? Do we want to go to lower temperature and increase the kinetics, which means decrease or reduce the operational time? And of course, at this point, it's a cost-benefit analysis to choose the best conditions that we want. As we said, the mechanism here is pi-pi or hydrogen bond. All right, I'll move on also quickly here to another attempt that we are doing, we're working on, and it's on the removal of caffeine and salicylic acid pharmaceuticals, this time using the Cape gooseberry husk. And Cape gooseberry husk, this is the Cape gooseberry fruit, and its husk, this cover is used in our study for producing, again, activated carbon at 2 different temperatures. The thing is, we are trying to work here with agri-food wastes, which is one of the problems that we face in industrial wastes, and we have used here the gooseberry husk that was produced from one of the industrial plants, fruit industrial plants, that was working on juice production, and they were using this as in one of their lines for producing the juice. And so we took the waste from the industrial line itself, and we worked on it to produce these activated carbons. We have the husk as H here, and the 2 other activated carbons, H350 and H500. We did zeta potential measurement. We find here that the one that has the lowest zeta potential, which is highly negative, is the H350, and this is the one that is most stable in suspensions. And we used this one we actually did, of course, characterization on all of them, but we are focusing here in image number B and C on the H350 because that's the one that was interesting in terms of removal. And we did also, again, BET on that, and it came out to be a mesoporous absorbent. So the mesoporous absorbent here is shown in blue, the mesoporous husk. We found that it contains slit pores. That's the type of pores it has according to the BET analysis, slit pores, and it was used to capture the salicylic acid and the caffeine. It is used to capture them by different methods. We figured out that underlying mechanisms could be electrostatic between the caffeine and the husk, electrostatic attraction. Between the salicylic acid and the husk, it's between van der Waals and hydrogen bonding. There's no possibility for electrostatic attraction because they are negatively charged, so it's in most cases a repulsion rather than an attraction. But it can work dipole-dipole, for example, by difference in the distribution of the surface charge, and it can work as van der Waals. We also did a binary system study. So we simultaneously absorbed the caffeine and salicylic acid, and we found an interesting result that the caffeine is more competitive than SA. And this could be actually understandable because the underlying mechanism, like we said here, is more of an electrostatic mechanism, so it's more competitive than the weak physical forces. And you can see that from the removal values. You can see that the SA, which is in binary system, is going down. It's very low removal relative to the SA, for example, in the single system, which is in hollow orange. The caffeine, on the other hand, was not affected, which shows minimal really interference here and minimal competition from SA. So in general, a food waste can be used here for removing 63% and 85% of caffeine and salicylic acid respectively. Like we said, there are different mechanisms of interaction between the two, and the binary system was highly favored for the CA adsorption. Okay, so now moving on from the biosorbents or sorbents that are based on activated carbons or agri-waste products, we move on to the biogenic metal oxide nanoparticles. And in this case, we are using natural products to produce, using green synthesis, the nanoparticles to be used for water treatment. Here we are working on zinc oxide nanoparticles to capture antibiotics, ciprofloxacin and tetracycline. And we used here a source of polysaccharides to work as a reducing agent for the zinc acetate to produce zinc oxide nanoparticles. The natural product we chose here is stevia, and stevia is used a lot in food industries. Nowadays, there is a trend of using them even more as a substitute for sugar. For example, one of the big fizzy drinks industries are using stevia now. They have produced a line for stevia as a substitute for the sugar. So we actually analyzed the stevia, and we extracted the polysaccharides from the stevia. So we have here the stevia extract, and we try to use as green processing as possible. Yes?
Can you please conclude?
Okay, right, I'll try it. Okay, so we have water extraction here, and we produce zinc oxide nanoparticles for treating, capturing these antibiotics. Okay, now here we did some characterization. We made sure that this is the zinc oxide that we have, and we got very high removal here. We have here very high removals that reach up to 72% and 86% for the two antibiotics. And we regenerated also the nanoparticles for 5 cycles. My last part here is on biopolymer coated magnetite nanoparticles, and we used the nanoparticles here, magnetite, as a core, and we coated that with biopolymers composites. We have a composite of xylan and chitosan here. We added this to the magnetite solution, and we formed the biopolymer coated magnetite. We were able to remove different classes of contaminants, the salicylic acid as a model for pharmaceuticals, congruent as a model for azodyes, and lead as a model for emerging heavy metal. And this is just characterization to ensure that we have a layer formed around the nanoparticle, and that we have the main function groups of chitosan and xylan. We did 2-stage adsorption and 1-stage adsorption, which means that we add our adsorbent in 1 stage, and then we remove the adsorbent with a magnet, and then we do another 2nd-stage adsorption. So our adsorbent dose, instead of using it once, we can split it into 2. Why did we do that? Because we found out from the results of the adsorbent effect that using 2 stages would increase the removal than using 1 stage, because in 1 stage there is a possibility of agglomeration of the fine particles of the adsorbent. So without going into details, we were able to get higher removals here, above 75 and above 80 for these contaminants. Our underlying mechanism is different, which means that we are working multimodal here. So our adsorbent can work chemical chelation for lead, and it can work also physical interaction for the salicylic and the congruent. And this is interesting because this means that we can use one adsorbent for different contaminants. Our nanoparticles are within the range of 11 nanometer here, and that's one example of the biopolymer coated. Another example is the activated carbon nanoparticles, which are coating the magnetite again, but we incorporate in the synthesis biopolymers.
We are exceeding the time. Can you please conclude?
A couple of minutes. Yes, just a couple of minutes. So the activated carbon was actually was giving high values of removal for the famotidine and fluoxetine drugs. Fluoxetine is an antidepressant, and famotidine is anti-inflammatory, and they have not been used much in literature. Only a couple of studies here. So what we are doing here is that we are getting high removals that are comparable to activated carbon, but we are mitigating some of the problems of activated carbon, like, for example, stability. We got better stability with the nanocomposites. We got better thermal stability, and we got better regeneration than the activated carbon alone. Just to conclude here, we need here a more holistic approach for water sustainability. We need to look at water, energy, food nexus. Like I've shown here, we are considering alternative approaches, not just looking at the water itself, but looking at agri-food waste and valorization of these wastes, looking at green synthesis and green processing methods to be able to have sustainable solutions for the challenging problems. These are my acknowledgements for my AUC team and the collaborators around the world, and thank you very much for your attention. Thank you.
Thank you, Professor, for the nice presentation. Now the session is open for questions.
Can I ask a question? Is it over? Can I ask a question? Very nice talk, Professor Mayada.
Thank you very much, Dr. Sabah.
Very nice talk.
I try to be as fast as possible. There's a lot to say.
How effective is the activated carbon? Because activated carbon, sometimes activated carbon fails to remove fluoride, nitrites. Such situation may occur. And sometimes, activated carbon gets clogged. How do you deal with these issues?
Yeah, the point is that's why we actually resorted to using other alternatives, incorporating biopolymers with the activated carbon, because one of the problems, for example, is that regeneration is difficult. Like you said, it agglomerates very easily. A lot of industrial problems were improving these properties.
Right. So it can catch all the microbes, right?
Sorry?
It can catch hold of all the microbes, right? It can microbes.
Yes, we also did, but I didn't show it. We are doing also some antimicrobial activity for our adsorbents to make sure that they are also safe to use in the water. Like, for example, the zinc oxide nanoparticles, we did some antibacterial, and it showed that it's very safe to the environment as well. It actually has antioxidant activities and antibacterial activities.
Right. Finally, what do you how do you dispose the contaminants?
Yeah, this is actually a very good question. Yes, because we did some, of course, we did regeneration studies here, but the point is we can concentrate our contaminants and then be able to dispose them off safely, right? Having the nanoparticles also within the biopolymer matrix will also help in mitigating the effect of releasing the nanoparticles in the environment as free nanoparticles, which we know that they could be toxic. That's why we are doing the antibacterial as well, to make sure that they are not toxic to the environment.
Thank you. Very good talk.
Yes, Professor Ishimori. Yes, sure.
Yeah, okay. Yeah, it's a very nice talk. And then I appreciated the biopolymer, or even some waste polymer. Okay, waste polymer had the active, because carboxylic or OH including, so that the whole cation like red or chrome can be captured.
Yes, exactly.
It's okay. Okay, right. So that is even without magnetite, it's possible. But with magnetite, you can remove, easily by outside magnet.
Excellent. Yes, thank you very much. Yes,
so
because I was talking very fast.
To
That's the point.
easy to removing. Okay.
Yes, that's the point. It's fissile removal. Yes, thank you so much.
Yeah.
Yes.
That is a very good, and also some magnetic field. Okay.
Yeah.
Dispersion and the collection, and it's easy. Okay.
Yes.
All
that's how we can collect them easily. Thank you so much.
Okay. That is my suggestion.
Very good remark.
For you.
Thank you.
Okay.
Hello, ma'am. Can we use carbon nanotubes for the removal of heavy metal from wastewater?
Carbon nanotubes. Yes, we are not really working on that, but carbon nanotubes also are useful because I did some work long time ago on introducing carbon nanotubes also in membranes because they can, in addition to their functionality, they can actually increase the mechanical properties, enhance the mechanical properties of your absorbents. Yes, definitely.
Okay, ma'am. Thank you.
No.
Thank you, ma'am, for your
Thank you.
nice presentations.
Thank you very
Next,
much.
moving to another invited session on carbon nanostructures, where the Professor Manash Jyoti Dekha will present. He's from the Department of Chemistry from Assam, India. And the topic is waste-derived fluorescent carbon quantum dot for artificial nanoenzyme applications. Professor Manash, are you there?
Yes. I
Okay.
have
We will
sent
do
you-
your presentation.
I
and
have
you
sent
can-
a PPT.
Oh, yes, we got it. We will do. Professor Manash, now you can start. Can you see your slides? Professor Manash?
Yes.
Can you see your slides?
No. Yes.
Right. Okay. Then you can start.
How can I make it full screen?
It's already in full screen.
Okay. Good afternoon, everyone. Today I am going to present my work on waste-derived fluorescent carbon quantum dots for artificial nanoenzyme application. So I am Dr. Manojyoti Dekha, Assistant Professor, Department of Chemistry, Bimola Prasad Cholia College, Nagarbera, Kamrup, and my college is situated in Assam and 70 kilometers from Guwahati city. So in this work, we have synthesized some fluorescent quantum dots from waste like tea waste, and we have already synthesized from water hyacinth waste to fluorescent carbon quantum dots. And this quantum dot shows beautiful fluorescence, and these quantum dots can be used in fluorescent detection as well as some other applications. So these are the allotropes of carbon. So our research interest mainly focused on graphene quantum dots and carbon dots. So graphene is sp2 hybridized, then graphene quantum dot is sp2, carbon dots sp3, and carbon nanotube sp2, and fullerene and diamond. So our research interest mainly focus graphene quantum dots and carbon dots. So carbon dots mainly three types: graphene quantum dots, carbon quantum dots, and carbonized polymer dots. So graphene quantum dots mainly synthesized from this graphite, carbon nanotube, fullerene, and graphene oxide. And also from exfoliated graphene. And carbon quantum dots mainly synthesized from different biomass, waste, then some amino acid and other sources. And these carbonized polymer dots are synthesized from different polymeric materials. So this CQD or carbon quantum dots were first discovered in 2004 accidentally during the purification of single one carbon nanotube. So this discovery triggered extensive studies to exploit the fluorescence properties of these CQDs. So our these graphene quantum dots are zero-dimensional, and quantum size graphene fragment diameter is usually less than 100 nanometer, arranged in a planar and hexagonal lattice, and it is composed of a single monolayer of sp2 bonded equivalent carbon atoms bonded together with sigma bond. So graphene quantum dots are mainly arranged in planar and hexagonal lattice, and with sp2 moiety, there may be some sp3 moiety present in graphene quantum dots if there is some or present some defects in the preparation process. Again, for carbon quantum dots also zero-dimensional, but it may or may not be arranged in planar and hexagonal lattice, and their sizes are below 10 nanometer, and they are mainly sp3 hybridized. So these carbon quantum dots and these graphene quantum dots shows beautiful fluorescent property. So this is the structure of carbon quantum dots, and this is the schematic representation of graphene quantum dot. So this in this work we have synthesized this carbon quantum dots mainly from tea waste. And we have collected the tea waste from tea industry nearby in our Nagarbera area. So from that tea waste, we have standardized the procedure and adopted a standardized procedure, and we have synthesized these carbon quantum dots. And then we have characterized these carbon quantum dots using different analytical techniques. So these are the synthesis approaches of carbon quantum dots: hydrothermal, laser ablation, and chemical vapor deposition, ultrasonic sharing, and chemical exfoliation. But we have adopted only this hydrothermal and this chemical exfoliation technique to synthesize our carbon nanomaterial. And for we have also worked on synthesis of graphene using this chemical vapor deposition method, but here I will talk only this carbon quantum dot synthesized by this hydrothermal method. So these are some application of carbon nanomaterials. So this can be used in some biosensor, chemical sensor, and as the size are below 10 nanometer, it shows beautiful fluorescence with different color. And it can be used in drug delivery, bioimaging, and screen in LCDs. So these are very important material, and we can use them in different fields. So these are the properties: tunable photoluminescence. Their surface area is high because their size is very low. Their photostability, biocompatibility, and it shows a low toxicity. As we have synthesized this carbon quantum dots from some waste and biodegradable materials, so that the toxicity is very less. So these are some preparation method. These are top-down and this bottom-up method. So top-down method mainly this arc research, laser ablation, electrochemical, and acid oxidation. And bottom-up approach are hydrothermal, thermal, microwave assisted, and template. So for our quantum dot synthesis, we have used this top-down approach. So the objective of my talk is to synthesize carbon quantum dot from TUS through hydrothermal treatment and characterization of synthesis carbon quantum dot using different techniques, and to study the peroxidase mimic activity of this CQD using TMB. It is a colorimetric substrate at different pH and different reaction time and different temperature. So what is nanoenzyme or nanoenzyme? So with the progress of research in interdisciplinary science, there is an urgent need to artificial nanoenzyme mimic that possess peroxidase-like activity like horseradish peroxidase. So nanoenzyme are nanomaterials with enzyme-like characteristics. So in simple word, nanoenzyme possess enzyme catalyzed properties and are easy to prepare, size controllable, adjustable in function, having their dimension in nanorange. So first nanoenzyme was reported in 2007 in case of iron oxide nanoparticle, and it shows peroxidase-like activity, and they detected hydrogen peroxide. So after the discovery, this enzyme mimic attracted much attention, and it can be used and reported for gold, silver, manganese dioxide, copper oxide nanoparticle, and many more. And this artificial nanoenzyme catalyze the oxidation of colorimetric substance like DAB, TMB, OPD in the presence of hydrogen peroxide to give a color compound, and it is used for the colorimetric determination or naked eye detection of toxic ion or as well as biomolecules. So we have here we have taken this TMB colorimetric substance for our work. So these are the some factors that affect the catalytic properties of nanoenzyme. So these are pH, then surface modification. So as the carbon quantum dots contain some oxygenated functional group, as we have synthesized the carbon dots from T, that the surface quantum dot surface contains some polyphenols. So maybe this surface modification, then the size of the quantum dot also affect the catalytic activity. Then temperature, and then doping, and the morphology, and the affect the catalytic activity of our nanoenzyme. So these nanoenzymes are low cost, size controllable, high catalytic activity, and highly stable. So it can be used in catalysis, biomedicine, bioimaging, chemical industry, optoelectronic device, then biosensor, etc. So in recent work, we have synthesized the carbon dots from water hyacinth waste, and we have used them for the application of sensing petrelacor. Petrelacor is a herbicide, and it is used in tea garden, and it is so we are able to detect with turn-on fluorescence of this carbon quantum dot synthesis from water hyacinth waste. So we have synthesized the carbon dots from water hyacinth leaf, and then we have some procedure. We make this carbon quantum dots, and it is fluorescent. So this is the procedure to synthesize this carbon quantum dots. First, water hyacinth, we have taken water hyacinth, then dried in sunlight 3 days. Then this is a dry water hyacinth leaves, and removal of chlorophyll in ethanol. So we have removed the chlorophyll. Then dry water hyacinth leaves in ethanol. Then we have grinded it to powder form and sieving to make it uniform. Then we have impregnated in phosphoric acid for 24 hours. Then heated this 150 degrees Celsius, and after that it disperses in water solution, and then centrifuge, and we take the upper layer of the centrifuge solution, and that's in this way we have synthesized this carbon quantum dots from this water hyacinth leaves. So after that we have characterized these carbon dots, and we have seen that the from SEM and TEM images it is clearly seen that the size of the carbon quantum dots are below 10 nanometer, and the zeta potential value also shows that the size are below 10 nanometer. And this is the Ir Spectra of water hyacinth, and this is, and other is the carbon quantum dots. And the carbon quantum dots, the peak is broad, the 002 peak is broad, which shows that the amorphous nature of the carbon quantum dots. So from these analytic techniques, we have confirmed that the synthesis of carbon quantum dots is successful. Then we have used this turn-on fluorescence of the quantum dots, and we have seen that the petrelacor herbicide can be detected for this carbon quantum dots fluorescence property. And we have put forward a mechanism, and we are we seen that maybe the electron transfer mechanism may be the responsible for the turn-on fluorescence of the quantum carbon quantum dot synthesis from this water hyacinth waste. So we have done some systematic study, and these systematic studies were you can see in this journal, published journal. Then in this presentation, I would like to talk about the synthesis of T carbon dot synthesis from T waste. This is the mechanism of this carbon dot synthesis from water hyacinth waste. So maybe the electron transfer mechanism is responsible for this enhancement of PL fluorescence after the addition of this herbicide, and we have also tested in the soil sample contaminated with this herbicide. After that, we have synthesized the CQDs from T waste. So we have adopted this procedure as our previous laboratory has already worked for the T, and we have this time we have taken a T waste, and the procedure is that T waste were first cleaned with water and then alcohol and dried. This process was repeated several times. Then these clean waste were heated at 100 degrees Celsius for 2.5 hours, making powder form simply by grinding. After that, the powder waste were heated 200 degrees Celsius to 8 hours to form a black carbonized powder. A quantity of approximately 300 mg of carbonized powder is dispersed in 1.1 molar acetic acid and kept for 2 days. And that dispersion was then centrifuged for at 10,000 RPM for half an hour. A supernatant liquid which contains the carbon dots were collected and preserved for the experiment. As you see, this is the dispersion of this T dispersion, and this is the under UV light, and it is seen that the under UV light it is so blue fluorescence, beautiful blue fluorescence. So we can confirm that the synthesis of this carbon quantum dots from T waste is successful. Then we have done some experiment to confirm the synthesis is successful. So then we did a TEM characterization, then UV visible spectroscopy study, then Raman spectroscopy, and we have confirmed that this the synthesis of T carbon dots is successful. So these are the characterization. So UV visible spectroscopy showed there is a peak at 270. This may be due to the N2 pi star transition of the functional group, oxygenated functional group present in the T surface, the T carbon dot surface, and this is the fluorescence spectra, and this is under UV light, beautiful blue fluorescence, and this is normal light. And from TEM images, it is seen that the particle size are below 10 nanometer, and there is a broad peak at 2 theta value 24, approximately 24 degree. And it is in that, so some crystallinity in there in case of T carbon quantum dot. So from this observation, we confirmed that the T quantum dot contains some oxygenated functional group and size are below 10 nanometer, and crystallinity remain, some crystallinity remain in T quantum dot surface. So this is the Raman spectra, and Raman spectra we have seen two peaks, D band and G band. So we can conclude that there are some defects or in the quantum dot because D band is for defect and it is for sp3 hybridized carbon. So along with some graphitic nature in this T carbon dot system, there are some defects is also present. So this is the fluorescence spectra, and fluorescence spectra shows some excitation dependent PL behavior, which is
you mean joint?
Yeah.
In the field theory.
So then we have investigated the peroxidase mimic activity, and for that we have used TMB and T carbon dot as well as hydrogen peroxide and sodium acetate buffer, and intracellular mixture for 30 minutes. And we analyze the enzyme behavior of T carbon dot and found that the carbon dot activates enzyme activity and can oxidize the peroxidase substrate TMP in presence of hydrogen peroxide, and it gives blue color solution.
I think about 1,000 stuff.
This is like These
are study of some peroxidase mimic activity, and we have standardized the protocol, and we have studied the peroxidase mimic activity at different temperature, different pH, and at different times. And it is seen that the 45 degrees Celsius is maximum activity, and for pH, pH 4 is maximum activity, and at they also observed that
he promised to include, but now
it shows maximum peroxidase mimic activity.
done online.
So next.
Perfect.
So these are the findings from this peroxidase mimic study. So we can use this T carbon dot as a peroxidase mimic, and we have established that T carbon quantum dots also without doping or doping, we can use as a peroxidase mimic substance for colorimetric as well as fluorescence sensor. So
have you been to Cairo?
No.
So we have analyzed the TCD, and this is the we put for the simple mechanism as this blue color of this TMB usually colorless. If we add H2 hydrogen peroxide in presence of our T carbon dot, it gets.
So can you please conclude?
Okay. So this the conclusion: carbon quantum dots are synthesized from TUS using top-down method. The synthesis process of CQD environmental friendly and also cost-effective. The PBR series shows beautiful blue fluorescence, and this CQDs can be used as an artificial nanoenzyme. And we have standardized the protocol at different temperature, pH, and reaction time. And this work is in progress, and in future planning to use this CQD colorimetric. We can use it a naked eye detection for this and fluorescence dual sensor for this biomolecule as well as some hazardous ion. So this is my work on it is not it is ongoing work. Then acknowledgement, I would like to HOD and my PhD guide, Dr. Debashish Chaudhary, Professor, Institute of Advanced Study in Science and Technology, Guwahati, for his help and support, and to providing me the adequate laboratory facility to complete this work. These are my publications till there. And we have we have also filed one patent on this activated carbon synthesis from TUS using some bio-inspired chemical. Thank you.
Thank you, sir. Thank you for this presentation. Now the session is open for questions.
Could you control the particle size very precisely in your system? The size, shape, and distribution?
Sir, size can be controllable if you can by centrifugation. Centrifugation, if you sonicate the dispersion, and after that use centrifuge, then the bigger particle comes down, and the superintendent, then we can get some uniform distribution of particle. Otherwise, there is lots of moieties along with this small particle. There are some big particle greater than 10 nanometer.
Right. Thank you.
Thank you, sir.
Okay, sir. I have only one question. Actually, you have prepared T carbon quantum dots.
Yeah.
But in the absorption, it is in the UV. It increase the absorption rate. It depends on the temperature. and you have shown that 45 degrees Celsius is increasing the absorption. So how will you conclude this? Because based on the temperature increase, the absorption will increase, or how will you conclude that?
No. After we have done to 50 degree, 60 degree, but at 45 degree it shows maximum.
At 45 degrees
it shows maximum for this carbon quantum dots.
Okay, sir. Okay.
And we have standardized this for the next detection purpose. We have to use that 45 degree. We have to detect at 45 degree only.
Yeah.
We cannot use 25 degree because at 45 degree we can get better result.
Okay. Thank you, sir.
Thank you.
Thank you, sir. Thank you for this nice presentation. Now, I call Mihir Kumar Sudar from the Department of Mechanical Engineering, Odisha, and the professor's topic is Influence on Different Process Parameters, the Mechanical Properties of Graphene Nanoplatelets, Reinforced Functionally Graded Material, and Overview. Yes, Professor Mihir, sir, you can start your presentation.
Yeah, good afternoon to all. Is it visible to all of you?
It's visible.
Yes,
Hello.
sir, visible. Yeah.
Yeah, thank you. So all the esteemed members present over here. I am Dr. Mir Kumar Sudar. I'm assistant professor in Bir Surendra University of Technology, Bulla. So today I'll be delivering a topic which is basically overview only. That is the influence of different process parameters to improve the mechanical properties of graphene nanoplatelets, reinforced functionally graded material. Okay, so the outline of my presentation will be a brief introduction. Then the materials and method includes the preparation of functionally graded beam, which is reinforced with GPL, and how to perform the experimentation. Then some basic mathematical formulation of a hybrid FGM GPL. Then comparison of analytical FEA and experimental data, enhancement of Young's modulus, enhancement of tensile strength property, different modeling techniques for effective material properties that have been used so far, and conclusion. This is just a brief overview till now. Now coming to the functional graded material, this is basically made of different materials whose property gradually varies from one layer to another layer, either in axial or in just a second, or in thickness direction. So it was first introduced mostly in the year of 1984 in Japan, where a space project was ongoing, and there is a sequel need for a thermal gradient of almost 1000 Kelvin. Okay, so functional graded material are mostly employed because of their varying functionality applications, and they're of different categories. They can be vary in concentration, as you can see here. They can vary in size, they can be graded in shape, they can be graded in orientation, they can have a continuous gradation also, they can have a layer wise gradation. Now why to reinforce this FGP with CNT? Because this carbon nanotube possesses a superlative property like high strength, high aspect ratio, high stiffness, and low density. Therefore, the reinforcement of this functional graded material with CNT leads to some excellent material properties. Now, coming to this reinforcement with graphene, compared to the CNT, graphene has a remarkable mechanical property that, for example, its tensile strength is in the order of 130 GPa, and the Young's modulus is in the order of 1 TPa, and but with comparatively larger surface area up to 2630 meter square per gram. The physical and chemical properties of graphene are also very commendable, and they can be functionalized as well. So one of the most important aspect of graphene is that graphene derivatives, that is your graphene oxides, GO, and graphene platelets, GPL, are available evidently in compared to CNT, and are very cheaper also. That's why they can be a good surrogate, okay, compared to CNT. Now, the analysis of the literature, the works done so far indicates that analysis of functional graded material reinforced with graphene platelets are quite scanty in nature, and analysis of various parametric influences and their optimization for better mechanical properties of functional graded beam reinforced with graphene platelets are very rare, and in axial direction they are very rare. Okay, most of the work has been done in the direction of thickness, but axial direction, very few works have been done. So that gave us a motivation to research in this particular domain. So coming to the application area of this FGM reinforced with GPL, they can be applied in the area of defense, sensor and energy, biomedical, nuclear energy, tool material, thermal barrier coating of rotating blades. Okay, and we'll be focusing mostly on this biomedical area in our research. So far we have discovered that this few works have been done that FGM was found to be an excellent thermal barrier for aerospace application, and also experiment results indicates some excellent mechanical properties of CNT reinforced FGM compared to the conventional composites, and the influences of volume fractions of carbon nanotubes and the S2 thickness ratio of the bending response, natural frequency and model shapes of the plates are predominant. Also, we got from the literature that the investigation results is a very close comparison to the data obtained from the various theories that been used by this author, and that this author discovered that the volume fraction of CNT reinforced with FGM beam is significant in longitudinal direction compared to the other direction during the analysis of FGM reinforced with CNT. And at national level, we have worked on this FGM, and we have proposed a generalized approach which is quite efficient, and the result obtained from the method that we have used is quite comparable with that of the literature and is very convincing. And also Jairaz and Rajkumar have obtained the static behavior of the composite plate was quite significantly influenced by the nature of temperature field and the nature of functionally grading of carbon nanoplates, nanotubes. Static bending deflection of the plate increases with volume fraction of the carbon nanotube, except for unsymmetrical distribution of CNT. Now, coming to the preparation phase, basically the preparation of this FGB GPL can be prepared by blending the graphene and epoxy. Then we'll go for a sonication that to give a sound frequency greater than 20 kilohertz. Then we'll dilute it. Then again we'll blend it. Then again we'll go for sonication. Then add some hardener. Then we go for blending again. Then we'll cast the bottom layer. Likewise, layer wise we can manufacture. Finally, we go for curing, and we'll have our FGM sheet. Then after preparation comes the experimentation, that is to find out some of its mechanical properties. So for this we have this very basic apparatus which is our resonant frequency damping analyzer. So in this single apparatus we can find out 5 most important mechanical properties, like your resonant frequency, damping characteristic, Young's modulus, shear modulus, Parsons ratio, etc. from this single apparatus. Okay, so once you get that through experimentation, then we went for the analytical approach to find out the properties using this rule of mixtures basically. So it is Boyd's assumption. It is based on the Boyd's assumption basically. So this one indicates